the vision is coming.
You should go to my channel. Go to my, when you have time, go to my channel and take a look at that interview that I just did with Sai Teja. I just bumped into him online, right? They're like, yeah, we've seen your stuff. We like your stuff. He's like, check this out. He sends me this video. And I don't know if you've seen that yet. So where I started with was this video of him in this fireproof jacket, but it's like normal fabric weight, right? And so I opened the video up, and he's like in this factory or something, and he's pouring molten copper on his arm, and it's just rolling off. And I was like, dude, that is so cool. So that's where I started. I was just like, okay, I gotta interview this guy.
Send me I'll put it on the note, but we'll touch base on WhatsApp here tomorrow. And give me that. I've got to write down and get some of the thoughts on the Magnons and the Manilas system before it gets I get too far on tangents. It's like there's so much stuff's going to come in through APEC and be like, oh, we got to follow. Which way do
I know. There's a lot going on. I'm struggling with the same thing. I have the day job, and then I have the conference, and then I'm doing the interviews, and I like doing the interviews. It's that there are a lot of different reasons for that. I do it for networking. I do it because I like to diversify and kind of just meet new people and explore new things, right? And APEC is kind of a closed group, not intentionally. It's just kind of a narrow focus area.
Yeah, it's a hard crowd to get into. Not get into, but you really got to want the knowledge that's here. I think Mark's gonna switch over to another computer, so we're gonna.
Okay. Yeah, we got about 2 minutes left, and I'm all prepped up. Shreesh is here, which is really awesome.
Okay.
So, yeah, this is exciting. And Shreesh, I owe you an apology for basically. I wouldn't say I misplaced it. What I would say is that I'm always juggling a bunch of stuff, and the challenge that I've had, this is like the last month, I have a ton of people that are really excited about presenting, but they keep pushing further and further out, and so they're like, yeah, I really want to do something, get me on your list for August. And I'm like, August? Man, I haven't figured out August yet.
August is like way down the road. Yeah, exactly.
Yeah, so that's the challenge. And so this week, so I would say like about a week and a half ago, I was like, okay, we're ready to go, except I don't have anyone for June 11th.
Everyone wants to go further down the road, not now kind of thing.
Exactly. Yeah, that's and that doesn't always happen. And then what's interesting is this week then, I was like, wait a minute, there's Shreesh. Okay. So you confirm, thank you, sir. And then I had my other guest, and then David Perez at the last minute. And then Michael Boyd, like yesterday, Michael Boyd emailed me. He's like, I got these videos. And I'm like,
my God.
What videos? I've never heard of these videos. So it was everything was like last minute this time, but it was really cool.
Yeah, it looks like a full house, just looking at the the schedule you have. I mean, it's like any other conference day that you have, right? I mean, it doesn't look light.
Yeah, and we had the other part, and I'll say this before we start rolling. We had a couple of folks that were a little disruptive, and so we did remove them from the conference. We're kind of trying to clean things up and take it back to its roots, kind of in some ways. So
okay, yeah, no problem. I mean, what I was confused about was I was not sure if you're getting my emails. The rest is up to you, like when you want to do it, because you've got I know you got loads of things. As you said, you got a day job also, everything, right? So, but because we exchanged a few emails, and then after that I didn't hear from you, so I said, okay, maybe because I've had this problem with my email. It goes to some places where then they say, no, we never received it. There's some really aggressive.
Yeah, no, I didn't have any problems with that. I got them. The problem is I'm just getting overloaded with emails. But Shreesh, let me do this. Let me meet you out, and then I will do our traditional intro, and I will hand everything over to you. Yeah, it is. It's super exciting to see everybody here. This is awesome.
Yeah,
it doesn't seem like it's been 2 weeks. Seems like it's been forever. Okay. Okay, and I'm going to put this thing on speaker view, and just for sanity's sake, I will spotlight myself. Okay. So counting down in 3, 2, 1. Welcome to APEC. It's June 11th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Shreesh Holla will present on the Quantumloop field propulsion technology. Jim Buckeyne will propose a mathematical model for quantized weight, and David Perez will discuss the variable electromagnetic drive. Mark Sokol and Aidan Schaefer will provide detailed lab updates in preparation for their upcoming experimental marathon, and we're going to be finishing off the event with an open discussion and ad hoc presentations by conference attendees. So, the normal quick reminders here. You can view our conference replays, details, and speaker info on our website at altpropulsion.com. Again, that's altpropulsion.com. Please save those questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. And I'll repeat that throughout the conference. That just makes it a heck of a lot easier for us to answer questions. You can also type those questions in the chat. We will go through them after each presenter finishes. So with no further ado, let me introduce you to our first guest today. Shreesh Holla is going to be talking about Quantumloop, a breakthrough field propulsion technology that functions as a unique thermodynamic non-equilibrium heat engine for anti-inertial propulsion by harnessing inertial vacuum energy. It's a highly scalable electric propulsion technology for high-speed, extremely low power consumption propulsion. Shreesh is going to discuss how it works and what makes it so unique. So without any further ado, I am going to place the spotlight on Shreesh, and I will ask you to unmute, sir. Oops, and oops, sorry about that. Hold on just a moment. There we go.
Okay.
Perfect. Perfect. Yeah, go ahead, sir. And you're happy to screen share that green button down at the bottom. And
okay, let me start that. 1 second. Okay, where's that? Yeah. Okay, can everyone see it?
Wonderful. Yeah, and okay. That is the yep.
Yeah, I'm going to start it as a slideshow so it's easier to see. Okay, so as Tim mentioned, firstly, Tim, thanks for inviting me to this. It's a great opportunity, and looking forward to talk about Quantumloop. And anyway, here we go. Quantumloop is an anti-inertial propulsion technology. So I don't have an agenda slide, which I should have, but basically I'm going to give a high-level overview of Quantumloop. And then I'll get into a little bit of the state of the art and that kind of thing. And then I will get into more details on the technology and the science behind it, and where we are at this point in time. So this is a high level. So it's an anti-inertial electric propulsion technology. So no reaction mass is needed. So basically the inertial vacuum background moves the vehicle directly. It is highly scalable because it's using ambient energies for propulsion. And there is some activation energy required to create the reactions inside. So that's quite trivial, which I will explain as we go forward. So theoretically, very high speeds based on an accelerating propulsion profile. And again, because it's anti-inertial, really speaking, theoretically, any axis propulsion should be feasible. And here's a kind of, I don't know how relevant it is for this discussion, but it's basically autonomous operation does not require anything because the engine itself can be configured to go in any direction. So Quantumloop technology. So again, so it's a thermodynamic non-equilibrium propulsion engine. It's based on this concept of anti-inertial thrust, which is an entropic thrust sustained by inertia. Okay, the engine itself is based on an optomechanical kind of heat flux system, and it is scaled by high frequency of these effects. So basically, it's a unique propulsion technology, since it's harnessing inertial fields in an assistive manner. Okay, and so basically, it's an unconventional kind of a non-linear propulsion system, because there's a certain non-equilibrium that's caused within the engine, which is measured by the vacuum, which produces propulsion. So a little bit of details. So basically, there's a kind of a virtual force which is converted into system momentum through our technology as a non-Newtonian type of propulsion. Okay, it's a second law of thermodynamics, which I will get into more detail. So we basically virtualize Newton's laws in a thermodynamic manner, which is made physical through this anti-inertial body force. Okay, and so basically the energy momentum is exchanged by space, as I mentioned, through the inertial vacuum background. And so energy for propulsion is coming from the vacuum background. Okay, so what we are really calling this thing as, it's a momentum machine, which is basically driven by momentum and not by a force, which is what we have conventionally in Newtonian physics, right? So as I mentioned, high frequency is a scalability option that we have. And here this diagram, I think it's there on my website too, if anyone has seen it. But basically, I kind of show that, there is something that's happening inside the yellow box measured by space, which produces propulsion. I'm just not focusing too much on this because I think everyone would want to know more of the specific details. So I'm just going fast here. So just, I'm sure most of the people here know about this. I mean, all propulsion today is Newtonian. So basically, we throw things out the back, different kinds of things, and it moves, really speaking. There's field propulsion, like solar, electric, magnetic sails. Of course, in the terrestrial, we have wind for marine. So there's various propellantless propulsion technologies which have been proposed. There's these inertial propulsion, beam drive, gyroscopic, etc. Just completely disregard those. Then there is asymmetric capacitors, but that didn't really work out too much, I believe. Photonic rockets, where basically there's a laser that is emitted, massive lasers emitted to the craft and spacecraft. So I think there's a lot of research going on in the academic and at various institutions, NASA, etc. EM drive, I'm still not sure if it amounts to anything much, really speaking. Then there's Mach effect thruster, which I think is doing well in terms of propellantless technology. I still don't know. I've never really understood how that handles conservation of momentum, but it's going a lot. So anyway, this is just a snapshot of. There's a host of other technologies that are there. I mean, including that have shown up at APEC and other places. I just want to give an introduction. So this is my opinion about propulsion problems. I mean, most new approaches are focused on the inside, and which I believe is more of an energy generation issue, and they do not focus too much on the external, because propulsion is about moving against the world, so to say, or the earth, or space, etc. So that is more important than what is inside. Field propulsion, of course, there have been various theories, but I don't believe there's been enough work in this area. Maybe because people are more concerned about what's inside, maybe. I don't know. And there's GTR theories, which, like wormhole, Alcubierre, I believe they're still at theoretical stages right now. So here's my vision for next generation propulsion, really speaking. So basically, field propulsion, harnessing field energy, preferably non-nuclear, but I don't know if that's feasible. Of course, it needs to be green and clean, given its field propulsion, really fast, and basically high payload mass capacity. And ideally, we want it to be universal, not just for space or not just for certain specific terrestrial applications, and needs to be highly maneuverable without kind of breaking the bank, so to speak. Okay. I need to make some changes here in that view. Kind of hides everything. Okay, I think that's good. Okay, so the next two slides is important to understand the quantum loop technology because it's the foundation of Quantumloop. Okay, so the first is the superstring propulsion. So I've just captured a snapshot of Minami's proposed superstring propulsion. So basically, what he claims is if there's an entropy gradient within a spaceship or an engine, really speaking, there's an entropic force from the superstring vacuum background as a body force. But this does not produce propulsion because space and the spaceship are held in place due to the act of emitting entropy at the ends, really speaking. Okay, and the action of the vacuum, the superstring. So what he claims is if you relax it, so basically a high frequency relaxation of the engine, you can get momentum as the superstring relaxes, really speaking. Okay, due to the finite time relativistically taken for the superstring to reach equilibrium. So from my analysis on this, this may be a problem because this relaxation still is in equilibrium with the spaceship. So I do not see that there's any way we can still produce momentum, really speaking. And second thing is this one is a body force. So any momentum that is achieved is still a body momentum. So we're not going to really see much of propulsion, really speaking, or none, as per conservation laws, etc. And that has been some of the comments on his theory, really speaking. So what it reads is Pinero's theory, which is the next slide, for system momentum. So I've just included a link here for anyone who's interested in knowing more. So Pinero came up with a symmetry breaking method, really speaking. As you can see, the diagram is pretty simplistic what he has, but basically this is the concept, really speaking. So he's saying if there is thermal gradient, as you can see, this thermal gradient between the ends of an engine, the engine is under non-equilibrium, and there is a momentum between the ends, as you can see this V1 that he shows, and there is a velocity space entropy gradient at either end. There is a net system momentum of this inertial vacuum background. Okay, so basically what I've deduced this as it's a separative change in momentum at the ends due to the thermal gradient of this VSEG. That is my short form because it's kind of difficult to keep on saying entropy space. Velocity space entropy gradient. So it's basically a separative total conservation of momentum. So basically we got momentum at the ends, and since they are asymmetric, the only way for the system is to conserve momentum is through momentum, actual system momentum, which has to be provided by the inertial vacuum background. Okay, again, I've linked the this theory here. Okay, so that's the background. So in terms of the technology itself, and this is a snapshot of what it is. So basically it's PNSB, as I mentioned, that's Pinero's self engine, which is produced of the MSFB, which is Minami's theory, scaled through a unique Doppler shift. Okay, so the MSFB itself is produced through a unique entropy gradient method that we use based off a thermo-inertial domain thermodynamic non-equilibrium method. So then the superstring vacuum momentum is achieved of MSFP by basically Doppler heating of the rubber-like superstring, really speaking. Okay, and it's asymmetric by definition by the PNSV thermal model, and so we get the the VSEG. And because we have the VSEG as per Pinero's theory, we get system momentum as mentioned before, which achieves thermodynamic equilibrium. So a little more detail on this. So basically we base it on a concept of an inverse Newtonian laws. So it's basically the right-hand side satisfying the left-hand side. Ma is equal to F. The reaction needing an action force, really speaking. Okay, so that's basically the basis of how this works, and it's based on this virtual Newton's laws, which I kind of mentioned before. So what I mean by virtual is a thermodynamically valid state without the dynamics in there, which is why it's virtual, which is made physical through this combination of MSFP and PNSV. So what we're referring to this as a superstring sail. So basically it is based off the superstring vacuum inertial background. Okay. Theoretically, it should be universally relevant and extremely scalable due to the superstring basis. As I mentioned, the Doppler shift is what scales the energy requirements as we go through accelerated propulsion. So that is through a kinetic energy Doppler effect. Okay. So here's my view, and this is of course questionable. Of course, normal Newton's laws are the vacuum provides the laws, and we supply the energy, as we know very well, right? Energy storage in some form, right? The inverse Newton laws is, of course, inverse. So basically, we supply the laws, not new laws, the same laws, but we need to supply the capacity for those laws, and the vacuum provides the energy. That explains the energy efficiency that I'm claiming. So this is a high level concept of the design. So basically, we have a spring in place of Pinero talks about particles, but basically we use a spring to scale the technology, really speaking, producing the same momentum at either end. There's a method to produce an entropy gradient at either end. This is again different than Minami's theory. Minami talks about one entropy gradient through the entire ship. So what we are doing is we have an entropy gradient method at either end, really speaking. Okay, and okay, so I'm just going to get into a little more detail here. So if you look at one, it's basically the classical. There's some force within the system, within a closed box, pushing on it. Of course, conservation of momentum. You get the dotted arrow on the left. Nothing further there, right? So what Pinero is telling is, if at these ends you have this VSEG, which is asymmetric, that's when you get momentum. Okay, system momentum. That's where the symmetry violation occurs, really speaking. Okay, because as you can imagine, otherwise we have Newton's third law, which would basically leave no external momentum, really speaking, right? Which is what Pinero also talks about in terms of a canonical momentum. If you have the same, if you don't have a thermal gradient, then basically it's the same as any closed box. So basically, the way we're doing it is so if you look at two is basically a Newton's third law, but using the superstring force. So because of the conditions that we've created, there is an entropy gradient. So instead of the normal reaction force, we have the Minami superstring force acting as the reaction force. But due to the existence of this entropy gradient, actually it's reversed, as I mentioned, it's inverse Newtonian. So basically the superstring force acts as an action force, and the internal forces that you see here is now become the reaction force. Okay. So then, as Minami says, we have to relax it. So once we relax it, we get we should get momentum. That is what 3 shows, really speaking. So basically, we get momentum here at the either end, really speaking. And as I mentioned, just using Minami's theory is for relaxation is theoretically feasible, but from my understanding, it requires some seriously large volumes for anything usable, really speaking. And that's why we are using this thermodynamics of the deep brain, really speaking. Okay. So that's what I mentioned, the rubber-like thermodynamics of the deep brain. Okay. Now, as I mentioned, if they are asymmetric, which it must be because of the temperatures at either end, we get the VSEC. And so, as per Pinero's theory, we should get net system momentum in maintaining conservation of momentum or translational symmetry. Okay. So the way this works is this relaxation, just to clarify this point, these are the entropy gradients that I mentioned, just a kind of like a block diagram to show what it is. But there is some way to switch them off, really speaking, and that starts the relaxation process through time. And that's how we get what you see in 3. Okay, and so that's when you get propulsion, which is now the blue arrow that you see down here is propulsion because of conservation of momentum. So I've kind of so one of the things is I've been kind of modeling this as a or saying that once you have momentum here, you should have an inertial force, really speaking, which is of course in reverse. So that is what is the inertial vacuum background, which produces momentum to this side, which is the direction of the blue arrow. Okay, so here I'm just kind of it may be evident to some of you, but basically I want to show how this works. So the analogy of rubber that Minami mentioned. So I'm just showing that. So basically you have the normal deep brain, and then you have the stretched deep brain as when the Minami superstring force occurs. Then we have the compressed deep brain, which is basically either achieved through through Minami's relaxation method, or as I mentioned, through our thermodynamics, so where we heat the deep brain, really speaking. Okay, so that produces a velocity of the deep brain, as we know from rubber thermodynamics, which is now VSEC, and so we get Pinero's conservation of momentum, total conservation of momentum. So just to clarify what I mentioned in 1 is, if there was no such thing as the VSEC, then it's just basically a very well-known box of forces. Okay, so a little more in depth on how this works. So basically, equation number 1 is basically showing what Minami talks as an entropic force, really speaking, through the superstring. Equation 2a is basically Pinero's theory. So basically, he says when you have P1 and P2 momenta at either end, then there is a momentum of the vacuum background. And this is through a velocity space entropy gradient, the delta Vs, and based on this, based on the entropy gradient at either end. Okay. So what he says, this must be a change in the system momentum by the inertial vacuum background, which should be the delta rho 1 rho Im called. Okay. So this continues occurring if it is sustained, continues occurring as you can see in equation number 3. So delta rho V by delta T must be equal to system acceleration, really speaking. And so basically if we can have the delta rho V itself, changing at the same rate as a certain frequency of activation, then we get that level of frequency, that level of momentum. As you can see, there's no force here. Okay, so this is the notion that I mentioned some time back. It's a momentum-driven propulsion. There's no force involved here. Okay, so to scale this delta rho v t, then we basically 2a needs to be monotonic, of course, which is quite evident. So then the last one is basically showing the basis for the thermodynamics of the deep brain that I mentioned. So basically, KQ is as an internal quantum loop factor. FEI I mentioned is the superstring force, and you see the 1 by T, 1 by T. So it's an entropy gradient, really speaking, for at an end, really speaking. So just basically summarizing here, right? So we have the rho I, which is the rho 1 and rho 2, which is asymmetric. And so there must be some manner of correcting that asymmetry, which is rho v, which is what Pinero claims. So here I just want to draw it like basically what I can see as Pinero's theory is basically connecting MSFP, actually speaking. It can be seen as a combination of Newton's second law and an entropic force as you transpose factors here, really speaking, as you can see in the second line. Okay, but this again does not produce any momentum because any system momentum, because this is still a body force, body momentum. So it's still on the system, so to say. We need the full PNSP, as mentioned before, to see any system momentum. Yeah, I just wanted to give a little more details as much as feasible at this point of time. So basically, as I mentioned, the biggest, hardest problem that I've had is basically the entropy gradient of Minami's, actually speaking. The issue, really speaking, is that it needs to be measured by the vacuum. And normally we have second law of thermodynamics, which would invert any entropy gradient anywhere. So the solution was basically determine a way to basically pause second law of thermodynamics itself for that momentary period of time by pausing entropy generation. Okay, so that basically results in a thermodynamic non-equilibrium state. Okay, so so basically Minami occurs and the whole quantum loop reaction occurs to re-enable this second law of thermodynamics of the deep brain, increased deep brain entropy, which achieves thermodynamic equilibrium. Okay. So the other big problem is a body force. So Minami claims that this is a body force, but we can't have a body force which is occurring from the outside to suddenly become part of the dynamics of a system, really speaking. So so this was the other hard challenge in trying to mix delta SR and this body force notion that Minami claims. So this is where the virtual Newton's third law really comes in. So basically, create a thermodynamically valid dynamic state, in terms of thermo-inertial behavior, which basically shows that there's a reaction force, but there's no action force, as I kind of mentioned before. And so MSFP, the superstring entropic force, can occur as the action force. Hence, also the inverse Newton's third law. So action is occurring before the action is occurring on the reaction, not the other way, as it's normally known. So this can occur because of this non-equilibrium, because of this delta SR. Okay, so then the relaxation is under one problem, really speaking, because we need to have high frequency operation of the engine, but we are talking thermodynamics also out here. So we have a finite time of relaxation required, but if we stretch it too long, then the second law of thermodynamics will kick in to some other means. So there's a bit of problem there. So we use photonics methods to do that. So basically, this is a very important part, really speaking, because normally you can't just switch off a reaction force or an action force, really speaking. I mean, rather you switch off the action force, the reaction force is gone, really speaking. Okay, but in this case, we have one side existing and suddenly we switch off the MSFP, which means there is some reaction that needs to occur to counter that. There's momentum of the MSFP while the normal reaction force can start occurring again. So, oops. So this is the other part. This is the part of Pinero's theory now. So I think I mentioned this a few times. So basically, the rubber entropy. So we basically we insert an entropy gradient through photonics to achieve this rubber, this heating of the stretched deep brain, as I showed some time back in terms of equation number 5. And so again, this is again a virtual Newton's the second law, as I mentioned. There's a thermodynamic state which indicates momentum is actually occurring, but it is not occurring, really speaking, which is now solved as an ma is equal to F, really speaking, because F is a body force, really speaking, right? So, but it occurs as a rubber-like momentum on the deep brain, or velocity of the deep brain. So as I mentioned from equation 5, there's a 1 by T there. So that requires infinitesimal heating, really speaking. Okay, but I mean, that's something that's very well known from rubber theory. So that's quite well known in that way. Okay. So one of the challenges also that I've been facing is the VSEC that I mentioned, that's the delta VS, needs to match the rho V, really speaking. Otherwise, if you're scaling rho V, you got to scale the delta VS also, really speaking. So the approach for that I've been working on is using an acoustic Doppler shift for this, just because we need to have, it needs to be linear, really speaking. So basically, this slide really shows how I'm claiming that kinetic energy can scale the propulsion over these Doppler shifts. So the actual scaling, well, of course, the conventional way would be, really speaking, an input force. Just put in more force, and we should get more propulsion theoretically. Okay, possibly the thermal gradient also can be used to scale it up, really speaking. I've not really experimented too much with that, and that's planned. But theoretically, that should also provide enhanced propulsion, really speaking, from Pinero's theory. Okay, but definitely, if you reverse the thermal gradient, what I'd shown before, you should get reversed propulsion, really speaking. But I think the big thing, really speaking, in scalability is this frequency of activation that I mentioned. In a previous slide, I mentioned NT. So basically, that equation 3 indicates a linear relationship between delta rho V and the frequency, really speaking. So as an example, theoretically, we have 1 Newton being produced at 1 kilohertz. So what this means is 1 Newton produced 1,000 times a second. We should theoretically get 1 kilonewton scale through the D brain, really speaking. So basically, I don't think this is 1 kilonewton, really speaking, and this is just so that since we all understand newtons very well and forces. But as I mentioned, this is a momentum-driven propulsion. So the reason this would work is because of the MA that is being produced through the heating of the D brain. So basically, each Newton of force that is there, as an example, needs to satisfy the MA, and so we have this inverse Newtonian MA that really makes it work. Okay, but yeah, basically based on that, the energy needed is really for 1 Newton, really speaking. So that theoretically is a massive amplification of power output. Again, the efficiency, I'm sure this must be evident. I mean, since we're talking about energy being inserted into the system by the superstring vacuum, it must be greater than 1. And given the kinetic energy Doppler shift, this efficiency should continuously increase through system velocity. Okay. And again, this may be a little bit smaller in terms of the other two, but based on how we control the asymmetry, we should get an increase in efficiency too. So just summary kind of thing, value proposition. I mean, I think this should be evident. So basically, it's an anti-inertial propulsion, so it's propellantless. So for terrestrial needs, we don't need any propellers, etc. So that should also be a significant energy gain because we're not rotating heavy air or water, as an example. Again, as I mentioned, it's very low power needs. So it's highly decarbonizing propulsion, whether it's terrestrial or extraterrestrial, so to say. And as I mentioned, it's theoretically it's bidirectional. Not theoretically, this should be possible. And basically, by controlling the internal momentum, really speaking, we should get almost any direction propulsion. And direct propulsion, okay, that's fine. Okay, it's kind of evident, right? And of course, should be lower cost, should be relatively simpler to construct, and theoretically it's usable in any environment, really speaking. I still don't know if it will work under water or under fluids, really speaking, but definitely surface transportation, air, space should work quite well. And this has been my biggest peeve about propulsion today. It is just keep putting more and more energy in, and so I like to look at this as an intelligent propulsion technology, which basically is not just yet another third law solution. So summarizing what it is, so basically constant force, constant acceleration, and constant energy. Inverse Newtonian model satisfies symmetry laws, as I mentioned many times before. Scale due to the ambient energies, and should work anywhere. And I don't see this working in a stationary or rotational manner, really speaking, and not really thought of that, but it is meant for propulsion, really speaking, linear propulsion. So as I mentioned, it's a momentum machine. It is not a conventional Newtonian machine, not an energy machine. And so given it is an inverse Newtonian, I would call it non-Newtonian, but theoretically in the end it is Newtonian, really speaking, because of the conservation of momentum aspect of thin arrow. But yeah, it's controversial, of course. I think everything that comes up here on APEC is controversial, so that's nothing new. So where are we right now? So basically, it's about TRL4. Most of the things have kind of have been proven. There's still some more work on some of the engineering issues in terms of has some various alignment issues with those springs, etc. Then some of the Doppler shift algorithms are still in progress, really speaking. Material design is pending, really speaking. I mean, definitely looking to get more into that because that's quite important for this kind of thermodynamic system. Because once we get there, we want to get more detailed tests, and so more study is required, and the photonics are required, really speaking right now, because right now I'm using simple laser and LED array, really speaking. So I need to study that more. So the other thing is compute. I mean, given the all the complex algorithms and timing and frequency needs, I'm running it off an Arduino, and I've been able to max it out at about 20 hertz. That's about it. I really, to get some serious scale, we need to go beyond that, but which is not possible in software. We need an FPGA or something similar for that, really speaking. But that's not feasible at this time. Maybe sometime in the future. Okay, and yeah, the simulation. I've not really gotten into it. I think that's a really complex problem, really speaking, given its non-linearity, the thermodynamic non-equilibrium, and all that stuff. So it's the to-do, really speaking. And at some point of time, we will have to get into some external validation. And okay, myself, I'm a mechanical engineer. I've been in various different areas: automotive, satellite communications, and consumer electronics. I've been an engineer. I've been product manager. I've been a few companies. I've been in Qualcomm. I've been at Lucent, Alpine Electronics, etc. One advisor who comes from GM, and he's recently retired, I think, over the last year. So been quite helpful. Also a member of LACI. I don't know if anyone knows about this, but LACI is a clean tech incubator in LA, and I'm part of the innovators cohort there. So yeah, summary part two, really speaking, it's a unique breakthrough propulsion technology. It's been there for about over 3 years of R&D, really speaking. I think there's a lot of new things that we could not do would become feasible once we have better progress on this. And of course, I'm open to, the right people, organizations, etc. And just a little bit of, I think I've talked about this. I'm not really going to dwell on this, but basically, given that it can achieve anything, I just kind of called out the different places it can be used. Okay, that's it.
Wonderful. Wonderful. Shreesh, thank you so much. Okay, so let me do this. I removed the spotlight. I believe that all of our spotlights are gone now. I'm going to stop the sharing. Perfect. Okay, so before anything else, I want to put this thing on gallery view. Everybody, please give a giant hand to Mr. Shreesh Holla.
Thank you.
A wonderful and in-depth presentation. That was really in-depth too. I was really amazed. Thank you so much. Thank you so much. Thanks. So we're running a little bit ahead of schedule. So what I want to do is this. Let's go to our Q&A session. So we're going to go to Q&A session now, and let me see.
Oh, it's a 1 hour long presentation, right? So I beat it. For the first time, I've done a presentation within time. Wow. That's a new thing.
Yeah, no, that's awesome. That's awesome. And you know what? I mean, this is it's kind of our tradition, right? We try and like to keep things mellow, but we set 1 hour for the presentation and 1 hour for the Q&A. And what we found is some folks run under, other folks run over. We actually had Bob Greenyer. He did 2 hours, and he's like, I gotta come back. I gotta come back and do more. I'm like, okay, but and then other folks do half an hour, and that's their entire thing. So we try and keep it flexible that way.
Okay. Some people have a lot to talk about, and some people say it briefly. Okay. Yeah.
So it kind of comes and goes, I guess, depending on the guest. But this is just me from my perspective. I look at everything that we do as we're creating kind of an archive, right? Not just to communicate to people today, but a record for people who are designing this stuff in the future. And so I'm always really excited just to capture whatever we can, whatever people are willing to share, and get it out there,
Yeah.
So, well, yeah, so let's go to Q&A. And so you guys can raise your hands using Option Y on Mac or Alt Y on Windows. And I will do my very best to keep up with you. Let me bring the chat window over here. Okay. And again, so Bill Alec, sir, go for it.
Okay, can you hear me okay, Tim?
Yeah, and I just changed it so you guys can unmute yourselves now too.
Okay, great. Shreesh, well, let me see if I get this straight. Are you modeling a photon with this? Because a photon has momentum.
No.
But no mass.
No. It's nothing to do with photonic. It's a superstring propulsion technology, really speaking. So basically, we use photonics to create a state of non-equilibrium. That's an internal thing, but it's not a photonic rocket. It's a superstring rocket if you want to look at it, really speaking. So just to simplify it again, so basically we use the superstring entropic force to create Newton's third law. Then we switch it off to get Pinero's velocity space entropy gradient, which produces momentum against conservation of momentum. But it's not a photonic rocket; it's a superstring rocket, so to say. That makes sense.
Well, I'm still trying to wrap my brain around it.
So think about it, right? There's an entropic force. Forget the superstring, right? Okay, there's an entropic force from the vacuum, really speaking. Given certain conditions, there's an entropic force from the vacuum. So that's what we use it, really speaking. Okay.
Yeah, it kind of reminds me of like something along the lines of switched reluctance type systems.
Oh, okay.
Where you switch the reluctance, in magnetics.
Yeah, I think I would say the Mach effect thruster, right? I mean, that one I think does something like that, really speaking, where they have a reluctance, they have an inductance and a capacitance which they switch on and off, really speaking, to get like these transient mass changes, really speaking, which is inside a system. So I think that fits that better, really speaking. From whatever I've read. I mean, I don't know much more about that, but basically that's what they're doing. So that may be more of a switch reluctance kind of method that you mentioned. But maybe ours is also something like that. I mean, I've never thought of it that way, but basically it's a way to get this entropic force in, switch it off, so to say, and get the momentum and get translation symmetry to work to produce momentum. In simple words, that's all it is.
Okay.
But as you know, the simplest things are the most difficult. So yeah.
Okay. Thank you.
Okay. Thanks.
Awesome. Okay. So, oops, just lost my mouse. There we go. Okay. So let me see. I've got lots of clapping. I'm just going through the chat thing. So Rob Chambers posted the Pinheiro paper, archive.org. Yeah. And he put a link in there. And again, I want to see some hands up in the air, guys. Option
was it too much? was it too, I mean, that's fine. I mean,
no, it was really intense, but intense is good. I mean, I love that. Right. So yeah, no, that's not bad at all. There we go. Jared, go for it, sir.
Hey, Shreesh, excellent presentation. Really interesting. I had a couple of questions just that I was writing down as you were going along. So you're talking about a heat flux, right? And an entropy difference between the ends and the middle. Right off the bat, it sounded a little Maxwell's demon-y, but I think you kind of addressed that a little bit. But do you think you might be able to address that a little more?
You mean the Maxwell's demon?
Well, how it applies to your tech, because it sounds like you're trying to pause entropy, right?
Yes. So Maxwell's demon occurs in an entropic state, right? I mean, basically under a second law of thermodynamics, really speaking. But if you don't have second law of thermodynamics, then we don't have any heat flow happening within the system. That's what I mentioned by entropy generation. There's no entropy generation. We pause that. And because we can't have the second law on pause, really speaking, so that's when the rest of the quantum loop reaction occurs, so that we have space plus system increasing in entropy, really speaking. Okay. So does that answer your question?
It does. I had a follow-up as well. So you were talking about on the string side of things, forgive me for not being very familiar, but it sounded like this was more of a D1 system. Did you calculate it for higher dimensions, for like D2 or D3, so that you can actually have curved and not just linear momentum transfer?
Curves is a bit of a problem, really speaking, right? Because the problem with curves is it starts getting into nonlinear. So here's the challenge with this, right? It's a nonlinear behaving system, but it's highly linear. Okay, so basically we can't. I mean, in fact, my original thinking was that, to use use a 3-axis method to build this out, really speaking, so that way we can, vary any axis to get any direction propulsion, but it does not work that way. So it has to be linear only, really speaking. But again, let me rephrase that a little bit. Maybe it's possible. I've not reached that point yet. Okay, if you're going to do something in a curved space, I think the physics will change a lot, really speaking. So because right now it is, I look at it as a completely STR system. I mean, so basically it's completely linear, and it's so far more modeled, and it performs on that basis, really speaking.
Okay. Final question for you. So I didn't really see any kind of materials or any kind of like mock-up on what what the dimensions or the requirements for such propulsion
actually,
drive
I forgot. I have a first stage. I mean, this is not the current one, but I have a video that I can show. I just totally forgot. As I was talking, I forgot to do that. So Tim, can I just show that video?
Yeah, absolutely. Yeah, just hit the screen share button. And hopefully it's not copyright. We run into issues with that.
No, it's not. I mean, the new one that I have, it's kind of proprietary, so I'm not showing that one. I still have to determine what I can show and not. But this one, okay. Can you see my screen?
Yeah. There we go.
Okay. Okay, what happened to this? Why is it not going? Yeah. So basically, this was almost like the first version, really speaking. Okay. Don't bother with that heat flux frequency 1 kHz. That was not right. But, So this is the one that I kind of mentioned. I tried it with 3 axes to see if I can get the entropy gradient in this way. Yeah. So basically what this is showing is, as we produce this one is basically in terms of the what's the rubber entropy. I mean, basically I'm relying here on the external ambient lighting, really speaking, to produce this. So basically I show in this that, all of these needs to be enabled, really speaking. So I don't know why it's jumping to and fro. Okay. Okay. Let me stop sharing. I don't know. Stop.
Okay. Yeah. And I can. I was gonna say I can stop that for you as well. So again, guys. Oops! I just lost my window. Option Y on Mac or Alt Y on Windows. If you have any questions.
Yeah. So I just wanted to finish off with Jared. I mean, Jared. So do you get an idea of the dimensions? I mean, the current one would be a bit more. There's a little bit more moving parts, really speaking, because there's some challenges with as I mentioned, in terms of the velocity space entropy gradient, to get them to be scalable. So there's a little bit more, but that size that you see should be around about what it is.
Sorry, more questions. So what would be the thrust to mass ratios that you think you could get, and what was the deal with the spring thing on top that you were wiggling?
Yeah, so this is the first version, right? I mean, so basically that spring that I was pressing on top, I showed it now as inside, really speaking, in the, right? So this is what I mentioned. This is the first version. So I was trying to look at, so basically what I was trying to do is, since it's orthogonal, really speaking, we can move the spring. It's actually speaking, even at that version, it should have been inside the box that you saw. But for a video diagram, it would be very difficult to see it if I did anything inside the box, right? I mean, so that's why I kind of showed it up top. But it's just for video demo, really speaking. Okay. So thrust to mass. So here's the thing. I will answer that very. It's kind of a difficult thing because of the inverse Newtonian thing. It is not a thrust-driven system. It's a momentum-driven system. So I can't call it as, okay, it produces 1 million newtons, because it doesn't. It cannot. Okay, but it's a momentum-driven system, which will effectively produce what, say, a 1 million Newton system would potentially produce if the conditions are right. So this is what I mentioned. We got to look at it the other way, right? From a momentum perspective. Okay, so to answer your question, really speaking, you can take 1 Newton theoretically. Okay, I'm just telling you right now, right? If you say 1 Newton, I showed a small calculation there. It runs based on a frequency. 1 Newton run at, say, 1 megahertz would theoretically, mind you, I only got up to 20 hertz, really speaking, but theoretically that should get 1 megahertz. How is that going to scale? Because the entire system is scaled on the kinetic energy to the Doppler shift, right? So that keeps on pulling, it's doing a full pull at either end. So that is scaled to the Doppler shift. So theoretically, it should work. Yeah.
Yeah, there we go. So there's a lot there. So guys, and again, we're running ahead. We're actually at the top of the hour. If that's it for questions, I'd ask Jim if he might want to present early. And he certainly doesn't have to. If we have more questions, we can go up to the full 2 hours. We're running way ahead, but okay. Well, Shreesh, why don't we do that then? So you know what I'm going to do. We didn't have a lot of questions. So yeah, no, that is again. Thank you so much. Let me put this thing back on gallery view. Everybody, please give Shreesh Holla a giant hand. Sir, thank you so much for presenting for us.
Thank you.
Yeah, sometimes they run fast, and that is completely awesome. We'd love to have you back if you have more that you'd like to share as well. I mean,
definitely. I mean, I think I'm making some, as I mentioned, there's some alignment issues. So I think once I've got them, where I've got a more reliable, demo, really speaking, I definitely will let you know. And yeah.
Yeah, absolutely. Okay, well, Shreesh, thank you again so much. So let me do this then. So we do have Jim with us, and he's ready to go early. So what I will do is, and again, please forgive me for being a little kludgy. The timing part gets me sometimes. Jim Buckeyne is our next guest. Oops, and you know what? Here, let me spotlight myself here. There we go. So Jim Buckeyne is our next guest. Jim Buckeyne has been working on using 3D rotation for vectors, for rotations rather than quaternions, matrices, complex numbers, etc. This eventually overlapped quantum mechanics spin and let him investigate possible applications. So in this presentation, he's going to reframe the existing 4D spacetime as 7D, which is 3 linear velocity, 3 spin, and 1 time. And he also has, he sent over some links to his channel. Jim has a ton of videos that he can show us. And so he can do that during the presentation, or we can go through some of those in the Q&A session. But he's got lots and lots of material. So what I want to do is, Jim, let me ask you to unmute.
Hello?
Yeah, and actually, sorry about that. It's jumping around on me.
Sorry, yeah, I'd like to use this as camera.
Perfect. Okay, there we go. Okay, and Jim, I can't see you.
I see.
Oh, there we go. Okay. You know what? Sorry, I wrong one.
Well, it depends.
Perfect. Okay. I've got you.
Let me see if I can flip that back around.
I can add that to the spotlight if you want, or if you want to just do a screen share.
Well, I'd like to use this other as my screen share. If I can.
Okay. Well, what I can do then is I will add to spotlight, and then it's side by side.
Okay. Sure.
Now, I should mention that's inverse. There we go. Do you think it would be okay? Actually, it is looking a little wonky. Would it be okay if you did a screen share and screen shared that second one, or is it a separate computer?
It is a separate computer.
Okay, that's fine. I've got it set up then.
If you just want to spotlight that though, because I mean, I'm just talking over the top of what I'm showing.
Well, I always try and have the guest. I always try and do that. So it's fine. I've got you side by side though, so people can zoom it up.
Okay. So, I don't know where to start. My journey is long and twisted. Where I started is not where I ended up. But I'd like to start at really the beginning of time. Before anybody has anything, you could have some balances. You could, weigh things on scales. You can figure out that for a certain amount of things on one side of the scale or another, it's at a certain tip.
Oh, Jim, I'm sorry. You have some background noise. It looks like there's some music. I'm sorry about that. It's kind of coming through and then disappearing. It's disrupting.
Any better?
Much better. Thank you, sir.
Sure. So, turns out that if you have like a 2-to-1 ratio, that's at an exact 45-degree angle. And why this is important is because that exactly overlaps actually Bell's theorem, and that at 45 degrees, you'll have a 50% correlation of quantum results. Or, through polarizers at a 45-degree angle, you'll have basically 50% transmission. The difference is that near zero, where it's almost balanced, there's a slight red line above the bar that if I calculate this ratio as a simple ratio, it's a certain tilt. If I apply basically the classical mechanic harmonic oscillator to it, which is what the term in Bell's equation actually is an oscillator between the upstate and downstate simultaneously, then that ends up with a function of cosine, and the result is not the same. So I have this test that at like a 3-to-4 ratio, a super simple count of things. If I can get it, then it's a 22-degree tilt, and classical mechanics would predict that as 20 degrees, which is only 2 degrees different, but as a practical physical experiment you can do without a particle accelerator to test whether hidden variables are even a thing. To go back to Bell's equation, in his original paper, he actually even proposed that there was a spin axis that, as a reasonable idea for the missing variable would be the spin axis of the particle, since you have spin. So I started working on this a long time ago, and this is pretty cryptic. I have basically from the North Pole, there's a rotation vector that happens that a rotation vector is axis and angle, that you have a direction vector and a amount around that direction vector that it rotates in a certain amount of time. So if you have like 45 degrees in 1 second, around this rotation vector, then around this direction, then you have this axis times angle that's just 3 coordinates to start with. It's very much like working with velocity. Instead of having like my X, Y, and Z direct velocities are this. I have a direction vector and a speed that, there's a direction and a speed, which doesn't make that a four-dimensional thing any more than axis and angle makes that a four-dimensional thing. Many of the interpretations of spin axis, like quaternions, expand this three-dimensional term into four terms, and you get what seems like a four-dimensional thing. But it ends up really just being three-dimensional. And there's this curve that exists that covers 720 degrees, and at opposite ends of the curve, opposite opposing sides of the curve, it's exactly the same looking kind of frame, but it's not really, because you have a different magnitude of spin. The spins are all positive or all negative. There's no change from one spin direction to another spin direction. I propose that because that leads into explaining charge as a positive and a negative. I don't really know how far to go. I get the graph of these points out on the outside is really rotation vectors that they start at the origin and they point to that direction, and the length of that vector around and the direction of the vector determine what that spin was for that particular matrix. So walking along, I can share some of these simultaneously here. And I have some neat presets for this. This is basically what you call hop fibrations, HOPF. That each of these loops is almost exactly a circle, and it's looped through itself all the way around continuously. But it's really just a combination of three rotations, that you have a spinning thing that's being spun around another axis that then is being spun around another axis. So you get these combinations of spins that results in these really neat shapes. Some of these are kind of wormhole-like, that you get this path through the axis where there's not a lot of change that happens.
Yeah, and Jim, if let me apologize sincerely for jumping in. So, okay, yeah, I just wanted to see. Yep, everybody's seeing they can see both. We have one person in the presentation who can't see both, and they might be on a different device, but it looks like most people can see both of your presentations. So I think we're good, and please accept my apologies, sir.
No problem. Really, if you'd just like to focus on the screen, I'm still here. And I'll be a little icon up in the top or something, right? But other than being pretty pictures, this in itself doesn't really do much. Some more practical examples. This is where I can actually show this basis map, that for every XYZ point in a range, I show exactly what that grid is, because this sort of rotation in this as a rotation vector is additive, and you can get from any point to any other point with an addition. If you have a spin axis like this and a spin axis like this, you end up with a spin axis that's like this. It ends up being the direction between the two vectors. The within this grid, there's constant twists, except up to the outside. Every point on the outside of the sphere is exactly the same as the inside the center sphere. So at your origin, you actually don't have a singularity, you have identity. That there's no change in any particular direction, so it doesn't matter what direction it is. Under most of the circumstances, though, when you composite all these rotations, very few of these actually go through the origin. It's very hard to get to identity as an active rotation. So this is just, I started with basically 4-5 nested frames, like a labyrinth marble game where you can tip the table in various directions, except to actually have a spin that could spin the table around. But I don't want to go there yet. Normally, like, Euler angles are mounted because you have a motor that can go in one direction, and you have another motor that's mounted in another direction. So your composite angles out of this are always going to be order dependent. The mounting of where you have your spin axis and your pivots is going to be order dependent and not just a rotation vector. Rotation vectors more apply for, like, spacecraft and engines that are offset in various directions, that when you fire all these thrusters, all of those spin vectors add together because they're all being applied simultaneously. There's not a step function to carry you from one to the next. So I spent a lot of time investigating all these rotations, fiddling with this particular demo. There's a ton of hidden options. There's larger ranges, so I can kind of flip tables around multiple times. And there's built-in, like, orders of rotations to follow. I guess I don't want that. These 3 circle curves that intersect out, these opposite points are the current point, but not the current point. It's the same orientation as this. If I rotated all the way over to that side, it would be exactly as if I was here. As I move these rotation curves, they're all 720 degrees all the way around each one of those. There's really nothing special about 720 degree spins. It's just the way rotations work. I don't really know where to go. I went through and replaced there's this physics engine called Canon ES. That's a JavaScript physics engine. It's really small and lightweight. And I went through and replaced all of the quaternion math with rotation vectors. And much of it actually simplified up to the point of actually adding the forces when a collision happened. Although after playing with the fulcrum with the balance beam, I'm finding that the calculation that is used for that collision may not actually be correct. because when you have a collision, you really have the center of mass of the body as the fulcrum, and then wherever you hit that is the amount of bias from that fulcrum that you can be up to the very edge of the object. So there'd be a scalar of 0 to 1, but then your momentum into that is your weight on that balance that causes it to turn. So the balance experimentally, how do I get back around to the other thing? There's this. So I took these spin vectors, which actually quantum mechanics doesn't actually have, because they take sine and cosine of the vectors and put them back into an imaginary number, and then you have part of this angle, and then when you combine that with all the other three angles, you get various parts of all the various fractions of the angle mixed together, and you don't actually have that original spin axis. You can sort of recover it because it all sort of scales into the same thing. I really like just this, I guess it's so when I got to playing with polarizers, and that the gradient of a polarizer lets only a certain axis of spin through, that 50 degrees, 90 degrees of it is blocked, 90 degrees of it is allowed through. But just because it enters at somewhere in that 90 degree plus or minus 45 degree range, it comes out in any of that range. It doesn't have to be in the same range it started with. So as it passes through, I have these on the right side. I can't point. This is like polarizers being tilted. And as you tilt them to 90 degrees, they become totally opaque because whatever can pass through one and then might come out is entirely blocked by the other one. So I got these graphs. They're pretty pictures, they're numbers. This is from a numerical simulation. I started with, it's kind of hard to show, but it's playing thousands and thousands of games and getting this curve out. And you can't really see it on the screen, but there is a green curve, which is the quantum mechanics prediction, that there'd be that the angle of the polarizer is just the dot product of the polarizer, then basically, or the cosine of that angle. It ends up being more an overlap of these arcs, that you have a potential arc that any of these could go through, and then this inner arc that is the amount that actually do go through, and then it's the ratio of those two inner arcs and not some piece of the arc to the whole. So again, here at 45 degrees, I have exactly matches the Bell inequality. So local hidden variables aren't disproven, just bad accounting of them. Because you can also measure this, that the statistics are 1 to 2. So I have a total of 3. So the samples is 33%. But that's not the true, because when you weigh that, 2 to 1 is a 45 degree tilt. That's 50 degrees or 50% of 90 degrees. The tilt of this balance is the same as these polarizers in that it's measuring intensity. It's comparing one against another. you can't have 100% intensity without having 0% of the other. You can't have total black if you have any photons on the other side of the balance. Your extremes of what you can actually get out of momentum is all in one or some balance in between. The pardon me, my voice is getting really rough. It works the same for, there's this Stern-Gerlach device that is a magnetic configuration that particles pass through and get sorted. There's basically a North Pole on one side and South Pole, and it's kind of a V shape that are nested. I can't do it with my fingers. And then at the other end, the particles come out as up or down. That's not really sorting up and down, because as the axes are going through the magnets, they're actually passing horizontal along the magnetic field, and you're really splitting them to left and right. That the precession of the torque on the magnets as the particles are going through more towards right will send them down, or more towards left send them up, or conversely. And like a Stern-Gerlach, you can measure both whether it was spin up or spin down, but passing through those magnetic fields, again, affects the particle, and it comes out as more towards the right or more towards the left, but not necessarily perfectly left or perfectly right. None of this is exact digital results. It's all very analog. Entanglements happen. I don't know. Can I maybe go a totally different direction? Let's go. On a totally different note, I was playing with, well, I actually have that other one that starts it. I think it's, so I have this, just curvature a little bit. So I was trying to understand this curvature and parallel transport and geodesic curves and all those wonderful things. So what you end up with is with a lot of curvature. When you leave, so this is all starting directly at this North Pole up at the top, and it's taking a certain amount of step. Center that. And it's taking a certain size step as it goes. And at this size, there's basically zero curvature. So it ends up coming, you take 4 right corners and you get back to your start. As you increase the curvature, then your path that you get back to is less and less lined as you go. If you take one step and turn a little bit, that's more what this other circular line represents. And you still end up slightly turned from where you started out. Started out. As you increase the curvature further, so now we're actually getting out to walking around the equator a little bit. then we only need 3 right degree turns to get back to the pole. By that time, you're turned 90 degrees. That you left with going with your right side going this way and your forward this way, and now your right side is this way and your forward is going to the left and right. I don't think you can see my mouse, but I'm pointing with. So, you can increase this curvature as much as you want, till you're walking from one pole to another. You only have to take 2 right degree turns to get back to your start. You can get really interesting harmonics as you get really, really tight curvatures, and your right turns happen in various positions around the globe. But all of this is predicting that you live on a sphere, and even if you add an elevation to that, so you get 3D space, you'd have to eventually consider that this 3D space that we're living in really doesn't have any curve to it, other than the ground. If you look at the ground, there's a curvature. I was referring more to in this local space around us is basically flat. From here to the sun, there's no arc around some external curve. So I really began to wonder what curvature is, how curvature would apply in space, that it would even deflect light and make these interesting Einstein lenses. So I looked at what a section of flat space would sort of look like. And if I just open a hole in it, then the space as a whole stretches outward for a certain amount of displacement in a space. The space around it is stretched. And then light, that's this light emitter that I'm kind of dragging around, emits these photons. They're red shifted or blue shifted depending on the stretch of the space that they go through. And the space that's tangent to the curve, that doesn't actually like head directly towards the body, is also stretched. So as you add more and more of these,
now, Jim, if it's okay, is there a URL that you have to your main website that lists all of these different? I had somebody in chat and I said I would ask for a URL and some links.
This is all a GitHub project. It's all open source. I will drop the link to the root of the project, which itself is a read.
Awesome. Yeah, and that's perfect.
To lots of other resources.
And I'll put that, if it's okay, I'll put that in the meeting notes as well.
Yeah, absolutely. So this is the main page of the repository. There's lots of markdown on GitHub that gives me nicely formatted text that I can drop images in and kind of explain some of this stuff. And a lot of this is written down. I should actually maybe, thanks for the diversion actually. The space displacement stuff is still very much work in progress. But there was this document that I started, which is this first principles that really, if I was to go back and accept that, rotation isn't just a property of linear space that's represented by quotients in a matrix, that spin is itself a thing, then what sort of consequences does that have? And I found I had to go through and define all these terms and what related quantities would be, because you have position and velocity and acceleration, and you have orientation and rotation and angular acceleration. And these are all mutually independent things. They're not really they're really two different coordinate systems entirely. But then if you go back to E equals mc squared, actually before that you have frequency and wavelength. You have wavelength is a speed, and you have frequency that's a spin. So you're limited very much by the amount of spin you have versus the speed you have. If you're going the speed of light, you don't have any spin, and all your clocks that depend on spin don't tick. At the speed of light, you don't sense any time. At normal, ground rate, we, have lots of time. Most of our time is in spin with very little linear motion to it. But then, like in a gravity field, the this is really slow to draw. It's a lot of calculations. Deeper in a gravity field, space is stretched more because there's more stuff displacing it. So your space that you have to go through is longer, and it takes longer for your ticks to go through it. So in that sense, your clocks are slower in a gravity field because they have more space to go through. Similarly, when you're going very fast, I suppose when you're going through a lot of space, your ticks don't have as much time to go through them. This was kind of trying to show the effect of cumulative bodies. As a photon is only passing through one body or two bodies or three bodies, etc., the space it has to go through is stretched longer and longer and longer. This is a very constant stretch, and one might call this Hubble's constant. But it's because space is expanded and not expanding that it's redshifted. I would love to take questions. I would love to have interaction with other people because I don't know where to go. It goes back to Bell's experiment. There's a simple pendulum that can disprove whether classical mechanics of a harmonic oscillator to balance model a balance beam or a simple ratio of objects on the beam is the right answer. If the objects are the right answer, then that means there's some things that I know would work. There's this guy in France named Aldo Costa. He built a huge Ferris wheel. And it looks something like this. It's not that. It's one of those machines that doesn't work. It's this huge Ferris wheel. It's got bottles that stick out on one side and not on the other side. It's quite obvious from its initial position that one side is definitely heavier than the other. Now the problem is do you get enough work out of the heavy side to be able to push one bottle up at the top and one bottle up at the bottom? Can you use all those bottles to move two? And it's tipping the balance. It's at the fulcrum of the balance, you get more angle out of that than you should by quantum mechanics, by classical mechanics and everything that's based on it since. I did find a couple of other examples. This seems to be an example of Aldo Costa's wheel, that it has a thing that flips weights at the top, but all the weights on the right are definitely heavier than the left. Now the problem with this wheel is he never actually lets it spin. You can't prove that it would just keep going, other than if it can flip one weight, why wouldn't it continue to just flip the rest of the weights? on this left side, they're all hanging by the rim. So the radius that they're on is inside the radius that the weights end up on the outside. There's one other example. And I know there's that channel called VE Project that shows all these wonderful perpetual motion machines that are supposed to work and don't. And there really is a difference between those and this particular one and these. This is not the right one. This more has weights that flop out on this right side and fold against the wheel on the left side. I assume there's actually something around this area that's pushing them off of balance. That normally they would be like have a pivot where the weight is over it and you just have to knock it a little bit to knock this weight out to its extent. That right at that balance point, this motion would give you momentum that the next carry past gravity plus that momentum would knock it further. But then if you can make it to not the top of the wheel, so it's not exactly top to center and you only have one option, it should be right at the balance of where the wheel is that you have to knock it out. If you can advance that towards the top, you should be able to get more effective work out of it. But you can't draw all the load off of it. Obviously, the unbalance would eventually balance out and you'd be back to just a stuck wheel. And that's how I got from playing with spin vectors to quantum mechanics and polarizers and magnets to Bell's inequality, them saying that local hidden variables can't work and I can make a simulation that works quite well. There's a CSSH game that has interesting rules to it. I don't. No, the link is here. There's a CSSH inequality that is best described as a game that you have two boxes. And between the boxes, you have an entangled communication path that they both receive the same sequence of randomness. Person A has two switches on their box that lets them select position 0 or position 1. Person B has the same switches that they can switch 0 or 1. The settings that they are selecting are not the same. They don't, like, what A is selecting for A0 is not what B is selecting at all. The game is basically that for A0, if A selects A0, then they know if B selected B0, that there's a correlation, that there's an equality between them. If A selects A1 and B selects B0, then there's a correlation there too. So on the one side of A, if he selects either switch, if B selects 0, then A knows what his result is. But if B selects his other option, A0 will know information about this, but A1 doesn't know any information about it. So these two never match. Although in the four-way equality, you have a cross and a cross and a cross. And by transitive property, they should all equal each other. You should know all the information about all the states, but you don't. Because what it's actually modeling is polarizers at various tilts. If you have one polarizer, well, see, independent observations, you can't stack the polarizers. It's not really the same. You would use something more like Stern-Gerlach that would give you both up and down without up and nothing. Polarizer event experiments have a lot of issues in that First, polarizers aren't perfect and they block like 97% of the light. But then there is that peak right at the curve, right at the top of zero, where stuff is just lost right away anyways. But anyways, with polarizers, you lose events from just being blocked by the polarizer. And they're only like 97 to 93% transmissive. And then on the other side, you have a photomultiplier that's supposed to detect these rare circumstances. But every once in a while, it'll just fire randomly and detect an event just because a stray cosmic beam, penetrates through and happens to hit it. So between false detections on one side, lost events on the other side, you have a lot of uncertainty in what your actual counts could have been, even in that quantum, even if you can have great counters. The percentage difference is within experimental error. It might as well just be cosine. I could multiply my ratio of weights by cosine and get exactly the quantum result. But I don't think that's reality, because the previous talk was just talking about this extraction of momentum from the unbalance. And there's something even in the vacuum in the quantum states that just off the tilt of the scale, there's more work there than should be accounted for. That's my observation. I don't know, how much more time do I have to kill? Can I have some questions, maybe?
Yeah, we can do that. So let's do this. So what I want to do is, let me see. I'm going to remove the spotlight there from. Actually, you know what? I'm going to remove the spotlight there, and I will remove this spotlight. Okay, and then we can go to Q&A. So let me put it on gallery view. Again, we're running a little bit ahead on schedule today. That is totally cool. So everyone, please give Jim Buckeyne an enormous hand, sir. Thank you. Thank you for presenting that. So I guess I could go first. In terms of our Q&A session, I would like to start by saying what I kind of picked up. I'm not an in-depth math person. It's been many years. What I kind of picked up, though, was it looks like you're refining a lot of physics equations, right? Like, so using vector rotations instead of using quaternions. The way that I always kind of visualize it is physicists and mathematicians, they put those together by hand, right? And when we put those into a computer system, maybe it gives us some shortcuts to understand things differently and to refine things. Now, an example, and this is a bad example, but I was reading last week about RISC versus CISC processing, right? And so the idea was there was a project back in '82 where they looked at computer instruction sets, and they said, hey, we've got these really great CISC processing systems, right? Like the x86 is one of them. And they said that the problem is the vast majority of these instructions, and hence the transistors that are used for them, never get used. So RISC was this idea about let's take this thing down to only stuff that gets used, and then we can do some other tricks to reuse them more effectively as well, right? It almost seems like some of what you're talking about is similar to that from a physics perspective. Do you think that would hold as a comparison? Yeah, you know what? You are muted, sir.
I'm muted.
There we go. Okay.
Yes. In the case of the spin vectors, certainly, it's keeping clarity on what the values of those values are, what the magnitudes of those are. Another example, so you have this Stern-Gerlach experiment that can measure left and right. If you chain them together, you can flip the results so that they match the other side. But when you do that, the electrons are no longer correlated. They have a different phase. So rotating 360 degrees isn't exactly the the same, and you have to rotate an electron 728 degrees in order to get back to its normal state. And that's not clear in any of the math that you would learn through high school. And it's not. So in physics simulations, bodies are represented basically by two things: its position and its orientation. And it's basically 6 coordinates already. That it's not just a position and a transformation of that position.
Yeah. No, that makes sense.
Yeah, it's sort of boiling it down. It's actually complicating it. I mean, on paper, this doesn't make it any easier to compute. But in a computer, I can just throw all the numbers I want at it and just spits out the results. And a complex system works.
Well, and that's one of the things that intrigues me. And it looks like some of the stuff that you're using JavaScripts, but it looks like these are almost like game engines, right? So they're game engines computing physics. But that's almost perfect, because game engines have gotten so complex because they're trying to represent those physics as well as they can, that those are probably some of the best physics modeling tools you could find.
Yeah. For sure.
Okay. Yeah. No, that's interesting.
Other than they don't handle electromagnetic, electrostatic, gravity.
Yeah. Well, and this is definitely an aside. I won't hog any more of the Q&A after this, but I did read, what was it? This was someone was saying that the double slit experiment and quantum mechanics, where basically you don't have results until the wave function collapses. They were saying that is similar to a game engine, and they said maybe that's an indicator that we're living in a simulation, right? Because you don't process stuff that isn't in the visual frame usually, right? So
yeah, to an extent.
Yeah, I mean, to an extent, yes. But
I don't know, that an electron has a fixed tick rate is more compelling to me, that we're in a simulation, because it has a 1/2 spin, it doesn't go below that.
Well, that's, see, there's another point there.
So that goes to actually quantum stuff. My talk was titled Quantized Weights. So I started with the balance beam, and that really what I'm measuring is the quantity of weight. And when you're playing with a balance beam, to have a balance, you have to have two of the thing, period. You have to have one on the left and one on the right. Even if you have nothings, you just have two nothings. But there's always a quantity of two. And if you take one away from the scale, that's taking a whole one. No matter how small that one is, there's a distinct change to it. And there was this graph on my page.
And if you want, let me see. Let me spotlight that.
It's quantized. I think.
Now, Jim, you also showed us a couple of your videos, but when I visited your channel, it looks like you have dozens.
None of those videos I showed were mine. Those were drawn from other places.
Ah, okay.
The wrong section as well. Or not. Honestly, I don't know where it is. I have this graph. I have a lot of Desmos scripted graphs. If I drag this back to this window, do you get to see it? Yes. So this is basically a balance beam and the ratio of, if you have weight, ratio from 1 to 2 and from 1 to 0, you get this curve that's almost cosine like. The derivative of that is the bottom, and I didn't actually do that myself. I plugged it into Wolfram Alpha and it had it give me the equation. But it gave me this neat equation that told me that at the balance point, if I remove one thing, the slope of that is 2, not 1. If you have a cosine graph, the maximum slope you can have on that is 1. At the ends of infinity there, at the at 2 basically, if you add one weight to no weight, your change is 1/2 and not 0. If I plug in a cosine graph here real quick. Okay. I'm still have to go further. Somehow not right. It's my squared. That's true.
So would you say that you subscribe to the simulation theory then, or?
I could.
Very non-committal. I don't want to pressure you on that one, sir. I don't want to pressure you. I was just curious.
No, mostly I think it's not a simulation, but it could be. I mean, it's not a lot of reason it isn't. Anyways, this cosine graph and that curve end up looking exactly alike. If you were to, use one or the other, it's probably not even going to matter in 99% of your circumstances. But the slope at the infinity of adding one weight for this graph is 0, whereas for this one it's 1/2. So you have, if you can tip the balance, it's maybe different than you expect. That's all I got to say about that one. I like that derivative of 2.
Wonderful. So let me go to Bill Alec, and actually let me remove the spotlight there, and we'll put it back on normal mode.
Yes.
Bill, go for it, sir.
Yeah, hi, Jim.
Hello.
I'm doing a lot of work with.
I can hear you. I'll be right back. Keep going. Come on.
Oh, okay. Yeah, I'm doing a lot of work with, these sine wave functions, but it's not classical mechanics at all. It's scalar mechanics.
Mm-hmm.
Okay. And to get that, I do a lot of work with that function you were just showing there, and it's the sine squared term.
Mm-hmm.
Okay. I'm doing a lot of work. I can replicate that very easily with my technology. And to do that, you basically do, this Q cross Q. Okay, two charges with the cross product. And the idea is that you pump these two wave functions. And when you pump the two wave functions, you get the sine squared term. Now, what's interesting about that sine squared term is that that's what Tom Bearden called the scalar wave. Okay, scalar wave functions. And that's that AC wave. Okay, classical mechanics is up here. Virtually almost all of physics does this.
Sure.
But when you want to work with gravity, you have to work with this. And Tom Bearden called the scalar functions gravity waves, okay? Because it has this DC offset built into this. So the idea is that Tom always said that fundamental particles, like electrons, protons, neutrons, they're trapped electromagnetic waves. And it's creating a wave function that's trapped, but they're multiple wave functions, okay, in a resonance mode. And so that when you resonate those two waves, the Q cross Q, you get a scalar function, okay, and that's what creates mass. And so when you look at this equation, E equals mc squared, that c squared term's always bugged me. It's like, why is it c squared? Shouldn't it be c cross c? Okay, the cross product of two wave functions, okay, is what creates mass. Okay,
Right.
and like electrons and protons. So you have these wave functions that are pumping together, creating a scalar function, which is your mass. Okay, and you can either do, if you take energy out of that system, you can create an anti-gravitational effect. If you put energy into it, you create a gravitational effect. Okay, and so I think you're going in the right direction here, but it seems like the focus maybe should be on the sine squared functions, okay, of these colliding, pumping wave action.
Okay.
Okay, if we work with propulsion type systems, that may be the direction to go in. And that's what Tom Bearden suggested.
Okay.
In that direction.
I understand that. Sine squared and sine really aren't all that different, other than one's always above the axis and twice the frequency of the other. The slopes are the same. It still can't go more than a slope of plus or minus 1. This ratio can be cycled the same way. I don't know if you can see my other screen there, the Jim B screen. You can also take that same function and square it, and it becomes more like the sine wave. Like if you take sine and square it, the same oscillating wave squared behaves like sine squared. But it's not sine squared. It's very close to sine squared. I mean, it's not sine. It's just very close to sine.
Yeah. Well, let me do this, if it's okay, Bill. Do you think I go to our next question now?
Yeah.
Okay. Robert has had his hand up for a while, and we have another Harold in chat. So let me go to Robert first, then. Yeah. And I hope I'm not cutting you off. Let me apologize. Yeah, go for it, Robert.
Jay, is that Jim as well?
Yes.
Jim, I'm just curious how your 3D rotation theories, mathematics specifically, how it differs from matrices, because I've been used to rotation about a z-axis and a matrix rotation format for cosines and sines.
Yeah. What I found was there's this small blurb on a Wikipedia page about quaternions that
I never heard that term before.
which one? Rotation vector?
No, quaternions.
Quaternions? Yeah, that's Hamilton's thing.
Okay. All right. Is this a step above a matrix format? Sort of?
No,
Or just an extension of it?
it's actually kind of a step below.
Step below.
Gorda. There's composition. So there was this Rodriguez guy in 1840 that did this math for what did I call it? Composition? Rotations and spatial rotation. That was the article. And
Jim, I can put that back up. Let me spotlight that again.
I was fine. Don't. I was just going to share the link in the chat, but.
Oh, okay.
It's this link. So in 1840, there was this guy, Rodriguez, Benjamin Oliver Rodriguez, that wrote this paper about doing rotations differently and basically off of axis and angle. With his formula there, you can give it an axis and an angle and get back an axis and an angle without keeping it in the quaternion form. It is kind of a partial conversion into a matrix, but it's not fully converting into a matrix. When you go to a matrix, you lose 1/2 of the projections. You can't get back to what the information was about, what the actual spin axis was.
So this is a true 3D. It includes all information that a matrix wouldn't, typical matrix.
Well, about the rotation.
Yes.
Yeah.
Because I'm used to these formats, finding a moment about Z as a function of theta. And it gives a 3x3 matrix, and then it transfers into a matrix, cosine and sines, and the rest zeros and ones.
Yes, I started there back in the 90s when I was learning to program and writing my own 3D engines.
And then this new format looks like, Jim, the other Jim's gave me a link.
That's me too.
And that's the mathematics that's being used.
Yeah, they're both Robert. They're both the same. He has 2 computers, and that was why I was having some trouble.
Okay.
Yeah, that got me
guys.
too.
This is Jim Buckeyne.
Buckeyne.
Okay.
Buckeyne.
Okay. All right. You're not Mr. Decker then.
I am. But
you're both names.
Decker's my internet pseudonym because I'm unique otherwise.
No, I mean your name that you were born with.
Yeah, my name is James Buckeyne.
Yeah, but then he has it's this like hacker name.
Yeah.
Okay. All right. So if I just review this information here, my question will be answered, most likely.
Yeah. See, I don't qualify for a hacker name, but that's because I realized long ago I couldn't hack my way out of a cardboard box if my life depended on it. So my hacker name is Tim. That's
the inventor.
So Jim, if I this link I got, it talks about quaternions and spatial rotation. So if you apply these mathematics by simulating rotation, you're saying you won't lose any information as you would if you applied typical matrix mathematics?
Yes, absolutely.
So you do lose some information if you apply.
Yes, the matrix.
Why is that? Is it because they can only do one frame at a time, or?
That's part of it. This is more analog. I can scale by any time also. But that's not the whole of it. It's because the 3 axes are broken down into their 3 angles, and then you take the sine and cosine of those. Now those sine and cosine don't really resemble those original angles. And then you take those sines and cosines of x, y, and yz, multiply them together, and yz and x, and all these various combinations. I don't really know where the information goes. It just, there's a sign, there's like you get a minus 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 in the multiplication, and that becomes a minus, but you lose that there was two minuses in the first place.
You what?
You lose that there was two minuses that went into that term, or three really.
Oh, you lose the signs.
Yeah,
The
so
previous signs, and so it's incorporated the final answer.
Yeah.
Robert,
So you lose the history.
Yeah.
what interests me about what Jim is doing, Jim, I think what you're doing is incredibly important. I'm not sure if most people grasp the importance, but basically from a computer science perspective, you're doing meta-analysis on physics. And in kind of a different sort of way, David Chester, who has been here many times, he does something similar where he's doing basically cross comparison of theories. You're doing a meta-analysis of the physics and the math. And I think that's also incredibly important, right? Because this is something, again, traditional physics, they do this by hand on paper, and there's nothing particularly wrong with that. But you're coming and saying, okay, if we apply these tools and we apply logic and rigor to this, then, you know, what can we find? And like streamlining is one big part of it. You'd mentioned values that are being basically data that is being lost, you know, and see, and from a formal mathematics perspective, they might not even notice that. They say, well, you've got two minus signs, of course those cancel out. From a data perspective, you're saying data is being lost, you know. So the meta-analysis, I think, is incredibly important, and that's one of the reasons I'm so happy that you were able to join us today.
Along that same lines, I looked into Wolfram's stuff. I followed him for a little while, and Wolfram's math graph ideas actually really good. And if they could plug it into a computer, they might get something. But the problem is they're going to give it the same tools that they're using with these matrices and quaternions and stuff, and they're not. It's still going to be limited to what it has for information. It can't necessarily extrapolate. Oh, you need to just forget all that and do something totally new.
Yeah, and with
Wolfram, you're referring to Mathematica?
Well, Wolfram Wolfram wrote a book called A New Kind of Science, and
Yes.
and in that book, my takeaway was there were a couple takeaways. One of them was he was getting into fractals, right? He was getting into these fractal processes. The other thing, and I've tried to apply this in life, which is probably stupid, but what he was saying was, he was saying there are some problems that are too complex to solve multiple steps out. So you solve it one step out, wait until you get to the next step, and then solve the next one. And actually, I was thinking about that the other day. I'm like, you know what? I'm messing myself up in my brain. I'm trying to solve this, you know, contingencies, or what happens if I do this 5 steps out. I'm like, I'll just do what's next, and when I get there, I'll do what's next after that.
I wonder how it could be applied to mechanical engineering, because in a theoretical standpoint, we've learned about transformation of vectors, and that an example is rotation is an example of that, I believe, unless I'm wrong. I just have my notes open up to me, and I'm trying to remember what I've learned. And when you mentioned about rotation, that interested me, when there was another way of expressing rotation other than the straight matrix format manipulation type. So what you gave over the link about quaternions, would that answer my question, you think?
That is the math. It's all there. Whether you can grok it or not, I don't know.
You mean whether I could use it or not? You don't know.
Sure.
Yeah, and Robert, that's going to be on the website too. I put a link at the bottom on the event page.
I have it. Yes, thank you very much, Jim.
And
Tim, sorry, I'm getting the names
Okay.
confused. Thank you, Jim.
There's a discussion page on the GitHub repository. Feel free to drop a comment there.
If you can get the link for that for me, that'd be great too, Tim.
Oh yeah. You know what? Yeah. So the link should be there through the GitHub page. He took you to the root of that page, and so the entire project is there, including all of the demos. And those are pretty in depth. I've written a little bit of JavaScript. What he's written is that's heavy duty stuff. So.
Oh, the GitHub.com.
Yeah. And GitHub is
Okay.
a software repository for storing files.
All right.
Let me go to Harold next.
Okay.
Sir?
Thank you.
Oh, great presentation, Jim. You know, that's fantastic. My question to you is this: I noticed you have done a lot of work with sine and the cosine function and how it applies to the field. Very abstract work. Looks like it has a lot of practical application. So my question to you is this: from what the work I have done is the cosine function normally applied to the amount of the electromagnetic field, and the sine function would be the magnitude of the interaction between the amount of magnetic field or matter interacting with something else, let's say another field like gravity or another electromagnetic field. So have you done any predictions, any quantifiable prediction about how those interactions will produce, for example, in terms of cosine, the amount of magnetic field or the amount of matter interacting with another field? How would they, what quantifiable prediction have you made in that area?
I haven't made it to electromagnetics and electrostatics to get back to the future from my prehistoric Stone Age assumption about balances. Mm-hmm. I'm getting there, but I don't exactly have the association. I know that the math is probably similar, that for a balance you have a thing of A's and a thing of B's, and the difference of those divided by the larger of those is a different function. It's then sine or cosine. It's only within a certain range. It doesn't like extend into infinity either. So you have to kind of do like mod 2 and keep, in order to get it to loop. But I don't have anything specific about electromagnetic balances yet.
But you did it with the photon. You were explaining earlier, you were looking how the cosine and you were changing in one of your early
yes.
And that's the part that I'm interested in, that because you were speaking about the cosine, how it was interacting in the photon, in the filter, the photonic aspect. So it is interacting with another field. So the sine would be the magnitude of the other field, because you have two fields interacting. Cosine, the magnitude, the amount of magnetic field, or let's say electromagnetic field interacting in terms of quantized weight, what would be the quantum function applicable to that? And it looked like you implied, that you're close to it, because that's what I saw earlier. You are kind of around that area. I mean, it's obvious. It was obvious from what you were showing earlier. So my question is, have you gone, or are you planning to go in that territory in which you would be making a quantifiable prediction using several equations, what would produce, so that it would be testable predictions to the physicists?
Other than the balance beam prediction, no, I haven't made it to something electromechanical.
So when will you be going into that area? Because it looked like you already got into it earlier.
Every day I'm thinking about
presentation.
Harold's putting his toolkit together. He's like, what can I build here?
This is
all right. Hey, thank you. That was great.
And thank you too, Harold. Yeah, and I'm sorry, I didn't mean to interrupt, but yeah. Well, so again, if anyone else, let me lower Harold's hand here, and then if anyone else has questions, those are Option Y on Mac or Alt Y on Windows. Okay, and all is quiet in the conference. I think people are just kind of trying to go through this in their head. You have so much stuff that you presented on, Jim. And I can't thank you enough. It is so wonderful to have you present on this. And I meant everything in what I said about meta-analysis. I think that it is incredibly important to basically reviewing all of the physics and science that came before, right? And looking for errors, looking for incontinuities and stuff like that. Okay, so why don't we do this then? I think we are all set there for the time being. So I'm going to put this thing back on gallery view. Everyone, please put your hands together and give a giant applause for Mr. Jim Buckeyne. And again, we're running ahead of schedule. So what I was wondering though, let me see. Believe it or not, and Jim he's posting some links in the chat there. Where is he at? Michael Boyd had some UAP videos that he wanted to show. I mean, he was asking if we had available time. And I said, well, our schedule is all booked up. Now we have available time. Michael, are you with us?
Yeah, but I'm not decent yet. So if I could have like 10 minutes, I could probably show you guys some of those videos I was talking about.
Yeah. If you want to run through those. Okay. Well, we've got about,
Yeah,
take about 10 minutes then.
I got to get dressed, so I just got back from doing a bunch of chores for my wife. So give me 5.
Oh, okay. Good deal. Okay. Well, so yeah, I guess we've got about 5 minutes while he puts stuff together. If you guys want, I can kind of show you what I've been up to lately. I'll do my shameless self-promotion, or Jeremy Reese could walk us through some of his latest stuff as well.
Excuse me, Tim?
Yeah.
I sent you a chat message. I sent you a message through your website. I just want to make sure you got them.
Oh, yeah.
If you want to talk about it. It's still up in the air, but I like to talk about details.
Yeah, you were talking about the spark reactor in Massachusetts, right?
Yes.
Yeah. No, thank you. I've read a little bit about that. That's, yeah.
Okay.
I've kind of scheduled myself solid, so.
All right, fine.
Yeah, so we've got that. Yeah, if you guys want, here, I'll tell you what, I can show you. I'll just do that. Shameless self-promotion 101. Okay, yeah, if you guys can see this. So thank you to everybody who's helped me get up to 837 subscribers now, which is actually not very much at all. But, you know, there are a lot of different reasons that I like doing these interviews. The one-on-one, I have folks that I invite to the conference who don't feel comfortable speaking in a group. Some people just can't bring themselves to do it. And so one of them is that. And then the other part is folks that just don't fit in the APEC conference, right? I cover a lot of different topics. So I can drop a link in here. This is just my interviews channel. Thank you to everybody who is, I think most of our list is on my mailing list for this. A lot of these are old audio interviews. And some of them not that old, right? Like I did these during the pandemic. I was still doing audio, and at one point we all just kind of switched to Zoom, but these were before that. So I've been busting these out left and right. You know, I mean, this top row here is all in the last couple of weeks. I did one with Ryan Graves, and I'll pause that so there's no volume. With Ryan, that's at 31,000 views. So people really like that one. He drilled down into the UAP phenomena. I asked Ryan if he wants to present at APEC. He said he's open to it. It's just a scheduling thing. So I'm going to try and get him here. And that's right. I did play this one here for you guys. So that's kind of what I have been up to. And then let me see if I can scroll down. And, oh, I don't know what those are. My daughter has been using my account, apparently. The other one that I want to show you guys is Jeremy Reese, alien scientist. Let me see if I can find his channel. I can find him, not his channel. Well, Jeremy's with us here. Let me stop sharing. Hey, Jeremy, do you want to show us your channel real quick? If he's paying attention, it looks like he's stepped away from his machine. Oh, Robert, looks like your hand is up. Is there something I can help you with, sir? Oh, you're muted.
I forgot to put it down. Sorry.
Oh, okay. No
There.
worries.
Sorry about that.
Yeah,
Hey,
so
Tim.
think.
Tim, while we're waiting for either Jeremy or for Michael, do you got any upcoming interviews that you'd like to give us a little preview snippet? Because you've been busting them out, so I'm hoping you're gonna.
Yeah,
you're
no,
all hooked up for some
I've
good
been
stuff.
super busy. I can let me see. I don't think I have anything I can show you, but let me go into my little spreadsheet. I'm starting to run into the issue there. So I have a couple that I need to work on actually. You know what? Here, let me. Yeah, I'll do a share screen on this.
Okay, I'm ready whenever you guys are too.
Oh, okay. Well, you know what? Let me come back to that later, Jared. Yeah, I do have a couple. I can put links into stories. I actually want to reach out to. There's some quantum computing and photonic chips. That's and I saw those and I was like, wow, that's interesting. And then there was the guy, and it's on my channel. There's the guy who was pouring molten copper in his arm. And again, when I saw that one, I was just like, I'm in. So. But yeah, I'm also really interested in some of the stuff that's going on with computing. Computing is, I think there's transformational stuff happening right now in computing. So, well, so Michael, take it away, sir.
Okay, let me share. Let's see here. Okay, this is called Apache. What we're looking at here is there's these 3 UAPs that they viewed, and so what I noticed is up in the right up here, there's a vortex. So that made me suspect that the 3 little objects are over here in that area circled. You can barely see them there, and I'll focus on those so you can see. But I'm just showing you this is what I saw.
Now right now it's just showing the files. We're not seeing video yet, Michael.
Oh, okay. Let's
now
see.
Also, if it's okay, I don't know anything about these. Could you give us a little backstory? You said these were just released by the government.
Yeah, there's 4 videos, and the reason that I'm paying attention to them is that because they're in infrared. Okay, now you're just seeing my file right now, right?
Yeah.
Okay, let me see. Why isn't opening up the? Let me pause it.
You may have just shared the file manager. I think that's the problem. And that way, when the video pops open, it won't share that screen.
Okay, so how do I get out of that?
Try stopping your screen share. Try stopping it entirely.
Yeah, I can see that. Unfortunately, control.
Oh, you know what? I can stop it for you from here. That's fine. Let me do that. Stop sharing. Okay. Yeah, and then give it a try. And you could try sharing your entire desktop and then just playing the video maximized. That's the safest bet.
I got to get back to Zoom here. Okay. Now go share screen and then go to my desktop. Is that what you said?
Yeah.
Just, okay. Let's see here. Huh. I don't see a selection for the desktop.
Usually it's the top left.
Top left? Okay, that says
Yeah, there should be
speed.
desktop 1. Hopefully.
No, let's see here.
There.
Now,
Okay, yeah.
see
There you go.
Files again.
Yeah, I see the files, but I also see your taskbar. So
Can you see it? Can you see the video now?
perfect. Perfect.
You do see the video.
Yeah, yeah.
Okay, cool. So now what's going on here is this is Apache video, and it's in infrared, and basically what I noticed is on the right above the 3 UAPs, which are in the little circle here, there's right in that vicinity, there's 3 UAPs. And I noticed up here on the right is like a vortex, a spinning vortex that you can see there in the infrared. So I drilled down on that. Now, how do I get out of this? Let's see here. Okay, I'm going to show a close-up now. And this is what we see close up of the 3 images. And then basically what's going on is they're not, they're basically what the little dots are is they're like little plasma vortexes. And that's why they're not really stable. Let's see here if I got a different one where you can see. Let's see here. Let's try this one. I don't know what's going on. It's taking a while. I think that might be the same one again. Let's see. I thought I had some other ones. So let's see here. So basically, what I should do, let me go look for, unfortunately, I'm doing this on the fly, so it's kind of like I'm not prepared. I'm seeing if I can find the actual original videos to show you. So there's another video where it shows, it's called Rubber Duck. And I'll see if I can show you that. So now we have these 3 little cows over here. And then the rubber duck's going to show up down here at the bottom. And what's cool about it is the rubber duck is cold compared to the background. So that's one of the videos that I'm going to talk about when I have a together presentation, that is. And they have one called A10 Warthog. Let's see here. Find that one. Oh. Okay, this is back to the Apache one. Now here's the three little vortice circles that were blowing up when we see those, the bigger view of them close up. This is what they look like in the distance. You can see that they're basically these. It looks like they're running into each other, but they're not. They're actually it appears to be some kind of atmospheric phenomena, is what we concluded in our analysis. Let's see here if I can find. Then there's another one where it's warm. It's A10 Warthog, and here's what the UAP looks like in that. It's just a little shorty. And then I have a closer up view of what it's looking like. Which is, again, I think this is some kind of atmospheric phenomena that's going on. And let's see. If I missed one. I've covered all of them, but here's the A10 one again. See if this works. Oh, maybe it's just the image. It must just be an image, sorry. Let's see here. That's the phenomenon again. And then you see over here the display, it says WH for white hot. And so here's our UAP. It's in the white hot. So it's warm. And let's see here if I got. I'm just like randomly picking some videos to show you guys. Oh, that one didn't want to go, so I'll wait. I guess not. Let's try another one. Okay, there's the A10. You can see the A10 there on the left. So we had to stabilize it to get it to work right. So that's what you're seeing there. Let's do it again. So you see you have the A10 on the left, and then there's the UAP next to it, swimming around. or from the A10. That's the other UAP. This is it's called a La Bruja. It's also been called the Witch. And you'll see what the reason I did this is is that in the black there is some cattle. Some of them are sitting on the ground, and then to the left up there in the image, the white spot, that's the La Bruja UAP. And again, if you look down here on the far bottom left, it says BH for black hot. So the cattle are hot, but the UAP is cold. So here we go. I'll run it again. So notice how fast that cow's walking compared to the UAP. So that UAP isn't going that fast. If you think about it, if you can see the cattle walking in comparison, my conclusion was this thing ain't that fast. Because cattle don't go like 100 miles an hour or something when they're walking. So that's just, let me stop share now. Okay, so that's just kind of some examples of the data from the 4 UAPs that the government released. The ones I have are, I have the originals, and they're on one of them is an hour and a half long, and it's only about 30 seconds of that hour and a half where you actually see anything. The other ones are shorter, and what I'll try to do is figure out a way to show the short ones in their entirety, and then just the section for the one that's an hour and a half. But I'm going to have to do a little editing on my end first. So, but that's an example of the data. Okay.
Awesome. Thank you, Michael. Thank you. And let me see, David was posting in chat. He said it looks like the UAP generates wake. I'm not sure which one he was talking about, though. You know, I did look up, and I just closed the window. There we go. Apache UAP. So this is written in, this is IFL Science. They were saying this was filmed at midnight on November 6, 2018, around 40 miles northwest of the Arizona city of Tucson during a training flight. And it was captured through specialized military night vision goggles. 3 small dots can be seen moving quickly through the air in an unusual and erratic fashion. So that was what the video was. Arizona, or I'm sorry, Mick West, an administrator at Metabunk, said he thinks that it's birds or potentially bats. So
yeah, well, the birds were doing probably Mach 10.
They're really fast birds.
You saw the little loops, the thing doing the little loop-de-loops, right? That I showed you the close-up. Yeah, I don't think those were any birds I've ever seen. I actually suspect it's so what my research found was, in my previous presentation, I talked about this pre-signal that precedes coronal mass ejection. I don't know if you guys remember that, but essentially what happens is when there's a solar flare, it takes 7 minutes to reach the Earth. But if there's a coronal mass ejection associated with that, part of the corona of the sun is thrown into space at hypersonic speeds, and it takes 3 days for that gravitational wave of protons, accelerated protons, to reach the Earth. Well, it turns out that around 2016, they noticed that about a day and a half before, or a day before the solar flare, on the opposite side of the Earth from the sun, the dark side of the Earth, they observed a decrease in the decay rate in radioisotopes. So certain radioactive materials, the decay rate slowed. And so, and essentially when I was doing my experiments with Revita magnetism, and I was chatting with Hal, I found some examples where the gravitational induction signal preceded the electromagnetic signal from the defect's edge. So there was essentially there's a pre-signal, something that happens a day before. So what I did is I went on the space weather station and looked at what was going on around that date, the 2018, or I don't remember the exact date off the top of my head, but it's on the display. And what I found was the next day, there was a huge coronal mass ejection in that big chunk of the southern hemisphere of the sun was thrown out into space. So what I suspected is that there was those were plasma vortices that were produced by atmospheric anomalies occurring on the opposite side of this, on the dark side of the Earth from the sun the day before, which is exactly where we were. As you describe, it was like 5 minutes till midnight is what the time showed. And you could see that basically it was right in the right time frame. So I like to look for natural explanation for things before we start talking about, is this an artificial phenomena that was created by other entities from us, put it that way, right? And what I suspected is it was natural, that it was a natural phenomena that was causing those three little dots, those little hot spots that showed up on the IR. And basically what it is when you have a vortex, at the vertex, the current increases. And so what happens when you increase the current, it's kind of like if you in construction, there's a requirement for how close you can put the wires together. So you can't put more than two sets of the wiring for your house. You can't put more than two of them next to each other for longer than 6 inches or something. So you have to separate them out, and you'll see up in the rafters there'll be little holes that separate the wire bundles. And if they get too close together, they heat up, and it reduces you have to derate the rating for the cable. Well, essentially that's what's happening with the plasma vortex. When it gets to the vortex, that's where the current increases and goes higher, and that causes it to heat up. So it shows up warm on the infrared. And so you see these three little dots moving around, but they're actually the vortexes of three little vortexes that are interacting with each other. And they're basically a plasma ball. Someone, kind of like ball lightning, but in the atmosphere. But they're not, you could see when I did the real close up that they go in and out of existence. They're not stable. So from the distance, they look like they're stable, but you have to really get close up to see that they're a natural phenomenon. I suspect that two of the other, the A10 one, where you had the single hot spot, what I suspect was going on there, again, I looked at the space weather report, and it said right at that time that there was a hole in Earth's magnetic field for about a 2-hour period that opened up. And if you remember in that one, you could see it looked like rain. It was raining in the background, and it was coming in and out. Well, that's because all the cosmic rays were coming in because there was no shielding. So there was no magnetic shielding protecting us from the incoming cosmic rays. And then the other The other one was the not the La Bruja, the rubber duck one. I also found, which was cold again, I found that was also associated with a coronal mass ejection. But the odd thing about that one is there were no sunspots at all on the sun. It was totally blank. And then the one with, I think it's La Bruja, the other cold one, I couldn't find any solar events. So that one remains a mystery to me. But the fact that it's cold on the IR, how do you explain cold? Is there anyone have any ideas why UAPs would be showing up as colder than the ambient background?
Yeah, I mean, I have several. I mean, the most obvious is they're absorbing energy from the surrounding environment, right?
Yeah.
I mean, so you could have, I mean, if we're just going down a list of reasons, right? Another one could be optical cloaking.
Or I was thinking maybe it's an anti-reflectance coating.
Yeah, could be
kind of like a Mylar balloon. Everybody always says, "Oh, it's a Mylar balloon." You know,
It could be temporal as well. They could be operating at a different rate, so the heat that they're giving off is not the same heat that we are observing.
well, like for example, if it was like a piece of ice or something that was cold, it wouldn't be stable. It would change over time, I would think.
Yeah. Now I should mention David Perez just joined us, and David, if you can hang on maybe just about 5-10 minutes, then I would love to be able to start your presentation a little early. And I should apologize again for the scheduling thing. Regulars here know that we rarely stick to our schedules, even though we plan them immaculately in advance. So
I see James has got his hand up.
Yeah, James, do you have a question for Michael?
Well, it was just saying about the cold.
Yeah.
I mean, I'm not a mathematician or a scientist. I'm actually an artist, so I'm good with pictures. But I remember I'm just interested in all this sort of stuff, and I remember watching a presentation where a guy was talking about passing an electric current, high voltage current, between two light-poled magnets, and the wire went really cold. So he got frostbite on his finger. He had to go to hospital.
Interesting.
Yeah, so and I could speak a little bit to that. In the mythology, I would call it the mythology of anti-gravity, right? Although that word has kind of fallen out of favor. But in the mythology of this community, one of the common characteristics of a lot of experiments, people report when things fly off, when they reduce weight, they lose weight, they run cold. Like the Searle effect generator is one example of that. Lifters run cold. Now there could be there could be many different reasons for that. For example, okay, in the case of lifters, it makes a lot of sense. They run cold because high voltage ions in the air penetrate boundary layers. So if you take like just as an example, your body, right? You have a boundary layer of warm air around your skin, and the hair on your arm, whether or not you have hair, but that helps to ensure that follows you when you move your arm through the air, right? So you're always surrounded by a little bit of air that's warmer than the rest, you know, that unless you're in like a hurricane that blows that boundary layer away. But so ions will penetrate that, and they're fast moving and they pick up energy from around them. So, you know, there are lots of different reasons that in the case of a lifter, where you've got high voltage currents, they run cold, and that's something I've seen and documented many times.
The gimbal video be an example of that? You know, it's hot on the IR, but then there's a cold region, what Mick West called glare.
Could be.
But but it didn't make sense to me, because if it was glare, why would it show up as cold? So I think that you might be on the right track, that there's some kind of ionization process going on that absorbs energy at a constant rate.
Yeah, and it penetrates the boundary layer too. And that's something, and the boundary layer part was, and in fact, you guys, I don't know if you remember this, it wasn't a giant rumor, but there had been numerous people, I think Paul LaViolette was one of them, who had said the B-2 bomber uses anti-gravity, and they said, well, why is that? Well, because the B-2 uses high voltage, and they said, here are the high voltage strips along the leading edge of the wings. Okay, and I looked at that and said, well, maybe it's not an anti-gravity thing. Maybe they're trying to manipulate the boundary layer. The reason that you would want to do that is, in the case of the B-2 bomber, even if the skin of the craft is radar invisible, if it's pushing air in front of it, Doppler radar is going to pick up that air, right? So you want to reduce that boundary layer as much as possible.
So you want to make it appear to not there's not a wake there. You want to make the wake disappear.
Exactly. Right? Yeah. And actually,
you
could do that.
You make it gradual, right? You make it a gradual wake. So instead of an abrupt barrier, it's kind of spread out. So
yeah, because a normal aircraft, right? And I'm gonna get in trouble for even mentioning this, but Under Siege 2, the one on the train, right? He's trying to target the B-2 bombers with a satellite-based weapon, and you know, and the Pentagon guys are like, yeah, well, good luck with that. That's our latest and greatest. And he doesn't target the planes, he targets the wake that they create, and he's able to see them with that, right, using Doppler radar from space. So in real life, I'm sure radar systems are similar. So the way around that would be you eliminate or at least reduce that boundary layer, and you can actually do that with just a high voltage on the leading edge of the wing, and then you can create that high voltage using what's called the T.T. Brown flame jet generator. And basically I'm going way off tangent here, but it is a mechanical electromechanical, or it's a chemical mechanical separation of charge. So what you do is you inject like 15,000 volts at a high amperage into the exhaust of the jet engine. And then you have a trailing pickup for it. And when it picks that up later, the actual exhaust increases that voltage to 100,000 or 1,000,000 volts. So you're actually using the weight of the engine to mechanically create high current, high voltage. And you can just run that back to the front of your wing.
So it's basically creating an artificial toroidal plasma, just like we're observing naturally, is what I'm hearing.
Could be, yeah.
And so basically that's my hypothesis. A lot of the so-called UAP technology that is artificially created is based on natural phenomena that we can observe.
Yeah. So that's one reason for things running cold. You know what? Let me go to Josh, and Josh had a question for Michael, and then at the top of the hour we will go to David.
Go for it, Josh.
It looks like Josh is still having mic problems, sir.
Can you hear me now?
Yeah.
Okay, must have been something with this. So you said that the decay rate changes like a day before a solar flare, and that. So I was wondering if you thought that it could that could impact something like the decay rate of thorium, and that's where the radiation's coming in to fill the lower electron shells in an ionized gas, and that's what's creating the plasma.
I would think thorium would not be a high concentration, enough concentration in the atmosphere for that to be the effect of thorium.
Right.
There are other radioisotopes that are aerosoled that would be affected.
Okay, so you think that the radioactive material has to be aerosoled?
Well, it's probably some kind of closed loop system. It has to do with the surface of the planet, what's going on in the atmosphere, and what's going on in the upper atmosphere. So
Right.
it would have to be some kind of closed loop phenomena, I would think. It wouldn't be like just like a random thing for it to be able to sustain the plasma vortex that we could see it for that long a period of time.
Okay.
The
I
other
have
thing
seen,
that made me think it was plasma was at one point it appeared to be they appeared to be following the Apache aircraft. And my question to the pilots was, well, do Apaches ever get hit by lightning? And they said, well, yeah, all the time. So, I look for what I call artificial intelligence, evidence artificial intelligence. And with the Tic Tac video, for example, it's obvious that there's something artificial going on there in the space around the Tic Tac itself. You can see the phenomena, and it doesn't look natural. It looks artificial.
So I have seen some of these videos in the past, and I've actually seen the Apache video just like a week ago when it was on a YouTube channel, and they actually quoted you in the video. Yes, they did. So there was one video that I saw. It was actually on Expedition X on the Discovery Channel, where they actually filmed this. They didn't know what it was, but it was these similar types of bright lights in the sky zipping around, and they had no explanation. They just called it a UFO. But the reason that they went to this specific location is because apparently it happens in that location often enough that they were able to go there and film it.
Cool. Well,
So,
again,
in
there
that
might
case-
be something in that area where you have the right combination with terrestrial, geological features in combination with atmospheric phenomena that will repeat there.
Exactly, yeah. And in that particular case,
Kind of like Skinwalker Ranch, for example, comes to
Right.
mind.
So I don't remember the name of the mountain, but it's the episode of Expedition X on UFOs. So you could go find it and find it
Cool.
that specific mountain. So that's why I asked about thorium, because I was like, well, maybe there's thorium in the mountain or something like that.
Oh yeah, well, that could
Something
be.
else.
That could be. Yeah, there could be something. Like I said, you need all three things to sync up for it to work. I would
Right,
think.
which is why it seems so random, is because it's these three sort of separate things that nobody's really paying attention to, and they have to converge. Like all three things have to be happening at the same time.
I think what I did that was new is I didn't just limit it to, hey, what I could see. I looked at other sources of information, like the space weather was real useful, because they tell you what's going on every day, and they keep a record, and you can go back and you can look at that data and see the actual data. So,
and that's an experiment that I think more people should work with, right? I mean, that seems like I've heard that a number of times, that before a CME, I think I read something about that online. It's well documented and it's very poorly understood. It would be really interesting if somebody did something with that.
Yeah, I've always thought that this specific phenomenon was related to space weather, and that's why it seems so unpredictable.
yeah.
Awesome. Well, it is 3 p.m. Everybody, let me do this. Let me put this on gallery view. Let's everybody give Michael Boyd a giant hand. Michael, thank you for demoing the videos. I know this was ad hoc. If you have something more structured that you want to do in the future, let me know. I'm glad that we were able to get you on. What I want to do now is go to David Perez. Let me do a brief introduction for a man who needs no introduction. Okay, so for the last 7 years now, the Quantum Electrodynamics R&D team has been developing a proprietary variable electromagnetic drive that compresses the fabric of space. The VEM drive requires no liquid propellant that chemical and ion drives require to move through space. The team has performed replicable demos of the VEM drive that can produce up to 3 pounds of pull solely on battery power, and has plans to construct a more powerful set of drives capable of autonomous lift for space propulsion. So David Perez joins us to provide the latest details on their research and progress. And let me see, David is here. I will spotlight him for everyone. Sir, welcome back. Thank you very much. And thank you for being flexible on the schedule as well.
Yeah, I just happened to see the phone message and said, okay, it's an hour early, no problem.
Yeah, you know, one of the things that I found is some of our guests run way over, and then others run way under, and so you know, I just kind of try and do the best I can. But thank you for showing for us, sir.
Bet. I have a PowerPoint presentation. If you'd allow me to share my screen.
Yeah, try the green screen share button right down there.
Right. Okay.
And it looks like you are already spotlighted, and so the PowerPoint should come up as soon as you do the share screen on that. And then I'll mute myself out.
Okay. I don't know how many people have seen any of our work that we've done.
Perfect. Looks great.
I've been, this particular PowerPoint goes through the beginning of what we have done.
Oh, David, do you want to try and let me see? It's got a big subtitles thing on the right. It might be a little bit bigger if you close that. Or you could try doing screen. You could try doing screen share mode or slideshow mode.
How's that?
That looks great. That looks great.
This way we can have the flexibility of going back and forth in the slides instead of going in a sequential order. I mean, I already have them in a sequential order, but it depends on people's questions at the end, you know, how we can flip back and forth. If this is okay, we can go ahead.
No, that's perfect. That's perfect. Yeah, I think people can see it great. And thank you again, sir.
Yeah, no problem. Pleased to do it. One of the things that we've discovered is that nature really kind of aids in a lot of our understanding about, well, in this particular case, physics. It's been one of these situations where actual thunderstorms produce antimatter, which is a recent discovery. And 2007 was the first inclination, 2010 confirmation that antimatter is actually created within thunderstorms itself. The other thing that's interesting about where we've developed our engine and using nature as the basic syllabus, look at it that way, how to actually do this. Thunderstorms actually produce tripole fields. And this is not that recent of a discovery, but 1984, Earl Williams from MIT, a atmospheric scientist, discovered that studying the electric fields and thunderstorms, that the top of the thunderstorm was plus, middle was minus, and the bottom was plus. And therefore, plus, minus, minus, if you want to look at it this way, of a dipole, an inverted dipole, plus, minus, minus, plus, and called that a tripole field. And so what we found out through empirical studies was that there were several pilots that claimed and documented effects that as they flew through a certain thunderstorm situation, many of these occurred, well, they occur all over the world if the conditions are right. If they have a lot of solar winds coming in, you have the separation between in the coal areas of high and low pressure systems, where you can generate what I refer to as mega thunderstorm inducements are created, and you get a bidirectional flow of electric energy from space and from ground to space. And particularly when you get closer to the equator, like 20 degrees north latitude or south latitude, but at 20 degrees north latitude, we have documented cases of thunderstorms erupting with the equatorial propagation of electrons that occur. And this was actually discovered during World War II for radio propagation. So there's historical note of empirical results of radio transmissions back and forth being able to be bounced off the atmosphere. but the indication of these high energy levels occur into the atmosphere itself. And in the December timeframe, particularly at the 20-degree north latitude area, one of our most documented cases of Bruce Kernan was actually went through into a thunderstorm at Bimini Island. He was surrounded by thunderstorms. He was coming back from Andros Island. And what had happened was in this circling around his aircraft, he couldn't go above it, couldn't go below it. But during the last buildup of these two thunderstorms, he found a hole at about the 10,000 foot level, and he saw blue sky on the other side. Now, as a pilot, you would never want to go through that, but as a last resort, he took it. And it was either that or eventually just crash into the ocean. So he went from Bimini Island to Miami Beach in basically a second. And this was one of the initial discoveries of a, you want to call it anecdotal, fine, I don't care, it doesn't make any difference, but the science of taking this into the laboratory and doing it, duplicating it, it worked. And so the crossing over of these tripole fields induced a non-sustainable local space warp bubble. And with that said, the aircraft got caught up into this and ended up flying 100 miles in about a second. And the wings held on the airplane, and that's 360,000 miles an hour. And to go from Andros Island to West Palm Beach in 47 minutes was pretty remarkable, since it takes 75 minutes in normal flight time. He actually went further distance in that flight time that he had taken. And bottom line was, he ended up with 9 extra gallons of fuel on board his aircraft that wasn't expended, which would have been expended during that 100-mile hop. So the bottom line was, something happened. From 75 to 47 minutes, that's 319 miles an hour that he would have had traveled. The wings would have fell off the airplane. He would have had structural cracks at 220 with these A36 Beach Bonanza that he was flying, was brand new, 1970. And there wasn't too much of an explanation other than beginning to do the investigation. This was heavy detective work, really, and trying to figure out into the atmospherics and potentially what really caused this to occur. And what we find out is that he was not the only person to ever have had one of these occurrences, but significantly enough, we have a C-97 supposed to take 6.5 hours on a flight, actually only took 5. And these aircraft only travel just a little over 200 miles an hour, some modified V-29, the C-97 aircraft. And they went from Kwajalein to Guam back in 1966. And so we have records of indications of similar occurrences. Arthur Godfrey, some of you may remember him as an entertainer, but he was a naval aviator. And he had an experience when he was going from Alaska to Japan, met a similar type situation as Bruce Kernan did, flying through the clouds, and got into a sucker hole and ended up in Japan a half hour early of his normal flight time that he would have experienced. And of course, we also go back to World War II with the Tiger Moth case, where he was doing weather radar tracking experiments in the early part of the war in 42. And the bottom line here was, he got caught up in an afternoon thunderstorm in London. And he ended up flying into a sucker hole and saw blue sky on the other side of it, took the aircraft through, and ended up in northern England. He flew back, landed, reported it. Nobody believed him. But he wrote up this thing and wrote up the letter, and his family had forwarded to actually Bruce and then to me of this experience that he had. I did look up, there was a radar experimental tiger moth group in England at that time during the war, and they flew these type of aircraft. So it was an open wing or bi-wing aircraft, open cockpit. And again, these related stories from World War II to basically present day. These are the actual numbers that Bruce encountered. His particular case is probably the most documented case because he had his all the flight maps. I have his refueling tickets. I have everything that shows a evidence, the path of evidence here, and people seeing him take off and see him take and land. His clocks on board his aircraft match the ground clocks. So this also relates into Miguel Alcubierre in 1994, where he had theorized about warp bubbles and how you can use warp bubbles to travel in space. And so what was interesting here is that things that Alcubierre talked about were some of the identical things that Bruce Gernon experienced. And the fact that didn't experience any type of momentum inside the aircraft when he entered into this bubble that formed around as a result of the crossover of the electric fields of the dipole fields of the clouds. And that he had a feeling of slight weightlessness as this thing began to occur around his aircraft when he was in the sucker hole. And as he came out, you guys were talking about ionization and how that affects things. Apparently, his aircraft got covered in an ionized field. He calls it electric fog. And when he got to Miami Beach, the fog dissipated around the cockpit of the aircraft. And this has been experienced by several pilots, documented in the past as well. Is it related, unrelated? It's all related into the electric fields of these, the ionization that occurs inside these clouds and the powerful amount of energy, like 10 to the 15 watts of power that you can get in one of these thunderstorms. It goes up to about 68,000 feet. I've measured these personally on radar up to 80,000 feet when I was in the Air Force. So these things are not unusual in that area of the world. Are they common every day? Well, you get thunderstorms down there, particularly, during the winter time, will cruise up easily to 60,000+ feet. But depending upon conditions, solar winds, also helps to energize these isolated development of these thunderstorms. And so I figured out the actual forecast parameters for these things, helped in moving this particular concept back into the lab. One of the ideas that we had initially was to take a UAV, Bluebird 2, which is the design that I have an actual prototype of in the garage, and was to fly this into the thunderstorm, have a chaser aircraft, chasing aircraft on front and back of the storms, and simulate this again, or try to recapture what Gernon went through back in the 1970s. Well, everything was set up. People decided to drop out. It was too dangerous. So I was left kind of holding the bag, so to speak. And so what we did then at that point was, well, look, if this actually occurs naturally, then we should be able to demonstrate and take this into the lab. If it's real, great. If it's not, okay. Then we thought a good game and tried to prove it. Nothing happened. However, that wasn't quite the case. So whether you have matter or energy, you can bend space. I mean, this is statement of general relativity. So that's been proven beyond a doubt. And here we have is Miguel Alcubierre with his concept in '94 and his formulas of how this can happen: compression of space in front, expansion of space in behind. And so what we found was we had indications in the lab that this actually does occur. And I'm gonna show you some of the signatures that we actually picked up here. These are all formulas that people, you probably have seen these onto the internet, inflation theories, and the warp metric that Alcubierre had come up with. And he's more from a perspective of going from point A to B. But what we actually discovered in the Bruce Gernon's flight is that you don't go in a straight line, that mass actually influences, in his case, a warp bubble. And so he went in at 10,000 feet, came out at 10,000 feet, which was a lot different than what theory would lead you to believe, is that you follow a straight line. And if he did follow a straight line, he would have ended up in outer space. If he hadn't gone in the direction he was going and took that warp bubble, or the hole, the sucker hole, he would have ended up 100+ miles out into the Atlantic Ocean if he was going the opposite direction. And he would have more than likely been lost, ran out of fuel. Anyway, bottom line was taken into the lab. So this is what we do. We built an interferometer, we built some tripole antennas, and we use frequencies that I've done a number of programs for National Geographic and Discovery and History Channel, and taking that opportunity, flying in the aircraft into the Bermuda Triangle, which, you know, could be in a circle, it could have been a square, could have been anything. So, you know, they've keyed off of the triangle name and a big mysterious thing. Anyway, bottom line is we replicated frequencies that we had flown into these clouds on careful measurements, 6 to 7 megahertz at the base of the cloud, VHF frequencies into the freezing level of the clouds, gigahertz frequencies at the top of the cloud. An actual thunderstorm is a cadre of frequency, quite fascinating. But we concentrated more into the near freezing level areas of where this sucker holes begin to overlap, or the fields crossing over each other. And so what we found out is when we passed the laser through these things, is that when the system was turned on and we had a projection screen, we would get the fringe patterns from the interferometer. When the system was on, the laser would shrink, would be compressed into the screen. And when we turned the system off, the laser expanded. And this kind of gave us our first inkling into this. And we also then did a frequency analysis, and we found out that there was a redshift going into the exciter, or the antennas, that was measurable. And so we also took that part of the information as that compression, redshift. And then what we also did was we set up an experiment with the early form of one of our etched motors. And we set it as far as 140 centimeters away from the box with the torsion bar. We call it the modified Cavendish experiment. In Cavendish, he actually had some masses on the outside of the sealed case, and he could actually measure universal gravitation, taking that concept that I had done an undergrad study in a permit that I was working there at Oswego State. I took that same kind of concept and I adapted it to this. And I said, well, indeed, if this thing is really doing what we think it is in compressing the fabric of space, then it should affect a free form, or a freely available torsion bar that had equal weights. And we put ferrous material, non-ferrous material in on the torsion bar and ran the experiment. And we would start at 30 centimeters and then work our way out to 140 centimeters. And this took hours to do because we had to get the torsion bar to settle back down from movement. And we found out that the compression of the fabric of space can actually go through solid objects. So it wasn't an electrical a charge, because we had non-ferrous material, we had ferrous material, and the actual rates of movement were pretty much curvature was different power levels at 25 watts, 100 watts of power. So we're getting movement at 25 watts with non-ferrous material at 140 centimeters. So we figured out swing rates. We videotaped all this. So that led us on to saying, well, if we can make these smaller motors and they have this kind of an effect at this level of power, then what can we do with other? So we developed a throttle, the full exciter, and then we went into the this next one here, where we actually went into our linear amplifiers, and we were able to develop up to 2,800 watts of power in our linears. So we would take the exciter and just like a car, an accelerator pedal, was to adapt this and run it under battery power. So we ran the whole system with 48 volts of battery power, about 160 amp hours worth of capacity, and able to power up 4 linear amplifiers, tune it to 50 ohms with the cabling that we had to the motor. The motor would use the exciter up to 3 watts of power, and for each of the linears, total of 12 watts of power. And we also had computer control in here where the software can actually turn the system on and off. Later developments, later designs are going to allow us to set thresholds in software. We'll turn the system on and off in case of an event occurs. Because when you experiment, you just want to save your equipment. You don't want to blow it up. And so that's what we've actually constructed. And on the design board is actually a quad throttle that we can actually manipulate 4 engines at a time on a lifter. And that's one of our new concepts and where we're headed. And that's part of the update that we're going to give you. But I thought it might be necessary for some of you who've never even seen any of this. Where did all this come from? It comes from nature. And we replicated what we saw reported in nature and was able to replicate it in a lab in a micro environment versus a macro environment. So this is the exciting part of it. You also were mentioning earlier in some of your discussions, you were talking about the cold area outside of the spacecraft and the gyro, I think they call it, or the tic-tac. Well, those cold areas literally are experienced by us as well. I'm going to skip ahead, but because you guys talked about it, we get the same effect. It's almost like a Peltier effect, and that this is the air before, and we cool it to 5.5 degrees inside the V of where the fractal arrays are located. I found that kind of interesting is that our thermal infrared camera did the same thing as like what the F-18 Hornets picked up on those spacecraft. So that could lead to some additional conversations from everybody here, theorizing or whatever, but we have seen the same effect. So we have redshift. We can go through solid objects, influencing other objects. And here's the start of the update of, I'll open it for some questions right now before I get into what we're actually headed towards, what we're doing.
Okay. Well, actually, David, typically we do the Q&A at the end of each session. Do you want to run through the whole thing and then we'll come back after that?
Okay.
Okay.
That's, all right. Well, write
Thank
them
you,
down.
sir.
Write them down. Write those questions down.
Perfect. Okay.
All right. This started actually in 2010, but the actual, the thought process and investigation started actually before 2010. But the process of actually building hardware and conducting the first experiments was the first results that we ever got, October 15, 2012, at 6:05 p.m. I know because right after the experiment, my brother called me out of the blue. And I noted the time. I said, well, this is kind of historic or significant. And we actually got the laser to compress onto the screen, onto the fringe patterns. And we did a bunch of calculations for that, whatnot. But that was the first indication that something brought in from anecdotal pilot reports and testimony there was some real guts behind it. Then the World Herald came in and they did a videotaping, and they did pictures of the experiments, of the effects of the motor moving the independent masses on the torsion bar. They were the first to actually record that live, and the movement of the engine. So that was a banner day. They published that on New Year's Day, that paper article, or December 26th, I guess. Yeah, the actual date of it came out just around New Year's. Everybody was talking, made it to Reddit, actually. And since then, our whole goal was to improve the efficiency of these motors and increase the power, more power, Scotty. And that's exactly what we've done. So we have capacity now up to 2,800 watts of power. And we're going to be moving into 5,000 watts of power it'll just take a longer period of time, but we've submitted an unsolicited proposal to NASA to try to seek funding for further development of the VEM. And this means scaling it up. So we've gone from a 7-inch model to a 2-foot model. And the 2-foot model, model 17, actually produces 3.37 pounds of pull. And we've been able to lift it, and we've been able to pull other objects into a solid case again, replicating the experiment over and over again. And our conclusion has been, in looking at the power and the resultant movements, is that it's exponential in nature. So that can we take this and get to faster than light? My speculation is that at least the data shows us that we could do it. It just requires a significant amount of power, probably in the neighborhood of 100,000 watts, somewhere in that range. Right now, it looks pretty good on the lower end of where the exponential curve, 5,000 watts, you get us several hundreds of pounds of lift. That's what we're after with this. Anyway, as we moved along, we proved that we could scale it up. Still worked from smaller motors to bigger motors, and that the efficiencies is it frequency dependent? That's another study that we want to do. What are some of the unique actions of the effects of the drive? Is that we have the warp signature of the craft. We're able to literally map out. We set up a sensors, 55 sensors. We use 10 watts of power above and below Model 15 engine. Got this data. And the graphic is basically the engine is underneath the fields of compression. So the tripole fields here are compressing the fabric of space. And behind it, at 4-inch level, above and below, we measured a gentle relaxation. It's not an actual push, as Alcubierre indicated with his theory. However, our engine is operating a lot different than what I believe that he was proposing of a compression of fabricate space of an engine that not only compressed in front, but also in the back expanded quickly. So pushing, quote, the warp bubble. What we found is that not necessarily the key to create a warp field is that you can literally compress it in front and move the craft, or in this case, the engine. We have videotapes of that you can go to our website, QED-NE Nebraska, and you can see the videos for yourself, read the papers, and it's hours worth of reading and looking at stuff. But anyway, that significant signature we accomplished this past summer, and the one on top was accomplished 1.5 years before that. It took a long time to collect the data. There's thousands and thousands of points every quarter second on the run that we make. And so the bottom line was, as we made significant progress, this is the kind of goals that we wanted to achieve here with the 3.37 pounds of pull. We want to develop within the next year is a 10-pound variant with a 45 Newton pull capacity. And that we want to be able to test a variety of different fractals and frequency configurations to find out what is the true optimum frequency that we would need to construct a motor with and acquire a proper FCC frequency license for that. I'm a ham radio operator. I'm using experimental frequencies I'm authorized to use in a Faraday cage. So if anybody's out there, well, you're violating it. No, I'm not. I'm fully legal and I'm doing it. We also want to develop this a quad lifter. And one of the other more expensive aspects of this proposal is we want to deploy a 100-kilogram microsat to space for operational testing and to up orbit from the initial orbit in space, taking a ride with SpaceX, $2 million. Not a cheap aspect of this, but the idea is we can get the unit into space, then it would look similar to this. So solar panels, expand communications, motor up on top of it would be deployed in a package. So all these things going on within a 5-year time frame. The name of the satellite is dedicated to Esther Goddard, the wife of Robert Goddard, father of modern rocketry. And she was instrumental in taking all of his data sets and generating a 3-volume set. I don't know if anybody has actually read those books, but they're more than just fascinating of this single man development of an entire space program. So we named and dedicated the satellite, if it comes to pass, or we actually build it at some point, dedicated to her, instrumental in his evolution of discovery. One of the other practical sides of this, in addition to what we're trying to achieve, is station keeping for satellites and future space stations using VEM drives. There's no propellant, use only battery power or any electrical source, and that it's very economical. I mean, an ion drive is over $40 million. Deploy that in space. Neon gas, which is rare. They are making some new ones with iodine, and or krypton gas that Elon Musk has used in his little satellite deployment for internet. We're looking at this as more of a practical thing because there aren't any moving parts, and there's no propellant. In fact, that there isn't any wear and tear on the motors after hundreds of hours of operation. So artificial gravity, one of the big complaints going in space is that atrophy of exterior limbs, exercise, hours worth in the space stations and the ISS. Well, by putting these underneath the floorboards of the spacecraft, 10 to 20 watts of power, which will, and we've done biological tests, it has no effect on well, it wouldn't have any effect on the humans, but we've also used these very sensitive flies, laboratory flies, and they actually had no effects after being exposed to the motors at 1,000 watts of power. The future generations of these flies showed no malfunction, what I'm trying to say is nothing different than what a normal generation of flies at eating habits, nothing to note. The same death rates on the control group to the actual exposed group. So that radiation experiments with Geiger counters, and that we got a 1.1 microrad increase from the motor at 1,000 watts of power, which is got to 8 to 12 microrads is the normal background radiation on the Earth. It goes as high as 56, 80 with Fukushima, and when I had my radiation monitoring lab set up. Anyway, bottom line is it's biologically nil, nothing. The other ideas that we have is to not just produce artificial gravity for spacecraft, but you can literally have a bubble, a warp signature within a warp signature. So from the context of a warp bubble around a spacecraft, you can utilize these warp bubbles inside the spacecraft for artificial gravity. So we think that this is should be a pretty eye-opener for people on being able to utilize this more for just propellant or for movement of a spacecraft. Now, from a terrestrial environment, the next step is to go retrofit if the engines can be made bigger and additional power available to retrofit aircraft, possibility, designing new spacecraft and aircraft to facilitate engine development. This is we're probably 10 years out, perhaps between 5 to 10. We're looking at doing our stuff within the next 5 years to get it to a point where it's more than just significant. And ultimately, I don't know about all of you, but I want to do FTL, and I believe it's possible. Anything else? Engine design, power availability, all of that. But I believe it will either be within my lifetime, and I'm almost 70. My family lives a long time. Maybe another 20, 30 years. I don't know. But within that time frame, I'm hoping to see this. And got to have dreams, or else you can't move forward. Anyway, the quad lifter is a terrestrial adaptation of the motors, so that we can 10-pound lifters on each one of these, and that we found an RG cable 400, super lightweight. I don't know if anybody's familiar with it. It's used in aerospace, in the military. It's extremely lightweight. It's like 0.06 pounds per foot. Double shielded, very expensive stuff. Anyway, we're gonna want to hook that up into our lifter, power up the VEM drives, lift that off the ground to see on a tether. Essentially, you're using the cable to go to 30 feet off the ground or more, and then to subsequently put our miniaturized linears that we're designing in the craft like this so that we can fly it around. Now, can we do it? Well, we've been pretty successful so far. Miniaturization, as technology advances, we've been able to take advantage of the new power chips that have come out, increases our relationship, but we also produce an awful lot of heat. And that means we're going to have to cool them down with like Palantir diodes, cooling chips. Now with our standard engine, well, I call it a 3.37 pound motor. The calculations that we've made, doing the same run that NASA does in the short run to Mars, takes them about 10 and a half months with some of their spacecraft. We can do it in 18 days. We can get to Saturn and Pluto in 147 days. Project Horizon took 10 years. The 10-pound variant get us even faster, and it's a constant acceleration. And what we've actually noticed, we've pulsed this engine, and when we've actually done that, the power is going. We get about a 2-second peak in power, even after the power is turned off. It's something I haven't been able to research. I haven't dedicated the time in the research yet to look at what is that function. Is it puddling of electrons, kind of like in a magnetron tube in a huge radio transmitter, or is this an effect of the fabric of space bouncing back? We're seeing this push. But we've seen the motor advancing in its suspension hanger for minutes. But again, we're not making any claims. Something weird is going on there, and it's going to require some research. But we're opting for a large walk-in Faraday cage where we can set up multiple workstations so that we can do multiple testing all at once and try to solve some of these issues. This is model 17. It's actually 3D printed, and the fractals are mounted onto the board. This is hand wired, this particular model. And Mark Sokol has offered and graciously helped us out with one of our new solid state designs, which I'll show you in a bit. But one of NASA's new next ion drives that they have just developed can produce 236 newtons of power, but it requires close to 6,000 watts of power. And the engine that we have requires 1,500 watts of power at 15 newtons of force. And what's interesting is one of our earlier models, model 15, which was 1.26 pounds of force, we're able to measure with the motor, required 1,650 watts of power. And so the new variant is not just lightweight. This particular engine variant weighs just a little over a pound, which has allowed more movement in its suspension, in its hanger, measuring of movement, which we thought was interesting because an ion drive in terrestrial environment doesn't move at all. You can't even move a Kleenex with an ion drive. So we're getting the movement, and we're using crude crude measurements here to move masses, 1.5 pounds and 3.5 pounds of mass through solid object. We were able to move several millimeters. And again, that kind of an influence, as demonstrated to us at least, is that what we're doing is real, and that the redshift correction of the fabric of space influence through solid objects to other objects on the other side becomes pretty interesting. So as we took these measurements, we also came up with magnetic field, curvature, and gravity data. And the sensor, the Adafruit sensor that we do, is a tri-axis accelerometer. And so we got these results. And then we did the bottom sheet a year and a half later, and it saw the expansion, or I call it the lazy expansion of the fabric of space behind it. So again, gave us some very interesting results. I know there was a kind of a flap recently of a signature of a warp bubble, which was retracted, I guess. But we've had this for several years now, at least the first indicator of the fabric of space for us. And you're probably all wondering, how the hell do you do this? Well, it took a bit took years to figure it out, but cross fields from thunderstorms, and that's what we emulated on these arrays. So the perpendicular emanation of the propagation of the signal comes out from the fractals themselves. And if you're not familiar with fractals, fractals are a device which can literally take feet worth of an antenna array and reminiaturize it. And that's what we were able to do. One of the big problems was, all right, I can set up these antennas, I can simulate this with low power, I can get all these measurements. How do I turn this into something that would be practical? And working a long time ago with the Atmospheric Science Lab, Dr. Brown, believe it or not from Back to the Future, but was real interested in fractals, caught my interest, and we had lots of discussions, and we talked about antenna arrays and all this. One thing led to another, and I read a paper from a scientist from MIT, who has Fractal Array Antenna Company, developed a fractal array for his apartment for ham radio operations. He wasn't allowed in his apartment in antenna, so he came up with this unique idea, made a fractal. Well, now everybody's doing it, bending wire and making fractals, miniaturizing your antennas. But we took this a step further. So we took the VHF frequency, and I mapped that out and constructed the fractal I've seen in one of these engine. I'll relate back to it real quick. And you see these things. This is a modified Koch curve, as they would say. And this is tuned specifically for the frequency of use in the VHF spectrum. And these have worked quite well for us. Spacing is critical. Spacing between the V shapes into the arrays, we've done 50 degrees to 75 degrees. You can affect the fields by either strengthen fields, reduce the field strength by the movement of these flexible V shapes. So variable, that's where the variable VEM, electromagnetic drive, comes in, of how we were able to accomplish this. This has 4 tripole fields mounted on these arrays. We could go for more, but we kind of kept it to the simulation of what a thunderstorm actually is. So that's why this particular configuration. I'd like to experiment more and go beyond this as well. So the bottom line here is, as we said, energy and matter are equivalent. In this particular case, this overlap of the field causes a compression or a side load to go down into the bottom of the antenna arrays. And this is what causes the compression, near field crossover. Now in radar, you have near field, far field, reflective power, all this. no one's done work in this area of crossing near fields over. And I guess we may be the first, I don't know, maybe there's somebody out there, but we're the first to apply this into an operational device. And it's been very successful in replicating the occurrence of this and doing all kinds of different data measurements, and with results of the pulling force of these motors. The signature pattern that we ended up getting, thermal patterns of the cooling effect, like a Peltier effect around the engine of 5.5 degrees, significant. 3D effect or 3D printing effect to lighten the weight of the motors. The original motors were etch boards, didn't weigh too much, about 1.5 pounds. And the larger variants that we made were over 10 pounds. And then we came up with this more lightweight solution because everybody kept saying, hey, you got to show us movement, man. You can't just measure in a hanger with spring scales on here and showing the downward movement of the motor. You got to show us some physical movement versus millimeters. Well, that's what we came up with the idea to lighten it up. And so we've gone from engine model 1 to now engine model 19 and variants in between there. And you can notice that we've reduced the fractal on the plus minus side. So we got plus minus plus, plus minus plus. So we're emulating more realistically what the actual tripole fields look like in thunderstorms. This hasn't been tested. I've had some medical issues and whatnot. That's delayed testing of this particular model for over a half a year. Actually, it's been longer than that. But I'm back on the thing, and I'm getting back into ready and roaring to get out and start to test again. So health issues become a problem in doing research. This is one of our articulated models that we're going to be producing using Model 17 design. We're going to cluster. We're going to put them in a quad. And these then can be manipulated and angled in any and all directions, going backwards, forward, side to side, going in towards the center. We don't know what would happen if all of these engines were pointed in towards the center point. We don't know whether to take warp insurance or not on our lab. I don't know. It's a possibility. It's a little eerie because we're doing a lot of unknowns. And at this point, when we get to this level, we're going to be able to get over 5,000 watts of power into this unit. And it can go into a canister. I know when everybody's saying, hey, it looks like the engine pods on the Enterprise. Well, literally, we got to be able to mount these things. The idea here is that the antenna arrays, if I were to take quad loop Yagis, for example, the gain you put by doubling the amount of loop Yagis is very tiny. It's only like 30%. But the engines themselves are standalone, whereas and again, we don't have any proof of this yet. And that's why we want to cluster them. We want to find out, can we maintain that 3.37 pounds in the Model 17 configuration? And each one of the units themselves, as they interact and create the compression fields, are we going to get an actual 12 pounds worth of force being able to be measured out of these motors? Or is it going to be a percentage of the cluster? It's unknown. I can't tell you that. I'm not even speculating on this. We hope it's the latter, and we get 12 pounds out of it. But that would also be beneficial is that one could actually use these units in clusters and power up spacecraft. So if we had a 10-pound variant, you want to put 100 of these together? Yeah, it's faster than light possible at that point. I believe by being able to, using the clustering technique, we might be able to achieve some incredible speeds within the solar system itself. And that's one of my big goals, is to see the actual basic economy of space blossom. Because if you can't get places from point A to B in any timely manner, waiting 10 years to get to Pluto to get maybe some raw materials from there, or going to the asteroid belt, 16 Psyche, for example, to get to there, we need to be able to process the material, like from off-Earth mining corporation. They have robots that can mine asteroids like that, but they can't get there yet. If we could get them there and get them back and forth within just a few days, we could get ore and precious materials that we need here to process onto the Earth to further our technologies, and let space blossom as a new economic base. We wouldn't have a lot of these problems we have on Earth. At least that's my little take on the matter. So space is the future, and what I have here is some comparisons between the motors. You can see these in the paper as well. But within 20 seconds, we can generate well over 15 newtons of force. And we have the various models listed there from the Dawn spacecraft, NASA EM drives, Hall thrusters. Some of these things take up a tremendous amount of power where we really don't require a whole lot to do what we do. And what we've done since the early investigations of last year, we've gone into a new configuration, an rack-mounted configuration. And this is a nickel steel cabinet. And so we're trying to reduce any and all problems encountered with cabling and all this. And we've gone to a lot of trouble to put it all and put in air conditioning as another factor to keep equipment cool, because obviously it runs better. It gets like 130 degrees in the garage, and it can get whatever the ambient air temperature is in the winter. We've had -20 here, so I don't run the equipment past 8 degrees Fahrenheit just to protect it. But if I had multiples of everything, I could care less. I'd run it at 20 below. Eventually, it has to go to space at 200 below. We're just kind of biting my time here. We need more equipment. Money, that's what we need. These are the linear amplifiers before they've been wired up. And this is the combiner. This is where we can generate a lot of power. This configuration alone is 2,800 watts of power with our new amplifier kits that we added recently put in to update our equipment. And this is the software package that we developed, and the throttle controls, and the software can actually control this and can turn the system on and off. The future evolution development is to set limits. So if we see any points of reflectivity coming back of power, we can set the limit. If we wanted 50 watts reflected power on the cables, the system would turn off automatically. There wouldn't be any particular damage to the linears. They can take up to like 400 watts of reflected power before they burn up. And we have done that, okay? And that's, these linears are, I almost don't want to even say what the price of making these things are. It's in the tens of thousands of dollars. That's a lot of teaching I have to do in order to pay for those. And you blow one up and it's like, $4,000 just to replace a lot of the burnt up parts. It's you all know this. If you're building anything, you know what's going on out there. And then this is the concept of the quad throttle design. It looked very similar to this with slider bars and LED lights on the side. Real nice, right? In the graphic. But it just shows what our future is looking like. This is the newer lab. We ripped it out about a year ago, last summer, and we redid everything. So we increased the space, throw away stuff, and we need more space. We couldn't even hardly move between the workbenches. Now we actually have 4 feet between the benches, and we can actually move around without bumping into each other. And my wheelchair can actually get in and out of them easier now, which is a temporary thing to do. This one here, and then this is how it would look inside a spacecraft underneath the floorboards. And one of the interesting things here, I don't know if anybody has ever looked or investigated gravity doses. That's the new lingo that they have out there. We can produce at 20 watts of power, 1.74 meters per second squared gravity dose. That's more than enough to hold a human on the floor and grow plants. Half of that is what's recommended to grow plants in space. So at 10 watts of power, which would be benign to humans, and 20 watts benign to humans and plants, we could hold and create the artificial gravity environment into a spacecraft. So you wouldn't have to rotate these things around if you didn't want to, or you could fly into deep space where, if the sun isn't effective for you anymore, then, high level, you don't have to rotate the craft around. A lot of reasons to do it, a lot of reasons to utilize that ability, like less exercising in space. Some of the future things, and I'll show this one and we'll wrap this up. Flying craft, I don't know, I've always been fascinated by individual one-man system. I actually have that up at the farm. The basis or all of the structure has already been made, waiting for the motors to be perfected. And so where there's a will, there is definitely a way. This is the, our solar system. It's way out there. You don't have something to get from point A to B real quick. Then the logistics to support, which I don't have to tell you guys, you understand that. But I mean, carrying all the food, all of the other stuff that you gotta have, it's mind-boggling. You gotta be able to consume 5,000 calories a day in space. That's what it takes. That's what they've said. You gotta carry a lot of stuff with you. So if it's more than one person, I mean, you're talking hundreds of feet worth of spacecraft just to manage this stuff. Plus growing, I mean, the amount of space it requires to grow stuff, you need to be able to get from point A to B quickly. So you carry minimal amount of food, resources, and if you're operating on battery power, you don't need to lug a bunch of fuel with you. You don't need to land on, particularly like, for example, Mars, melt water, create your own fuels, because if you can't do it, you can't come back. I mean, to think about it, I guess, as early pioneers is exciting in one respect, but it's dangerous as hell. Now, if you can do this and do it in an appropriate way where you don't have to risk the crew's life to produce fuel, then I'm all for using the electric propulsion in this particular environment. Anyway, so this is the what we envision. We're building the full-scale Bluebird would be 30 feet by 30 feet, can hold up to 7 people. I'm still holding out for that. The prototype I have in the garage is 7 by 7. So it's a quarter scale of it. And then here's our last shot of going to Mars. And if I could get them to give me the money to go to the space to demonstrate the motor, I'd definitely take it out of orbit after a year of testing. I'd definitely show them that you can go someplace. With a 10-pound variant, we'll get there. Anyway, that's about it. That's the latest updates of what we're trying to do and accomplish. And I'll leave you with this picture. We're 26 million light years out from the core of our Milky Way galaxy. We'll only be able to explore potentially within the local star group, which is less than 1,000 light years. That's nothing. The Milky Way is 200,000 light years across. So that's my story, and I'm sticking to it. Questions?
Well, David, thank you, sir. So let me do this. I want to, let me see, I'm going to remove the spotlight and okay, I'm going to stop sharing on you there for a moment. Let me put this thing on gallery view. Everyone, please give David Perez a giant applause. Sir, thank you so much for presenting today. That was a wonderful and incredibly in-depth presentation. So thank you very much. I can't thank you enough for coming and presenting that. That's, you guys have done a lot of work since the last time you presented also.
Well, there's still a lot more to discover and to research. It's never ending, really. I could, our proposal has put in for over 10 people. I don't want to have a group. I need a small group of people. Right now, it's just the 3 of us. We have other ancillary people on the outside, but they don't do the technology that we do.
Yeah, no, that makes sense. Yeah. Well, sir, let's go into Q&A session. Let me jump right into James, who has his hand up. James, I think you're in Europe, right? Because it's dark there. Oh, let me here. I'll do ask to unmute. Okay. Oh, James, you're still muted, sir. There we go. Yeah.
Yeah. Is it sort of similar? Was it Arthur Townsend?
Say that again, please.
Sort of thing.
Was
it Arthur Townsend? I might have got the name wrong.
No, this is David Perez.
No,
I know.
Yeah,
I know your name. No, my advice, right? Developing some technology like this is to keep as quiet as possible about it. Don't mention it to governments, or you'll find the Air Force come and close your lab down and take all your technology away.
Well, I mean, we've already been broken into, and one of our engines were taken, fractals were removed. They were pretty slick in what they did. I even had security cameras in. But the bottom line is, I found that the best place to hide is in the public, clear view. You know, if somebody wants to do something evil to us, well, if they do, I can't stop it from happening. And I'm not wishing for any of that to occur. I want to continue with our research because this changes the way we move on the Earth and in space. It's too important to BS with politics and do all this militarization stuff. The future is space. Maybe I'm too idealistic, but we really need to concentrate to develop that new blossoming economy. And then everybody would be on an equal basis. In other words, you can make as much money as you want. Everybody would have good standards of living. I'm trying to look for the future on this. The squabbling that we have here on the Earth.
I'm all with you there. Something I thought of, does this because I'm an artist, so I'm not technically, no math skills, no engineering skills or anything like that. But I sort of get ideas pop in my head, and I've always been interested in things like this. And I just had this idea that space, it was just something come in my head that space-time has a small positive charge. I don't know whether that would pan out with what you're discovering.
Actually, I've been doing research on the entangled particles and the media space between the entanglement of the particles. And after doing, well, I was in the hospital for months. I had a lot of time on my hands. And and what I figured out and kind of realized after just, well, years of dealing with entangled particles and doing research on that, I had envisioned creating an entangled particle tunnel and pushing a warp bubble in it. However, all that has gone in the garbage.
Yeah.
And what I have found out is that the upper limit, like Karol Putov and some others have speculated that faster than light, you could only do 100 times, 1,000 times. Well, what I've come to the conclusion is it's the point of singularity. That's 26.1 million billion watts of power is your upper limit of faster than light.
Wow.
Using the concepts of, well, of a warp bubble. I think those craft that you see that they've been documenting with the video tapes from the aircraft, from the F-18 Hornets, they're all using warped technology, using warp space. And the fact that they disappear is that you just have a lot more power, and you're here 1 second and you're gone in the next, but you're already, I don't know, thousands of miles away.
No G-forces.
Well, there is no G-force. See, this is the beauty of the whole thing. There is no momentum inside. The crew is protected.
Yeah.
And this, at least we were able to glean from Bruce Gernon's flight, not just the 10,000 in and out, and the lack of tidal action around the bubble, the non-sustainable local space warp bubble, but the fact that he felt this sluggishness going into this thing, and then no G-forces on this aircraft. He went, well, if you don't want to believe 360,000 miles an hour, thousands of miles an hour in order to traverse 100 miles. But he was lost on radar from Bimini Island and reappeared over Miami Beach. And approach radar rotates every 15 seconds.
Yeah.
So if you want to argue that he disappeared for 15 seconds on radar and reappeared on Miami Beach, then make the calculation and you'll find out it's in the thousands of miles an hour.
Yeah.
But I don't think that's how this works. We're talking 10 to the 15 watts of power on crossing these fields. And this particular individual and others, as I described in the beginning of this, they went for the gusto, nature's brute force method. And that was my big significant problem. How the hell do I replicate something like that? And move an aircraft to displace it, linear displacement, hundreds of miles downrange. Do I fly it through 2 antennas? That was one of my ideas. Get 2 huge radio towers, energize it, fly the plane through it, and end up where you end up. That doesn't work. It's not practical. But the engines, fortunately for us, worked. And
it's amazing what you're doing. Great. The other thing, have you experimented with high voltage, or are you doing that?
It's RF generated, so we're actually transmitting frequency. It's propagation of electrons.
All right.
So our high voltage would be what type of RF current can we come out of the linears? And that's why radio stations can produce 100,000 watts of power.
Yeah, right.
But this stuff is too heavy, and I can't demonstrate in a lifter. We have that's why we have spent and some people criticize us for trying to make it more efficient, smaller, more output, less power in, more output of work, energy, pulling power in our case. And but we've succeeded in that. I mean, in less than a year, we've doubled the amount of output and 100 watts less of input. So we more than doubled the weight of what we can lift and 100 watts less output. 1,500 watts, 15 newtons. I mean, that's why when we submitted this proposal, we went for 10. And an intermediate would be 6 for us, but I think we can get to achieve that level pretty easily at 6. 10, I'm a little dubious. I know we can do it, because you got to set up these milestones and timeframes and stuff. Doing it full time with the proper funding, I believe that we can get to 10 pounds easy in a year.
Cool, it's great, incredible.
Wonderful, wonderful. Okay, well, yeah, and let me move along. Thank you, sir, as well. Let me go to Bill Alec next. Bill?
Yeah, hi, Tim. Hello, David. Brilliant work, by the way.
Thank
Great
you.
work. Just one thing. Now, the way that I understand it is that you're mixing 2 RF waves at an angle, right?
Perpendicular
Okay,
to
perpendicular, right
the
angle.
array. Yes.
Okay. Now,
And
I'm doing-
they're crossing over at that point.
okay. Yeah, 2 RF signals in phase.
Yes.
Yeah. Okay. Yeah, I'm doing similar work, but at a much lower frequency. And I'm replicating Tom Bearden's work in this area. And he produced what's called a scalar wave. And you have to use quaternion mathematics, okay, in order to calculate this. And when you mix these 2 waves together, it creates a sine squared term. And what's really interesting about the sine squared term is that it has a DC offset with it. It's a higher frequency sine wave, sine squared wave.
Right. Okay.
But it has this DC offset to it. And Tom called that a scalar wave or a gravity wave.
Okay.
He used the 2 terms.
Right.
And I'm kind of wondering if, well, we could be talking about the same thing.
I think we are.
Your technology is producing a scalar wave, which is a real gravity wave.
Correct.
And that's the way that the mathematics works out. You can't use conventional EM, electromagnetics, with it because it was oversimplified. The Heaviside Maxwell equations simplified the original quaternion equations, and he took the scalar component out. Okay?
So he's looking at, he's not actually producing longitudinal waves, but he's producing transverse waveform. Is that correct?
Yeah,
in his experiment?
Yeah, well, that's what I'm seeing on the scope here, is this sine squared term. And it has this built-in DC offset with it.
Yep. Okay.
So
we're talking in some certain similarities. We're at a higher frequency than what he's working on. We want to investigate HF down into the HF spectrum because equipment-wise, it wouldn't be as critical to make the VHF. The VHF equipment is tricky.
Right.
Very, very tricky. You sneeze on something and you've changed the frequency. I'm being facetious here, but it's that critical. You space a fractal over a fraction of a millimeter, and you just screwed up your entire waveform. I can't tell you how many thousands of hours that we've spent perfecting the spacing of the fractals. That's critical to generate that. And the other thing is that I'm not too concerned about the break-in that we had because they stole one of our motors. I don't care how many motors that you steal. If you don't know how to create field, you're shit out of luck.
Right.
I'll be quite honest with you. If you don't know how to generate the field, it ain't gonna work.
Mm-hmm.
So in a way, to keep it secret, all of our stuff, we got trade secrets and it's copyright, it's proprietary. We have a patent pending, but not to the point that the government can walk in and shut us down. No one patents anything anymore of significance, from my understanding. After talking with Dr. Plutov some years ago, he said nobody does this anymore. He says they don't want the government walking in and taking their stuff, like they did to Robert Goddard. I don't know if you know the real story, but Esther sued NASA and got $1 million. The only civilian to actually sue and win the case against NASA for stealing her husband's patented or his patents on rocketry.
Well, Bearden says, forget about the patent, just go for the licensing.
Yes, yeah, and that's what we're after. We're not. We're making progress. It's not enough progress that I'm happy with. I've had this medical setback, but I'm still moving forward. I'm still designing stuff. So damn the torpedoes, full speed.
Right. Yeah, Bearden said in his lectures, it's available right there on the internet. He says, well, you can do anti-gravity at 400 hertz. And John Hutchison was doing the RF waves, mixing RF waves, where he levitated a 90-pound cannonball, which was very interesting. He got that.
Yeah, that's the guy up in Canada.
Mm-hmm, right.
Hutchison, yeah. Right. He used the Tesla coils.
Fascinating work.
Yeah, it's interesting. But it can't replicate all the time. That's an issue. Is if you can't replicate, I don't know if it's positioning of his equipment, but he's not able to replicate on demand. It happens sometimes. It doesn't happen at least that's what I saw in the video.
Uh-huh.
So it's a shame that whatever he's discovered that he hasn't been able to perfect, unless he has, and he's gone secret, being able to lift things. We're all in the same neighborhood in a way, manipulating the fabric of space.
Right.
We're also looking into, and it's been in the back of my mind for some time, creating a longitudinal output waveform, scalar waves, but longitudinal, because that will give you about a 30% increase in effective power. So less power, more output of work energy. So I'm looking into that. That's kind of takes some finessing to do. Those are ideas that I'm still floating around. And I don't mind discussing that with everybody, because if you think you can solve the longitudinal issue of generating longitudinal waveforms in that manner, RF, hey, call me up.
Okay, brilliant
We have
work.
to modify all of our equipment.
Awesome. Okay. Well, Bill, thank you, sir. Let me lower your hand there. Let me go to Jared next, sir.
Hey, it's so awesome to see the amount of work that you've been putting in on this over the years. It's quite the treat to get to hear the most up-to-date work you got on it. I got a couple of questions here. The first few should be just quick, wham, bam, bam, and then the last one might take a little more longer form answer from you. So first one with Bruce German's airframe, you said that its clock matched the clocks on the ground. There was no offset in the clock.
That's correct. That's
But
correct.
his experience was of a much shorter time.
From a clock perspective, it was 47 minutes instead of 75. So he arrived earlier than normal, but that doesn't mean he time traveled.
Okay, but so his awareness, his perceptions matched the clock, which matched the ground clock.
That is correct. And that also matches Alcubierre's theory about no momentum for the crew, and that the time signature in the crew capsule would be identical to the observer on Earth.
Excellent. Next one.
No time dilation.
Awesome.
And that's significant, because if you did go to space and you were able to go faster than light, we calculated 55 million newtons to achieve that. Okay, it's not significant. We'll do it next week. It's a lot of energy, and I'm still trying to figure out how can we get there and do that. But if you're looking at the twin paradox of the twins go out, one comes back younger, the other one's an old man, you wouldn't have that with this. It means you could explore space into the deep reaches of space and come back and still be within the same time frame as we are here on Earth. And that would be a significant advantage in exploration of the solar system and beyond.
Awesome. Follow-up question. So if you said that his direction of travel, because he was traveling in a certain direction, that's why he didn't shoot off into space, why he shot, parallel to the ground.
Know that the mass of the Earth affects warp bubbles. He went in at 10,000, came out at 10,000. He followed the curvature of the Earth. And so this has also led me to try to develop a new navigation system using white dwarfs, red dwarfs, for navigation buoys in space. We got like 50,000 of these things within a couple of light years of, like about a couple hundred light years away from Earth. We have about 50,000 in the local star group. And if you were to fix on every one of those points, you could then adjust, because as you travel in space, trying to go in a straight line, you wouldn't deviate if you had a good navigation system to make the proper adjustments. Since we know now that a warp bubble is affected by mass. It's not as what Alcubierre envisioned, go point A to B. There's a little bit more to this. And that's why we'd like to get to the neutral point 1 million miles away from Earth to the sun with our spacecraft and do some experiments there and have the effect of the Earth and being able to be testing that neutral point in space, one way or the other. We have a lot of unknowns here. Like, what happens if a particle comes in towards the motor? Does it penetrate in through the motor and destroy the spacecraft? I can't tell you that right now. One of the shots that I had on my PowerPoint was a shot of Star Wars, as they go into hyperspace, and you see the light coming across, the stars. I don't think you're going to see, if you go faster than light, you're going to have a milky screen, a windscreen in front of you. And you're going to need a navigation map, a computer generated HD screen in front of you, a heads up display that shows you where the hell you're going.
Well,
because you're not going to be able to see anything.
Yeah, all that light would blue shift too, right? Or yeah, so all that would shift up into the X and gamma range. So.
Yeah, it's not what Star Trek. We've been so polluted with science fiction. Is that the reality of the world is there is no noise in space. And notice that you hear in a lot of these other Star Wars things, there isn't any noise. And as far as when you go faster than light, you're not going to see anything. It's going to be this milky something. That's what I'm kind of envisioning. Just because there is no focus, and they see the stars coming by, and it's so beautiful. Oh, I'm cruising through space. Ain't gonna happen that way, boys.
So, if I could follow up with the next question, have you vacuum tested the device at all?
Yes, it has. Actually, there was a German lab who copied our design from our internet, our website, and actually tested it in a vacuum. Now, they copied our fractals. They obviously did a shit job because they didn't get the results that we did, but they did get results, but they considered it to be down into the noise level. But the bottom line of their paper that they published here, I think it was last year or a year and a half ago, the results was 0.005 newtons of measured force. And what they did was they had the torsion bar, and they put the motor towards the torsion bar. And the motor and the torsion bar were in a vacuum. They turned the motor, and the torsion bar didn't turn as fast. And as they put it towards, and that's the most significant part of this, even though that they did a crappy job, and they only used 100 watts of power because they were too cheap to invest into a more significant, huge, well, I consider our linear power generator or amplifiers be really unique. They're custom, but they used a standard ham radio attainable linear of 100 watts. They both commercial off the shelf, but they got these, kind of results, but they didn't think it was significant, and so they concluded that our stuff was shit, that it didn't work.
That wasn't Martin Tamar's in Dresden University doing the test, was it?
I don't have that paper in front of me. Those guys pissed me off. So I read the paper and I deposited the results in the back, and it's in the in the waste paper there.
Final question.
Yeah.
So for the fractal antennas, the fractennas that you got, have you looked into going into a three-dimensional pattern form rather than keeping it in the two-dimensional pattern?
Yes. That's kind of way off for us right now. One of my electrical engineer, he insists that I use triangles like cell phones. And like cell phone arrays. And I'm leery about that because then I have to do all new research that's taken 10 plus years to do. I don't have that kind of time. I've got to work with what I know works, and I could be wrong on this, but I'm caught between a rock and a hard place on this thing. I'm trying to get results, and I'm trying to satisfy the doubting engineers that are out there of, well, you got to be over a meter of lift or else we don't believe what you did. And despite that you can pull things through solid objects, influence objects on the other side of solid objects, we don't care. I don't know what the deal is here, but I think if I was at NASA and I accomplished this, they would be parading me around like the Nobel Prize in Physics. However, since that ain't the case and we're working out of a garage, low overhead, I'll have you know, it seems like you can't do original technology or invention in a garage. All the major Fortune 500 companies started there. Are we any different? We held to a different standard? Do I have to have a lab that has $1 trillion worth of hardware to be recognized? I don't know. So that's why we're out there. That's why we put the stuff on the website. That's why we videotape everything. We document everything. We produce the images, the graphics, and all that stuff. And so if people think we've been BSing them for the last 12 years, well, that's a whole process in itself to create that kind of fib. I mean, you know, what we do is real stuff, and it's replicatable. So I don't know. I guess seeing is believing, but I thought that the videotapes that we produced showed the movement and what we were able to accomplish. I don't know. You know, I'm still a little perplexed about the attitude, but this is a paradigm shift. I just have to understand is that you have to be able to educate people on what is going on, how it works, and the ins and outs without giving away all the real secrets of this thing, of how it really works. But to at least demonstrate to them that it does work in the future is here. Now, whether we're mature enough to utilize this because I know of a ton of military applications which is not pleasant. I mean, and that's the thing that I think I talked about this last time I gave a presentation. I have real reservations on the world in general and their attitude on warlike actions, but to deliver a bomb, within a second, you couldn't defend yourself against any of this. The world would be in total chaos. That's why this stuff has to at least start in space. And then as people get more familiar with this, maybe we'll become more mature enough to accept this kind of technology to levitate cars, to fly aircraft across the ocean in a second or so, and not have to use oil, refined kerosene. I mean, think of a 747, that's 150,000 pounds of fuel that they burn. You eliminate that. And look what happened in 9/11 with 3 days of no aircraft in the sky. The actual heat energy budget went back to normal on the Earth instead of being delayed 13 hours. But it actually went back to 24 hours in, 24 hours out, in and out, no big deal. So is this kind of will affect climate in a good way? Yes, if we adapted more of this and we were allowed to advance technology to that state of using bigger and bigger craft to haul bigger masses to space and around the Earth, yes, it would definitely improve things in that capacity of our atmosphere. And I am an actual meteorologist and multidisciplinary scientist and engineer, but I teach meteorology and astronomy in colleges that I teach, and physical geography. I've cut down from 5 colleges to 3. I'm only teaching now about 50 semester hours a year, which is still over 2 positions of full-time faculty. But that's how I have to generate the money in order to fund this project. But with my latest medical fiasco that diverted money to pay bills. Oh, well, all in a day's work, right?
Okay, well, so I think, let me see, I think Robert is next, right, Robert?
Yes, Tim, thank you very much.
Yes, sir.
David, very good presentation. I'm a big fan of Star Trek. And what's interesting, first of all, Robert Goddard's wife, Esther is her name?
Yes.
Okay. You said she helped gather some information, astronomical information.
But the actual data that he produced from his rocketry, and she assembled a 3-volume set.
Can you get that online?
It's been withdrawn from libraries. I got mine from a used bookstore. Yeah, they're.
All right, so I might find on Biblio or Alibi.
Yeah, yeah.
Okay, what's it called? The set?
It's a 3-volume set. It's in the cabinet. I don't have the name
okay.
of the title. I have the books. I've read them. The title escapes me. During your presentation, I'll go over and take a look, and I'll write it down, and I'll let you know at the end of your presentation.
I don't have a presentation.
Oh, you were next. When he said you were next, I thought you were giving a presentation.
No, no.
Okay, gotcha.
Is it on your website?
Those books?
Yeah.
No.
No, I mean the title.
No.
Okay.
Of the books. But you could, if you look up the Robert Goddard by Esther Goddard, she would pop up. I'm positive of that.
Okay. What kind of data is it again?
Oh, it's photographic. She took all the photographs of the rocket launches, and she wrote all of the lab work that he had done. They're real. The entire book set is about this wide.
Okay.
3-volume set.
Yeah.
It'll cost you probably close to $300 to get this.
I think it was interesting. You mentioned there's no time dilation. Now, that's one of my researches that I don't think there is any time dilation. I don't think there's any length contraction or I forget what the other, I think it's our perception of nature that gives the appearance of this. And it's interesting you started researching thunderstorms because nature, I believe, holds more secrets than realized. Victor Schauberg discovered many secrets of nature. He had some very unconventional research and that. And I like to share with you on that if you want to. But I'd like to get your website down if possible.
Yeah, it's named QED. QED dash NE.
Hyphen?
Yes.
Okay. NE is
Nebraska.
N is in Nancy?
Yeah. Nancy
Okay.
Echo.
All right. Very good. .com?
.com. Correct.
All right. Thank you
It's
very
got all
much.
of our, it's got all of our papers, videos, images of our work. Not as extensive as I did here for your presentation. One of my guys is a little touchy about divulging too much stuff, but I figured for you guys, hey, why not?
Well, yeah,
roll on the business together.
And David,
Thank you very much, David.
Welcome.
Thank you, Robert. David, I would say, if you feel uncomfortable or if your team feels uncomfortable about divulging anything, definitely don't share that.
No. Look, I'm the guy who makes the decisions, and I've only given you what I've determined that I will give you. That's all. Which I think was quite a lot. But
oh yeah,
you don't have all the real intricate stuff that would make me very concerned. At this point, everything I presented is out there.
Yeah, that's perfect. Yeah, I don't want to steal anyone's secret sauce, so to speak. That's not what our conference
Wasn't
is
asking
about.
for that myself.
Yeah.
Okay. Other than the Germans stealing our stuff, but actually they did us a favor by putting it in a vacuum. We had some people that kept insisting that we put the whole thing into a vacuum, and I said, look, I don't have $10,000 to build a vacuum chamber and all that, and that's just like conservative, and to go down to how many pascals, I said I'm not doing this, and these guys did it, so I said okay, fine, somebody paid them 30 grand to replicate our stuff. And
how would you say your work is an extension to Townsend Brown's research, or a totally different area?
Looking at electric wind from Brown's experiments to what we do, we're not like an ion lifter. We're not affecting, quote, the atmosphere. And the fact that the Germans did us a favor by putting it in a vacuum and got the effects that we got in a terrestrial environment was satisfaction in that respect. So are we generating an ionized field inside? It doesn't appear to.
So you're truly a field propulsion type of research, I would think.
We're literally compressing the fabric of space, which is really fascinating from the aspect of, from a relativity point of view, it makes no difference where you're at. Mass or energy can affect the fabric of space. And that was another conclusion that we came to. I mean, it's on a micro or miniature aspect, but when you ramp this thing up, this has some powerful implications.
I'm interested in reading about the details on your research and thunderstorms, what you discovered, the past history of airplanes make it to the destination minutes or hours before they're scheduled to arrive.
That particular paper was removed from the website. We can probably mount it back up again because it was like old hat. You know what I mean? It's just the old story. And
I've never heard of it.
Well, like I said, I'll talk to the guys, the one guy that administrates our website. And
Don't make a big project out of it, though.
Yeah.
Well, I'll look into it. I mean, the paper's been written, you know, and it's
Right.
we had it out there before. It's just that there's an evolution to the thought process that occurred from Bruce Kernan's paper that I wrote to today. I don't want to say it's 180 degrees out, but what I'm saying is what we learned is so more detailed in understanding how this process really works.
I'm interested to see your website, what you said about thunderstorms that could be causing this phenomenon.
We
Really
talk a little bit about that in the major paper that we presented to the AIA.
Yeah.
Okay. Thank you. Thank you very much.
Robert, thank you, sir. Let me go. I'm trying to move things along a little bit. We've got probably about 10 minutes left, and then I think we're going to go to Mark. So let me go to Michael Boyd next, sir.
Hey, David. So I'm curious. You mentioned about you don't think that you can go faster than the speed of light, and would you consider quantum tunneling an example of superliminal information exchange?
Well, I've looked at that as a possibility. I mean, the fact is that nature's telling us that it can be done. I mean, it does it.
Yeah, well, your cell phone, the touch part of your cell phone, that's quantum tunneling. That's actually applying quantum tunneling. It's well accepted that it's possible to go across a barrier, what appears to be instantaneous, but if you think about it, it's
like entangled particles
going over a distance, however small it is,
right,
faster than light to do that.
Yeah.
So
and what I'm saying,
obviously there's no signal loss because, like you were describing, it's not heating up. It's not.
That's correct.
It's just a property of nature. Essentially, it's natural.
Yeah, and I think the upper limit is point of singularity for energy level, that you can't go faster than that point of singularity.
So, Tim, would it be okay if I share the video image of the Tic Tac?
Actually, not at the moment because we're kind of pushing up against our schedule, and I want to get Mark on at 5. Now we do have an open discussion coming up today later, and actually during that, Phil Bouchard wanted to present something as well. So we can hopefully...
that's fine. The other question I had, David, is your fractal antenna array.
Mm-hmm.
Have you considered stacking them?
Kind of like a supercharger, like a turbocharger.
So
yes, I have.
What you want to do is create what's called a surface plasma, and what it is it's a particle wave, but it's in the horizontal direction. So essentially, it would create your what do you call it? Your propulsion, your linear propulsion would come from this surface plasma. It creates what's called a torsion field. Between the different layers, you create a torsion field. The other thing that's important to consider is a kind of like a dielectric material that your antennas are embedded in that. And there are certain dielectric materials that have certain properties that would similar to, you're basically trying to tune it, right?
Yeah.
Recording in progress.
So I suggest you consider that, and I appreciate your answer my questions. And that's it. Thank you.
You're welcome.
Okay. So let me go to Jeremy Breeze next. We have someone else who is recording, but that's totally cool. And actually, somebody asked me about that in chat earlier. I've been recording for, let me see, close to 6 hours now. So, and then I think Jeremy is live streaming also. But speaking of Jeremy, let me go to Jeremy next. All right, Jeremy, you're live streaming, right?
Yeah, I am.
I am live streaming.
So,
I have a couple questions.
Yeah, we're live streaming on YouTube. I think we got 83 people right now watching live. The questions, I got a couple questions from the live audience. Join the Technicians wanted me to ask you about the enclosed box pendulum test that you did.
Yeah.
Can you comment on that enclosed box pendulum test?
I thought there was additional comment about that. Yeah. So the box was made of plywood and glass, and the pendulum, or the torsion bar, was suspended with monochrome fishing line. And then a neutral point was attained. We used a non-conductive mylar mirror on the end of one of the non-ferrous material. It was able to be moved between that and the ferrous material. And then we used a pen laser of a basically insignificant amount of power that was reflected off the mirror. And when the experiment was neutral, in other words, no movement whatsoever, we had dampening pads underneath the box. And so when there was no movement detected, and we turned on the system and used the laser to measure the movement of the torsion bar. So that was 1.5 pounds of material in the one experiment that we did, and 3.5 pounds of the ferrous material being moved on monochrome fishing line. And so what it proved to us was that we were able to effectively, through the compression of the fabric of space, was to move a freewheeling object within a solid case. So it went through solid material and influenced something on the other side. And we did it up to 140 centimeters away. This really eliminates the speculation that there was charged particles, that there was charged air, that there was an attraction of some kind. We went to large extremes to show that the reaction went out to that distance at 25 watts of power. I mean, that's pretty significant. And 100 watts of power. And doing the actual curvature graphs of our, that we actually recorded, and the swing rates and the algorithms that we made to do pre-prediction on power versus the engine size and variability of the motor, the main structure. So we did an awful lot of that. That took close to a year of testing that we did alone.
And then the next question I had was about the exponential fall off in the thrust after turning the device off. And did you ever measure any electrostatic fields after the operation and test for that sort of thing?
We have a tri-field meter that actually is near the cage, which would measure any of that. And we did not get any static measurements of electricity. We have other meters that would measure that as well. The magnetic field was gone, but yet we still had an energy level. And again, I haven't had time to research that particular facet of this engine, but my initial speculation was that it could be attributed to the rebounding, and that's what I feel it is a rebounding of the friction of the fabric space in the back of the motor kept pushing it. Because once the power is off, there really isn't any kind of compression, but yet in the back of the motor, there's this gradual relaxation, and it could be as a result of that. Still has to be researched. It doesn't match Alcubierre's theory, but then again, I believe that his theory was a device that compressed the front and expanded back. We're not doing that. We're only doing one in the front.
Thank you. And then the third question, I don't know if you can answer it, but it says he wants you to talk about the driving signal that you use. Anything you can comment about that, or what you're driving it with power wise and wave?
Well, these are custom linear amplifiers. They're in-house design, and we don't really talk a lot about the structure of the stuff, but what I can tell you,
waveform.
The waveform, no, we don't talk about that. We don't talk about the frequency, nor do we talk about the waveform. I'm sorry, but there's something.
You. No, I understand why, and that's why I said it. If you can answer the question. No.
Yeah. We do generate right at this point 2,800 watts with the current setup. We have a capacity to generate a little over 5,000 watts of power when all of the linears are online and combined together.
Yeah. Well, and again, don't talk about anything that you don't feel comfortable about.
I think you're right.
More than fair. Yeah.
Yeah. Sure.
Yeah. Okay. Well, Jeremy, was that just about everything that you had, or?
I might have had more, but they might have gotten lost in the mix.
I have about 2 minutes until the top of the hour.
I'll see if I can get to their questions, but otherwise.
Okay. Robert, do you want to go again, sir?
One very short question.
Your shirt is.
When do you think that patent pending will be officially available to those who want to read it?
Well, you can go on the patent office now and find it.
Oh, do you have to know the number?
You can look it up. It'd be under Paris, Pares.
We're gonna get flagged for that if you don't change your shirt.
Yeah, Robert, you're having a wardrobe malfunction, sir.
Oh, sorry. Okay.
Yeah.
Yeah, we did that years and years ago. We did that only to protect ourselves from claiming our intellectual property, the date and time, which would be, they gave us, I think it was 2012, November 17th or something, 2012. And it's numbers 60000 something 9, I believe. It's in there.
All right. Okay. Thank you, David.
Yeah.
Wonderful. Okay, well, so let me do this. We're at the top of the hour, so let me put this back on gallery view. And again, everyone, please give a giant applause to Mr. David Perez. Sir, thank you so much for sharing, and thank you for doing the Q&A with us as well. That's remarkable technology, and the depth and scope of what you presented today is just amazing. Amazing. This is it's based very much on your last presentation, as we talked about earlier in the week. But again, you've taken this so much farther, and it's just amazing work. So thank you yet again.
You bet.
Okay, so what I would like to do now is go to Mark Sokol. Mark, we are at the top of the hour, sir.
Hello.
So welcome. Now, Mark, if I could preface this for everybody, Mark gave me a laundry list this tall. So they've been going into crazy mode. I have Aiden Schaefer with him. I'll have to start. Aiden is becoming a regular in Mark's lab. So I'm going to have to start adding Aiden to the write-up with Mark. But you guys, I don't even have it memorized. So, you know what? Give me a second. I'll take a look at the. So you're working on a ton of projects right now. It's really amazing. Let me see. We're talking about, okay. So vacuum vapor depth, which is
We're actually working on it right now. We just got it hooked up and we're pulling a vacuum and just turned on the diffusion pump. The system's right behind me.
And if I could jump before I hand this over to you completely, you guys are replicating Art's parts. I just realized, I'm not sure if I'm the person who could help with this, but that would be coast to coast AM worthy material. We should try and get you on coast to coast with that and say, look, we've replicated it, especially if you're getting results. If you have videos to demonstrate with that, I mean, that would be, national audience. So.
Yeah. I mean, the Arts parts sample amongst others. When I was looking at it in light of the work with the Alzaphan experiment with EPR, trying to orient the subatomic particles in the core of the atom, there's a problem with the high frequency that we're using has a very low skin depth. So the RF is not able to penetrate the sample very well. With a sample that is made up of basically a parallel plate capacitor on a nanoscale, where you have a metal and then it's oxide and then another metal, that's basically a parallel plate capacitor. And each metal layer will then have its own skin depth and would allow for deeper penetration into a sample.
So do you think Art's parts actually is part of Alzaphan then?
It's possible. It's possible. I know Hal Puthoff claims that it was terahertz waveguide, but and then that's the new red herring. We don't have the terahertz, equipment, blah blah blah. We can't do anything with it. Let's Chicken Little, sky's falling. But I'm looking at it. Maybe it'll work in an EPR machine and produce better results. We have seen the best results with Alzaphan we've seen were with thin film aluminum deposits. So I'm thinking thin film, oxide, thin film, different materials can eventually get us there. Is that the picture of it?
That's the side layer.
Yeah, that's the side. So you can basically see it's metals with oxides and a parallel plate capacitor sort of design that we're working on. We built this massive clean room over here. I'll just show you real quick. So this is in the corner of the lab where there used to be a table in the corner. And now it's just a clean room. We're putting in the hoses for it during the conference. I was out at Home Depot earlier, getting the air hoses and parts. So it literally is just coming together right now. We might be able to vapor deposit some gold in a little bit. The machine came with gold on the filaments. So we might be able to do some vapor deposition of gold in the next hour or so, if anyone wants to stick around. Also, Aiden Schaefer's been working on his Manilas device. You want to show them that?
Yeah.
Yeah. Well, let me hand this thing over completely to you. I'm sorry for butting into your presentation. I'll put myself on mute and I'll disappear into the background, sir.
I'll bring that forward. I'm going to back into this.
Let's see. How well can people hear me? So good.
Yeah, you sound pretty good.
Okay. So the Manilas device is, I learned about it through Tom Vallone at the Integrity Research Institute and his conference on future energy. It is heavily based off of the Buckeyne schoolgirl circuit, which was shown to you could run it off of a 9-volt battery. It had the original one. He was using these jewel thieves, which this is a replication. It's a ferrite rod. There's two coils. One's the trigger coil, one's the power. I'm in the midst of fabricating the circuit. So in the heart of the Buckeyne schoolgirl circuit, they have a solid state device, a mechanical device where it's like a wheel with a bunch of magnets on it, with the north side facing out. The first battery, like you give it a kick, and you get enough of an impulse off of the jewel thieves that it will feed back some energy back into the battery. So Arthur Manilas went through and he actually this is unconditioned or degauss ferrite. This should be showing pictures or a color. It's just staying boring and gray. So he conditioned the ferrite, these large slabs, using knowledge that he gained through Floyd's suite. And I've been talking with some of the researchers on it, and the key word here is magnon, M-A-G-N-O-N, and there's this second sound phenomenon, which is where the thermoelectric conversion is coming from. So Arthur, basically, we're in the midst of doing it, which you can see is this large chunk of iron. Here's a magnetizing coil. So you have to basically degauss it, and then you repolarize it so it's, north would be on the outside. And then while you're doing that, you have this high voltage coil and you're putting a toroidal field spinning into it. I've heard from some people that Dr. Vallone has keyed me into that they may have had some sort of success with it. It's very noisy. So I said, well, why don't we, this is my function, well, not functioning, but switched over to a circle. I'm, studying flying saucers, and we've got to learn to build on the round. Also, nature uses circular geometry. So what this monster is work in progress, in that we've got huge coil. I got to be careful with ferrite. Have over the last week learned how to recondition ferrite thermally, degauss it thermally, using some knowledge I gained from foundry work. If anybody's taking notes, like you let it soak at 200 to 400 degrees for a couple hours, and then I did these 200-degree jumps. 400 to 600, let it sit for 90 minutes. 600 up to 800, let it sit for 90 minutes. And then around 880 degrees is its Curie temperature, or Neal. I think sometimes they interswitch. Curie is what I understand. So the Curie temperature is when basically the stored magnetism, there's enough thermal energy in the ferrite that it becomes non-magnetized and no longer polarized. So talking with Mark, we figured that this kind of setup, we still need to do some fabrication on it, but the idea is this is probably too thin. We've got some custom barium ferrite in process over in Europe. They'll end up being 3-inch discs and no hole in the middle, but so go in here or on here. We'll give it a whack and we'll try to develop, get it so it's like a southward pole on the inside and a north pole on the outside.
It's basically like a scalar magnet. Think of a scalar electric field where it has no polarization other than to the outer space. A magnet like that would be almost scalar, except that it is on a flat field. If you make it round somehow, put a whole bunch of them together, we could probably build a true scalar magnetic field.
So in this, when I have it finished, this this piece is just keeping the ferrite and the bismuth. This is just a leap of intuition, putting the ferrite and or the bismuth inside of it. Thinking about Bob Lazar and the element 115 and how it's like the densest element within the vehicle, and it's in the center of the vehicle in a special shape. So I said, well, you know, why not? Let's throw bismuth in there. It also might help keep so spin wave. This is where I will come up with a presentation here after we do some experimentation. So magnons and spin wave and second sound, those are key words for this research. Once you get into the second sound jargon, that's where you start seeing the physics for the thermoelectric conversion. So the second law of violation, second law of thermodynamics violation is in progress, shall we say. So it's the spin wave, once it's alive or energized, and I have the magnon going through here. The first set of coils keep that alive. I still have to wire up and create a collection coil. And the system, there are some really good books on the Bedini schoolgirl circuit, but basically another intuitive leap is that the coils, once they're charged in combination with the diodes, they act as a capacitor diode filter ladder, and they keep the waveform centered. So that's why there's 5. You could do 7 or 9. It has to be odd in order to keep the waveform that's coming out. The second sound phenomenon runs up at over 180 volts. That was, or the original Arthur Manilas circuit. That's also part of the job of the coils, is to bounce the input voltage and get it up to the 180 volts, and that keeps the spin wave going. With spin waves and magnons, the current research is going towards the very, very, very small and using like waveguides and whatnot. I think the other, for power generation, you go into big bulk substrates or bulk chunks of ferrite. From the technician notes, barium ferrite repolarizes easier than strontium ferrite, strontium hexaferrite or barium hexaferrite. The hexaferrite structure is at the 100 nanometer wavelength, and from the original presentation by Dr. Ahern, he was suggesting that if you got this stuff ground down to like the 3 to 10, 3 to 12 micrometer range, that would be, that's where you'd start seeing the second law of thermodynamics violations. Because the original device was documented. Arthur ran his home off of it for 12 years off of like 1,000 pounds of batteries using, I don't know, 25 watts or something of input power, and it was continuously outputting 70 watts of power. So
and it was getting cold in the process.
And it was getting colder, and so that is understood within the second sound phenomenon. It's on Wikipedia and such.
Basically, it would be like a thermoelectric conversion device, turning on an air conditioner and producing electricity.
Well, yeah, it's so the wave. My personal feeling is we're in the realm of quasi crystals. If you look at ice and phase changes and the spin wave that's going on in here, it's a moving phenomenon, and it's trying to become more organized. So that is having an exterior near field effect on the random chaotic motion. That's, Sorry, I don't have graphics and all that. I've got finger magic, but so we're getting there. I guess in another week or so. Well, yeah. Over the next week, we'll be playing with that.
You have to machine out some of these parts. We got them a little extra long, so they're going to be machined down for different magnet sizes. 3 separate center rods. That's where the match is going to happen. Looks like they.
Well, that's part of this.
Yeah, looks like they sent us a second one.
We have a. I think I won the bet because everybody was saying that this whole device was going to be like way over 200 pounds, and I'm like, oh, I have an anvil at home. It's like I can't lift. That's a 200-pound anvil.
That's pretty heavy.
No, I weighed it with the coil. It's at 66 pounds, and my original estimate would be that it was under 80 pounds tops. So Mark owes me a shot and a beer of something.
The next thing is.
So that's the Manilas system. I'll show it in another couple weeks here, probably July or August.
So this is a big acrylic tube that we got. And we are going to be replicating the Quantum impulse experiment. Basically, we got a superconductor. It's going to be hanging around over here. Of course, there's going to be an end plate on it, which I have over there. There's several end plates for various configurations. So there's going to be a superconductor over here with a copper pipe feeding liquid nitrogen in and a vacuum. And then there's going to be a either copper or silver block that it's going to be handing into, be feeding it with 1,000,000 volts using our megavolt Marx generator over here. Oops. There we go. There we go. That just fell down. Yep, there we go. The megavolt Marx generator. That's what happens when the wires are. Yeah, using the megavolt Marx generator. And apparently it's supposed to create some sort of gravity impulse field. We've tried this before without the vacuum chamber. It was a pretty exciting experiment. Jeremy and Jeremiah were there actually for that last attempt. This time we're going to have a high-speed camera to see if any magic happens with up to 1,000,000 frames per second. We're probably going to have to drop that down to like 250 or even 100,000 to get any decent pixels. Also, there's going to be massive Helmholtz coils that are going to be going around this, 26 inches in diameter. They're still being built. We're going to be using a massive garbage can that I got from the Home Depot gardening department as our bobbin for that. So 2 massive Helmholtz coils are going to be going around this device, this thing, creating a homogeneous magnetic field that the impulse is going to follow. It should be like laser-like down the tube, and we'll see any effects out the other side. So solid 1/2-inch acrylic. That's for the Quantumloop impulse experiment. This might be happening more like in July. I know Todd Seattle plans on coming down and sometime in July. So stay tuned for that. What else we got?
The clean room. It's been we've been working on the clean room. That wasn't there last week. So it started on like Thursday-ish, Wednesday, Thursday last week. No, it was a bit. Well, anyway, within 2 weeks, it's called 2 weeks of effort. We've got this. We've got 2 little holes left to seal. I was shooting for class 6, but
we might get there.
We might.
The vacuum pump is actually running its first cycle since we got it. We literally just hooked up the air during David Perez's presentation. It's right now down to 10 to the -5 torr. We might get it down to 10 to the -7 if we add liquid nitrogen. The system is set up right now to vapor deposit gold. That's just how it arrived. That's what the previous owners were using it for. So we may deposit some gold just to try it out in a little bit. Any questions?
Oh, I forgot to mention
the book.
If you get this book, is really useful. Now, there's some other books that this needs to be used with in combination, but what you're seeing on the cover is waveform being refracted. So this is like negative index, positive. So all sorts of terms in there. Useful book.
Oh, one other thing that we got going on here at the lab. So Todd had this idea of making split ring resonators using the vapor deposition machine. And we got a art printer. It basically can cut different materials. Over here we cut this, it's basically black tape, paper tape in the shape of a crop circle that represents pi. Actually, the differences between the little indents are the representation of the number pi. This was from back in 2009. We'll be sticking that on the wall over there. We also have the Falcon Space logo that was cut on that. But what we're able to do with that, more importantly, is vapor deposit. If we're going to be making parallel plate capacitors, we don't want them shorting out on the edges. So we're going to have vapor deposit a large area, then we'll do an oxide layer. Then the next metal layer will be a little bit in. We'll make the ring using this printer as a stencil to keep it, sort of tapered upward, and then we'll cut out the actual material from the center. Just the way we keep everything separate. Another cool thing, what we're going to be doing for oxide layers, got heat lamps. They're still in the mail. They're like food grade heat lamps that you see at ShopRite heating up chicken. So those kind of things. We've got 4 lamps coming in for a total of 1,000 watts of infrared light, and it's all going to be centered on this 6-inch diameter turn plate. And we're going to be feeding pure oxygen in there from the center, hopefully to get a nice clean oxide layer on that entire sample. And we'll be able to test it for whether it's a true oxide layer by just putting an electrode on top of it, very lightly, of course, making sure that there's no conductivity. Then we know that we're done. We're ready for the next vapor deposition layer. So that's how we plan on building the arts parts sample. Amongst other things, we got lots of different types of samples. We plan on vapor depositing silver. Right now, we're set up for gold, aluminum, iron. I'm not sure if the machine can handle iron, but we're going to try. And of course, zinc, magnesium, and bismuth. Those are the 3 layers for the art parts materials. It'll be very interesting to see what happens with very thin film layers of bismuth in an EPR setup. We know magnesium and aluminum both have very high retention values for dynamic nuclear orientation, which is orienting the subatomic particle spins using our Alzaphan experiment over this way. Actually, it's covered by the airplanes that just came down when we were setting it up.
I don't know if you get Drew on. So Drew, you made a comment. I've got a couple clean rooms from around Albuquerque. I guess they're more clean work areas, but Drew in sunny Florida, if you have any suggestions on how to improve it, we do have.
It's not 100%.
We're not done yet. We've got another anti-chain or a door to put on the inside. We have flaps right now, but if they keep outgassing, we'll switch over to something a little bit more sealed. The other technicians that have been helping Mark or working with Mark, been teaching teaching them habits over the last couple of days as we've been building it. It's just a mindfulness practice and doing what we can. We do have some funding, but we're trying to do this quick and lean. I'm sure, building a real clean room, like I've already said, we should be much bigger and a lot more filtration and such. And then absolutely no wood used, but what you're not seeing is that on the other side, we've sealed everything with aluminum tape and used.
Yeah, the wood is only on the outside. There's no wood visible on the inside.
Yeah. So Mark has a fabulous network of advisors. So we've had some people that have also had serious scientific experience come in, and he offered. We had a brainstorming session of after we got the skeleton up and sealed. So it's any tips and tricks.
Oh, he said he'd like to do it offline. So
Okay.
Yeah,
All right.
we could do that after the session. Also, David Perez, glad to see you're still alive and with us. This same technique for the vapor deposition, this is the stencil, so this would be the negative. We could put this on the vapor deposition machine and make your fractals out of any material, and make them layered too. I don't know if that's helpful. There's a rumor going around that super thin films of bismuth are superconducting. So maybe copper with a little bit of bismuth on the edge. I don't know if that'll help. But we can try.
I think that could be very helpful. You were talking about depth penetration. I've done some statistics on that, and the relationship that we found, because we were trying to look at different fractal sizes and frequencies. As the frequency goes up, the depth penetration on the material goes down. I don't know if you've discovered that yourself and run some calculations.
Very, very much so. I mean, we're in totally different wavelengths here. You're at a lower frequency. We're at 9.5 gigahertz with this EPR experiment. So the skin depth is extremely low. It's extremely thin.
It's in the high-powered microwave book.
Yeah, there's a chart and
there's an equation for it.
I asked a couple people to give me the number, and everyone came out with a different number somehow, but it was very, very thin for frequencies of that magnitude. The reason why the power grid is at 60 hertz is for deeper penetration in the wires. One of the reasons.
Yep.
Oh, yeah, Drew said that he's also setting up to do vapor deposition of the metamaterials. Drew, you want to get on? Tell us about what you're doing.
Yeah, Drew, come on. We'll have a metamaterials walk-off, man. It'd be like Zoolander.
Oh my gosh. Where's the book? Which book? Oh, the high-powered microwave book. No, it should be.
Oh, it's right there. It's right there.
Oh, look at that.
I think it will be I think it will be a giant first. I think it will be a giant first.
Oh, and this book, by the way, I took it to a conference on a whim, and the writer of the book was there.
Adel?
Yeah, he's right there, and I got a Polaroid picture with him, and he signed it for me.
Oh, there you go. Cool.
That's a Polaroid picture of him signing it.
Let's see. Skin depth. I don't know. Sorry, using the equations but if we need a better format for like sharing some of these. I don't know if that's getting across, but this book is really quite useful. Used with caution, but this is a good book. So I don't know. I've been working with Tom and Jatine and trying to get down to like a core, a core of technicians' equations or literacy, the basic practice of literacy. The camera's up here, the screen's down there. But it's just been, I've been here for a couple weeks, working nonstop. For me, this is, I enjoy it. I tried to get into Area 51 politely while I was at UNM, so it didn't work out because of whatever situation. But the knowledge I gained in the Albuquerque engineering environment, and just my natural handiness from my ancestry has helped Mark quite a bit. So I don't know. What are you doing, Mark? Oh, he's getting some stuff. Yeah, right now, like, it's just pretty much unplanned. If anybody has any good suggestions or anything, I too am setting up a,
Well, once you guys get the vapor dep in place, right? Once you guys get that in place, it would be interesting to see what kind of different substances. And so the Bismag bilayer, that's number one. And then you might be able to, I mean, I don't know how long this takes, but you could try variations on variations on that.
Oh, there's one, it's from the Unlab. I don't know if we should be talking about it. Charles Chase, Garrett Modell, he talked about it, and Jeremy Reese has also gone into it, and like using pumping energy from the vacuum and using some metamaterials. Yeah, some of the stuff in the Unlab presentation was for public release and not. So if you tuned into that one, it was good. But you have like metal and insulator, and then another metal diode.
Yeah.
I'll have to go into that. He was playing around with trying to get energy from the 0 point, and then tapping into the Casimir force. Most of my mind is in the Magnon research.
Well, but I mean, okay, so then Tony Robertson has a bunch of stuff for superconductors, right? Or Glenn Robertson, and I'm sure that's something that's been percolating in his head for years, right? And so that might be something that he might have some ideas just off the cuff, where it's like, okay, let's try this. And one of those claims was with Pogflanoff that maybe it was the surface layer because it was more dense, yada yada. So you've got some superconductor stuff there. The other one was the fellow that I interviewed who did the room temperature superconductor. The only way they were able to get that to work at room temperature was to put it in a diamond anvil.
Right. Yeah, that's how you're cheating, though. I mean, that's super high pressure.
Yeah.
But
one of the things I asked him in the interview was, I said, well, have you thought of vapor depth to get those atoms as close together as they were? And he said, yeah, that's something we'd like to try. So, you know?
Yeah. Once some research done and out of the way, the very hefty investment. So if we can make some material samples for people, I'm sure we'd love to do it. I'm trying to work with our current the night shift the night technicians and pass on some of my lab experience from Albuquerque or higher education, and we're doing like I said, literacy. I'm making sure that they're all bringing in notebooks, and we're having little physics chats.
Yeah, there you go, man.
Deepening our madness, shall we say?
Well, how large can you make these structures?
Not very. The platter is designed for maybe 3-inch discs. So not very large at all.
That's significant.
But there are CVD machines that you can walk into. So once I found out about that, it's one of the ideas I thought of. I'm aware of Art's Parts. It's been floating around for a while. It was a really useful book by that Crandall character. They all told the truth. The first half of that, or the first quarter of that book, is super useful. And the rest of it, no offense to Mr. Crandall if he comes across this, but it's like bench notes from the rest of it. But the main point was CVD. They have CVD, PVD machines that can do large sheets. Like the chamber is big enough to walk into, or they have some sort of rotating drum, and they're doing multiple things on the inside. But So the technology is there for doing larger sheets, and then we would just have to figure out how to shape it, borrowing probably from some of the innovation that Mr. Musk has done for the Starship and getting the nose cone sections. He's been reducing the amount of welding that they have to do. On this, there's a type of rare welding. It's called magnetic pulse welding. So the idea is like, how do you get a seamless saucer shape? Well, you do a large press, and then you still have some welds or joint areas. One of my models here. We're not playing around with the flying saucer shape enough, but I've thought about this. I have some notes in the back. This is 3D printed. I'm working on getting some more shells printed with this Fortify company nearby, and they have a 3D printing technology where they can actually polarize the metal or the material in it, so you're getting a better lattice forming. Like I said, Tim, in the beginning, is like it's cloud.
Yeah, no, I know there's a lot, man, and you guys are opening some really big doors too.
The magnons, so like with the magnon and the spin wave research that I found online, the best presenter so far is this Andre Chumak over in Austria. His presentation's really nice. It's on YouTube. Magnons and spin waves, just look that up. But I've said it multiple times. I've seen optical cloaking twice, and the second time I saw it, it just, it keyed me into the fact that the propulsion field is spinning around the vehicle. A very nice aerospace mentor has told me in the past that the vehicles run cold. So, if we can get the materials correct on here.
Now, do you think it was actual cloaking, or do you think it was?
No, poof, gone. It was actual cloaking. If you haven't heard of this website, National UFO Reporting Center, newforce.org. My first sighting was in, said the 12-year anniversary of it. May 28th, 8:03 p.m., Taos, New Mexico. Maybe May 20. It was the last Saturday in May in 2010. And a pair of saucers came down, and I was with my coworker and he saw them first, and he goes, "What the hell is that?" And it was two saucers. There was a white mist underneath them, and there was all these little objects around them. And we're sitting there, and I was like, "Hey Ray, I'm seeing less." And he's like, "Yep, I didn't see any bright flashes. Did you?" "Nope." "Didn't see anything like shoot off randomly." He's like, "Nope." And I'm seeing there's just the two vehicles now. He's like, "Yep." So within that amount of time of me recounting, that was the exact thing. They were gone. They were just like, and the two crewed platforms came down. They went over the hospital in Taos, and then about 10 minutes later, they were the Terminator. Nightfall was coming, and they disappeared into nightfall. The odd thing about that one is that in Cimarron, New Mexico, the next day there was crop circles, and a whole bunch of little crop circles were found in a field. So the vehicles which it's a very rare, for me, that's totally exciting. Like, oh, it's, a coworker saw them, and then another person, or these crop circles were found in Cimarron.
Yeah.
I got to find that newspaper because that would really help, and I'd be able to know how many I saw. The second time I saw optical cloaking, it was August 12th, 2012. It was, we'd gone down to El Paso, Texas, to an industrial supply place, and we were picking up a giant spherical tank to use in a pumpkin cannon, like the pressure vessel for a pumpkin cannon. And then I was watching, and I looked up, and I saw this, like, it was doing like half circles, like it'd be I'll draw it this way, but it would do like a half circle kind of move, and then another half circle kind of move, and another half circle, and then the yard manager's walking by, and I'm like, hey, yard manager, like, what is that? And he looks up and he's like, oh yeah, I see them all the time here.
And where was that at?
El Paso, Texas.
Were you guys near any nuclear materials production?
No, just at this point. So I've thought about it, and I've done a lot of. Let me go through the story, but recounting. So I'm watching the single vehicle up there, and then two little tiny glowing dots. They were flashing kind of like reddish yellow. So what is it? Optical aberration due to the atmosphere, and that there's such a small object that the arc second, or I'm not seeing much. I'm just getting, they're twinkling like stars. But anyway, these two small objects go around, they circle, and they hold position at like 10 o'clock and 2 o'clock. And then out of like the 5 o'clock position, this black dot comes out, and then I've said it multiple times, I need to find the right graphic artist to show it, but it goes, my hand's doing what it did, like
kind of came out and swirled. Yeah.
No, it was a single point, and then it looked like it exploded into a swirling thing, and then within a couple seconds, milliseconds, longer than I'm talking, all the parts were just gone, and nothing was.
Well, the reason I ask is, right, in the UAP reports, even in the government, they were talking about what they call signature management. And then the thing that I noticed was in that Puerto Rico video, there was what looked like relativistic effects. And so I was almost wondering, was it like, do you think it was trying to cloak, or do you think it might have been like a byproduct of the drive system?
No, it cloaked. I had a really strong spiritual reaction to both of these. That evening, like, we went up onto a building. I had the worst case of vertigo ever. But at that time, in Ciudad Juarez, if you go back, you can look into the maquiladoras. There's, and for lack of a better word, there was a demon. But there was a lot of murder going on south of the border. Like, these young women were just getting torn apart by guys high on something. So there's a lot of like random, really bad murder going on. So my gut instinct is that little ball, the platform that I saw cloak, went down into Ciudad Juarez, and they were doing some sort of interference on the negative karmas, the negative actions that were happening.
Yeah,
that's a strong statement. That's my personal thing. I usually don't go into that part of my feelings on that experience, but what did Mr. Mathis say earlier, that the entangled particles was why, because we know that the light's coming in, it's hitting the shell of the vehicle, and then it's not being reflected, it's spontaneous re-emission. So the propulsion field, they know what frequency the metal is, what angstrom wavelength. so that they modulate the propulsion field and I guess spin it up, catch the outgoing photonic emission, and impart some energy and spin into it and push it up either into the UV or the energy goes somewhere. So
oh, I see Charlie Crawford is here. He had some update. He was building a pretty cool coil.
Yes, and then we do have another, in case you forgot, where were they in chat? They were in chat. Let me see.
Charles Crawford III.
Drew was talking about wanting to, oh, maybe he doesn't want to come on though. He's setting up to do PBT metamaterial. So.
I can't tell if this microphone's live or not. Can anybody hear me?
Yeah, I can hear you, Drew.
Okay, wasn't sure.
Here, let me remove. I'll remove the spotlight. There we go. Now when you talk, it should show you.
Oh, okay. This is all very interesting and magnetics and spinny things and like that. Our thrust production is all static. It has no ferrous material in it. We're making multiple millinewtons of thrust on microwatts of power. So I can't talk to any of all this super high power stuff y'all are talking about, but the metamaterials is extremely interesting to me because we're looking to reduce the permeativity of our coatings on some of our plates.
Okay.
So right now we're using vacuum, which gets us a 1, but we'd love to go to a stacked operation. So our 100% of my attention right now is trying to figure out some clever coating, some type of metamaterial, whatever, in order to drop the permeativity of the metallic plates in our stack down below, or at least down to 1, without vacuum. That's the big thing. So is anybody out there doing anything like that?
Zinc oxide. I read an article that zinc oxide becomes a super resistor, super insulator at cryogenic temperatures.
Yeah, I saw that too. I don't want to screw around with cryo.
In this book,
yeah, I just ordered that book. I hadn't seen that one before.
Mu negative. They talk about MNG, mu negative materials. You have like double negative and single negative materials, but I'm not going to pretend to be an expert. I just barely got the book and I need to lock myself in a room. But what you're talking about with affecting the permeativity is, I think they're classified as like mu negative, think like mu metal.
Yeah, that sounds exciting.
And what I've seen in here is that they're using, it is layers, like with the bismuth and magnesium layers. So they're using, basically you'll have 4 layers of your metamaterial, and then you'll just stack that up on top of each other in order to get either something that's structurally sound or the right frequency correction, or the right waveform correction through the material. So it's a multi-step process, which yeah, I mean, I haven't found the direct connection. My brain's working on it, so it's just we've been busy getting the damn room built and living life. So but yeah, let's look up mu negative materials. MU, like
that's like that zero magnetic material, mu metal or
right. There you go. But it's going to be some sort of multi-layered laminate that you're going to want. The book walks you through some parts of that, like learning your layers, the spin structure of the metals that you're working on, like that's going to be important as well, like how well it polarizes. Most things are spin 1/2, but like magnesium and aluminum are like, what is it, 3/8 or 5/8. So they polarize differently.
So is that what sets up the permeativity?
I believe so. It's like the spin characteristics of the metal and how it's handling, how electricity goes through it.
Okay. Yeah, I'm the engineering side of our equation. I get mad rocket scientist, genius on the other side of it. And I just, I heard y'all talking about vapor deposition, and then I've got something that's very similar to the thing you got in the background there.
Yeah, it's a dented.
It's about 6-inch diameter platter.
Yeah. Where'd you go, Mark? So we've got part of the machinery outside. He may be checking on that. Yeah, it's thermal management is the next step, like, because it's adding a lot of heat into the building. So,
yeah, just running all the fans in well, basically you have a clean work area, but just running all the fans in a clean work area adds heat to the load, because all you're doing is compressing the air, basically. But you know, if your goal is to try and knock down particle count.
Well, we've got two. You can't see them. There's two filters up on the top, and then there's another filter inside of the AC unit. So I mean, I wanted to put another one inside, inside of the baffles as well. And then, it is positive ventilation, so it's right here. It's forcing stuff out.
Yeah, you're probably better off just setting up a massive clean bubble over the area you care about, and just forcing HEPA filtered air, because you'd need 100 times as much filtration as you got to clean that room up.
Yeah, I've been saying that we probably need more filters on it. So,
and they need to be HEPA, or the next generation.
So
it's very, very, very expensive to get clean. Clean workbenches work well, and like I said, forced HEPA filter air is probably your best effect. Just keep a steady stream of clean air moving over your whatever you think is important.
It's a good point. Yeah, the first clean room I was associated with or helped set up was at UNM, and their it's called Cosmiac. It's their growing aerospace college, but it was a hand-me-down from one of the AFRL directorates on Sandia. It was pretty simple. Like, it was mainly just a roof and four corners, and they had hanging curtains for most of it, and then sticky tape on the inside, and we're making CubeSats. Be a clean work area. So
yeah,
on this one I tried to get it as sealed. The goal was to have it completely sealed, and like if you don't have air flowing into it, like after a while you just pass out and fall asleep. But,
are you planning on wearing smocks or bunny suits or booties? And
smocks. We've got the start of it. This goes on the ground on the antechamber, the sally port. We have the curtains here. They're very smelly, so we've been leaving them outside. I think I brought them in because we might get some rain, but over the next week it looks like the forecast is okay. So I'm just going to keep them outside and try to get as much of the smell out of them as possible. Let some UV radiation harden the polymers in it a bit. But yeah, I mean, one of Mark's contacts said that anything that's plastic, like, that's going to leave a volatile organic chemical or a VOC compound. There you go. A VOC somewhere in there. So
yeah, you've got no hope of keeping your NVR levels down to anything reasonable.
Yeah.
But there's always cleaning. You just precision clean.
Well, acid washes are going to be the next step. So we've got some, personal, some PPE equipment. So we'll have to do the acid washes in that, and then put it into, something that's got forced air that's HEPA filtered on it, and then get it into the machine as quick as possible. So we're we're working lean and quick in order to get
reagent grade IPA, and I mean reagent grade, like from Fisher. $40 a gallon stuff in the bottle.
Okay.
That's your good. That's a friend. Then there's always the fluoro solvents.
How is that called again? Reaging?
It's reagent grade. So when you contact somebody like I don't know, Brulin Holding Company or Fisher Scientific, you just look for the expensive stuff, the reagent grade. And I mean, you can use methanol, or if you want to take a hit on it once in a while, or just IPA, it's a little cheaper. But it has a NVR, sub one milligram per deciliter or whatever it is. So that stuff doesn't have nothing in it. It actually is clean. The stuff you buy at Walmart, the 91% alcohol is garbage.
I know.
There's nothing you can do with it. The stuff you buy at the hardware store is garbage. There's nothing you can do with it.
I was telling Mark that, like all the stuff that's commercially available.
Even if you buy the acetone, you want to buy reagent grade everything, and get ready to spend $40 to $150 a gallon for it.
Drew, what are you building metamaterials for?
We're hoping to take our propulsion system to the next level. Right now, we're in the 1 to 100 millinewton range, but we want to jump to the Newton class. So we need the metamaterials to do exactly what you're doing. Try and reverse engineer the magical UFO skin. We actually understand what's going on, but the trick is to actually make a little bit of that stuff so we can play with it. Because our physics fully explains what's going on. So trick is to just get a hold of some of the stuff.
Who's the hour in our physics?
The other guy in it is Dr. Charles Bueller. He was on a couple of weeks ago.
So you're working with Charles Bueller?
It's the other way around. He works with me, but yes.
Okay.
We're a team.
Okay. Well, no, I'm glad that you guys finally made it back. I've been bugging Charlie for a presentation, so.
Yeah, we're trying to decide on whether we want to do that or not.
Well, and that's up to you, sir. And it doesn't have to be about your primary area of research. Most folks have lots and lots of projects. So if you have something else that you want to present on, I mean, this is kind of our community forum, right? That's what we're trying to do. We're trying to create a forum for everyone in this community to share and collaborate.
Yeah, well, pretty much we've shut every other thing down. I mean, I used to build telescope mirrors and underwater vision systems, and you have no idea. But everything is shut down for the propulsion system, so because it sucks up 100% of the time. In fact, it's operating right now out in the shop. But this was such an interesting discussion. I decided to listen in and put the test on hold. It's pretty cool.
Yeah. Well, again, we had a few folks who were kind of disruptive and that kind of grew over time. And so it's a difficult decision to boot people from, I think, any venue, but especially from one as open as ours. But we did that, and things, I would say this week, last week somewhat, this week definitely, things are kind of getting back to normal. We're getting more focused, on track. I mean, this is a hardcore, intense audience. And so it helps to let people be able to focus without a lot of the distractions.
Yeah, I'm totally stoked about that there's somebody else out there trying to build metamaterials and trying to induce changes in permeativity in the skins of the materials via RF. And I don't know anything about RF. It all terrifies me. I don't like electricity at all. But it's the future. It's definitely the direction. I had no comment on the whole cloaking or whatever stuff. I don't think any of that's part of anything I'm ever going to work on.
Drew, does your system not involve RF at all?
Not at all. No, we're pure DC. But we understand that in order to change the permeativity of these metamaterials, that we are going to have to go AC, and there are AC components of our physics. but our physics works well right now in DC, and it draws so little power. And in fact, turning it off is the biggest problem. You lock the stupid thing up and it stays running for weeks on end. So
because there's enough charge built up that it trickles through. Yeah,
we're building really nice electrodes, and you can build an amazing electrode with the most basic of materials. So that's the problem, and that's why we're moving to the next major step, which is building a variable permittivity surface. And then the only way you're going to do that is with some sort of RF modulation and whatever. I'm not sure. I'm sure there's some magic in there somewhere that I'm never going to understand. But I don't have to. I just have to build the RF system the way Dr. Bueller says to build it, and usually they end up working. So, but yeah, I'm stoked that y'all got. I got a clean room. It looks similar to that.
I got rid of my Zoom shirt. Now I'm wearing my normal. Yeah, so I feel much more comfy now. It's just a cheapo Abercrombie shirt. Well, I try and dress up a little bit. Although somebody said the other day, they're like, "Are you trying to copy Lex Friedman?" And I looked at his website. And he wears a suit and tie for everything, and I'm like, "Damn it, that was what I was going for." But now I got to change it. Then I asked Mark. I said on my website, I was like, "What if I do a black and white American flag?" And he's like, "No, don't do that. Do that." He's like, "It's surrounded by hate." I'm like, "Oh, come on, man. There goes all the good ideas." So,
Drew, you're using high voltage DC?
Yep.
And how are you differentiating ion wind or static attraction from thrust?
I run the whole thing at 10 to the minus 6 torr. The whole thing's in a vacuum chamber inside of a full Gaussian shield. Everything you can think of, and some things you haven't, we've already taken into account. And typical test is 10 to the minus 6, 5 times 10 to the minus 6. Vacuum chamber, it's all suspended. It's run on a digital force meter.
Oh, I see a gravity capacitor on your shelf too.
But
a what?
Up on your shelf, Drew. I see on the very top left. No, other side. It looks like a big pancake.
That thing?
Yeah, gravity capacitor, right?
No, thank you. That's very clever. No, I'm sorry. That's I did Society for Creative Anachronism for 25 years, and I used to build lathes, or not. I'm sorry. I used to build vintage telescopes. So that's a copy of a 1610 telescope that I created for it. That was the Hubble Space Telescope of its day. If you lived in 1610. No,
electrostatic repulsion would work in a vacuum.
Yes.
So
it works perfectly.
Yeah, I know it does. How are you differentiating electrostatic repulsion or attraction from thrust?
Okay. One more time.
How are you differentiating electrostatic repulsion or attraction from thrust in a vacuum?
Basically, the entire test cell, which is I don't know, they're about this big. The entire test cell is itself suspended with nothing around it, and that's tied to a digital force meter. So it doesn't really go anywhere. It just pulls against a little tiny force meter. So when you say electrostatic attraction, we start with, first of all, the entire box is ITO, so you can transparent, you can look inside it. That whole thing is grounded to the shell of the vacuum chamber. So there's nothing going out of that box, that's for damn sure. And then the test articles themselves start with negative plates, and then there's a couple of magical things in the middle, and it ends at a negative plate. So the entire sandwich is literally sandwiched in ground. Now we pass that ground because we actually want to measure how much charge going in and out of this toy. We pass that down through a very sensitive current meter. And then it just goes right to shield ground. So everything in the entire article is tied to shield ground. Some things pass through a meter before they get there, but it's not important. So yeah, we don't have a electrostatic attraction problem.
How many volts are we talking about? Is your potential in kilovolts or?
Yeah, a couple of kilovolts. Yeah, 3.5, 4. We were down from 150. That's what we started at a couple of years ago. We were at 150 kV, and that was ridiculously, stupidly dangerous. And now we're down to about 3. But we're headed down into the 150, 250, 350 volt range. We just need to
this higher
shrink the spacing between them.
You ever get zapped when you were working with the higher voltages?
Oh yeah. I found out the hard way that you want to have the ITO on the inside, not the outside of your containment box.
Yeah, I used to because I used to do lifters all the time.
I loved lifters. They were so much fun.
I used to get bit.
Yeah,
and, and then little stuff, right? Like little stuff like you wouldn't think of, like you when you're at the higher voltages, like you use a wooden stick to poke it, but if the wooden stick, even if the stick seems dry, if there's enough moisture inside of it, it conducts. And so you have the stick out, and it's like the same stick in summer, you're fine, you could move it around, but then in winter, it's like, and you get zapped. There's that. And then the little things pick up charge too. That was one of we noticed some anomalies with that, but little things. So like my bench vise, I'd walk by my bench vise, wasn't connected to anything, it wasn't even near anything, but those ions flowing through the air for some reason, and they would, and I'd get a zap from stuff like that. So
yeah, well, we got it down to an art now. We fire this thing up literally every day. So there's far less time that it's not running than it is running. It runs every day, all day. And
have you noticed anything weird? Have you noticed any weird anomalies?
Yeah, I could fill up one of these about every 2 weeks, and I'd say half the pages don't make any sense to me.
We saw, this is going back 20 years, right? But I was doing lifters every day in my garage. And I used a variety of power sources, but we'll say 30,000 up to 150,000 or more pulse DC, using a flyback sawtooth off a Marx generator. And, or using a sawtooth waveform off a flyback powered Marx generator. And all of our stuff was heavy duty, custom built by Information Unlimited, at the time. So it was bigger than the.
That's where all my toys came from.
Yeah, from Bob. Yeah, I love Bob. And so one day, I don't want to distract too much, but I was in just Yahoo groups, right? Everybody was in Yahoo groups at the time, and somebody mentioned something about. They were like, you notice any weird anomalies? And I think I mentioned, yeah, I've seen some weird stuff, and it was like, then you could tell people were being hesitant, and people start talking about stuff. And so one of the things that I found was a time anomaly. I don't know why. It's hard to explain now, but like, okay, you get a feel for your equipment, right? We would run these things every day, and then you turn them off, you let everything dissipate. My entire setup, my entire system would dissipate typically in about 10 minutes, and that's not a problem, because if you're running, you're building, and you're testing these things, you get done at the end of the day, you go in, you eat dinner, you're gone for 2 hours or something. What I noticed was I would come back down to the garage the next morning, before I even plugged anything in, and I would get shocks from these things. And it was like, well, wait a minute, why? There's nothing going on here. Everything should have dissipated. Why is there still high voltage here? And so we noticed stuff like that. There were a ton of little ones. There was also an inertial. There's no good way to describe it. The inertia didn't behave right.
What you want to do? You want to get Dr. Bueller, Charlie, to come on and talk about his, ketchup on the French fries doesn't hide the salt or something. He's got an analogy for everything, because nothing he ever talks about makes any sense. So, but you want to have him spend about 30 minutes giving everybody a primer in electrostatics, because then it will terrify you to your soul. You can put a lethal charge on a ground plate. You wouldn't believe it. that you can actually put a lethal charge on a plate that is tied to ground. You can put a lethal charge on a plate that is isolated in space, and you can put a lethal charge on a plate that's tied to high voltage. It is terrifying how you can pack up charge on matter. And I personally, although no one else seems to believe me, I personally believe that because I know our propulsion system works fine, and it produces far, 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 like orders of magnitude more thrust than could be explained by any of the fringe effects. So I personally believe it's time dilation. It's identical in my book to gravity. So I believe that we are, that the field that we're generating, the electrostatic field that we're generating, is dilating time, much like matter in space dilates time, and that's what we call gravity. So I think this is all very exciting, and this has been a big weekend for us because we doubled the thrust this weekend, but that's not important.
I would say, I think you're on to, based on what I've personally seen, right? And I never figured it out. And the folks I was talking with online, and back then, we never figured it out. We just kind of chalked it up in our anomalies book. But yeah,
I know it's getting way off topic, but if y'all want to have a discussion on time dilation, I got some engineering observations that certainly fit all the known pieces of the puzzle.
There was some time, I felt like time was being affected. I just never had a good idea, and we noticed some other stuff too, inertial stuff, rotation. So we had a couple experiments. We had one where, so the other thing was with the lifters were tied down, right? But you use like a string, or you'd use like a piece of wood and
built many a lifter.
Yeah, and you could touch the tethers, right? And so one of the things that I noticed was they resist an external force. And a good example is if you fly them outside, especially if they're bigger, you fly them outside and a wind comes up. These things are so lightweight and the thrust is all down. You would expect the wind is just going to blow it, but they actually fight the wind. And so they also fight rotation. And so Savoir did an experiment where he took a lifter in a completely sealed container, right? And he had the power supply was on gimbals. So he rotated this thing up. He got it going to about 20 RPM. He was blowing sideways on the entire enclosure with a fan to spin it up, right? So he spins this lifter up to, I think, about 20 RPM. It's going around at a pretty good clip. And he had a couple of these. In the first one, he turns the fan off and it just keeps going and gradually slows down to a stop. So then he does the same experiment. He spins it up. It's about 20 RPM. It's going around. He turns the lifter on and it self-stabilizes and stops, even though it's in a completely sealed container. Yeah. And it was like, well, how does that happen? In fact, somebody in the conference asked me about that last month, and I think I said it to him. It was an old Windows Media clip from like 2001 or something. Yeah, and and I saw the same thing. It was almost like they would reject an externally applied inertial force.
Yeah, the problem with lifters is there's an awful lot of high energy going on. You've got highly charged, wires and components and whatever. So you got ions flying around. It's just so much. The Earth's magnetic field can screw with it. Local magnetic fields. I mean, it's just whatever. You put it all in a vacuum chamber and all the nonsense goes away, and then you don't have to worry about being called ion wind anymore.
Yeah. Well, and in my case, I moved on to interviewing folks like yourself, but then for people like Mark who's building stuff, I will say, man, don't even mess with lifters. It's been done.
It was fun because it was nothing else. That's where I started on this. I gave up on NASA ever getting off their butts.
We're gonna do a lifter for my kids' 5th grade science fair. So
yeah, that's fun.
That's
as long as you don't electrocute the kids. That's the other.
Yeah,
it's not worth the hassle.
Put ticker tape around it. I wanted to ask you, Drew, does your technology correlate in any way to the gravitator from T.T. Brown, where he had parallel plate capacitor and various dielectrics?
Yeah, actually, I guess it could. You know, he was operating at 1,000,000 volts, so there's really no telling what the hell he was doing.
I think 70,000 for that. He said. Paper.
That doesn't that go to what David was saying about David, weren't you saying singularity is the you were saying singularity is the limit. You were saying singularity is the limit to the energy density or something like that. And I've heard variations on that.
Schwinger limit.
Schwinger limit. Thank you, sir.
Yeah, that's what I was talking about. Point of singularity, you know, the 26.1 million billion watts of power and across space-time metric in the entangled particle relationship. One thing I was going to add, I wanted to comment on, with the fields that you're getting with the subsequent charges being not dissipated, have you ever thought of using a deep earth ground rod? Most people who have grounded facilities, they're not really grounded. Like here in Nebraska, there's a 40 ohm resistance at the surface. Go down 20 feet, and it's still 30 some odd ohms of resistance. So any ground rod that they have on a house, and you were talking about getting electrocuted at the plates and things, setting the charge, I have a deep earth ground rod in my Faraday, for my Faraday cage, and it goes down 100 feet. And
Yeah, in
so-
Florida, you don't have to worry about that. I mean, my water table is about 18 inches under the surface of the dirt, and there's sulfur in it and an enormous amount of iron. So my ground rods, you know, I've got an all steel building, and the ground rods go down 6, 8, 10 feet. The facility is fully grounded. The building is grounded. Everything's grounded. No, that's not the problem. The problem is you put a couple of whatever it's microcoulombs, or I don't know. Charlie handles all the numbers. You put a couple of 4,000 volts at about 2 seconds worth of current. Usually when we get a spark, we're getting 100 microamps. Yeah, about 100 microamps. That's all the power supply can put out. But you can pack an awful lot of charge onto a little bitty surface, and then it just never goes off. And because it's electrostatic, so there's nothing you can do about it at that point. You just have to.
I mean, if you're having a
dissipate it the next day.
breakdown, Drew, if you're having a breakdown, it'll be more than the output of the power supply, because you're building up a capacitor essentially. Whatever you're charging.
Yeah, we measure the current flowing into the system. We measure the current flowing out of the system. We measure it going in and out 2 different ways. So we know exactly how much current's going through that system, and it runs out.
I'm saying for the breakdown, not your system doesn't have breakdown voltages, right? It doesn't have. It's not breaking down on a regular basis.
No, but I mean we can see the sparks. You can see the breakdown thing. We're I don't know, with 250 cycles, or I think it records at 250 or 350 hertz. So you can clearly see the spikes in voltage, because on the output graph it's got thrust, and it's got the current that it draws normally, and then you can see.
Have you tried a pulse DC?
Yes, we have. We've tried AC, tried pulse DC. So that it doesn't matter which direction the voltage is, because it's electrostatic.
There's a special waveform.
The problem isn't voltage, guys. It's all about field. I mean, you can screw around with voltage all you want. When you're in the DC land, it's all about field, and you get up around 10 to the 8th volts per meter. That's about it. And you can't afford to make better vacuum, or a vacuum good enough to stand up to much more than about 10 to the 8th volts per meter. It's just gonna, there's still ion, there's still gas in that chamber. I've gone all the way down to 10 to the -7, and this thing still breaks down around 6,000 volts, and that's about 10 to the 8th volts per meter. That's about it. So that's why we want to switch to metamaterials and direct contact, so that we don't have any gas between them, and that's why we want to.
How about oxide layers? Have you looked at
that's the magic. I'd love to get a hold of a piece of this alien spaceship. I've got a.
I mean, that's what we're building.
I've got a world-class SEM. I'd like to throw that thing in, but don't actually have a little piece of alien spaceship.
Drew, make nice to Linda Moulton Howell.
Yeah, I got Charlie on that. He says he knows her.
She doesn't have it anymore. Yeah, I know Nick Pope. He said they gave it to TTSA, who gave it to the Army, yeah, under a contract. That piece doesn't exist anymore, but we're trying to replicate it over here.
Yeah, well, I'm trying to replicate it too, so we need to stay in contact.
Definitely.
The problem is there's so little. I mean, we took a look at the picture and I threw it up and I zoomed it in, and I measured how thick the materials were, and I know how many microns each one of the materials is in thickness, but you don't know what it really is. You don't know if there's an oxide layer between them. It could just be metal on metal on metal.
There could also be. We're looking at the side. There could be another pattern when you turn it horizontal.
I agree. And
they're all unknown. But
the guy that's teaching me how to do vapor deposition, because I've done telescope mirrors for 25 years, but this is deposition on a whole nother layer. This guy makes diamond for a living. So we've got the ability to actually lay down diamond on select materials. It's very hot, but he's telling me that bismuth is a nightmare to deposit. He says it's just you might as well just give up on that before you even start.
Aqueous. No, I think the way is aqueous. There's that damn company.
You mean just a chemical deposition and evaporate away the liquid?
Yeah, you do your mother metal, the mother substrate, then pull it out, put it in an aqueous solution, let it sit there for a bit, pull it out, do another.
Oh, that's interesting. So basically, it's a combination of vapor deposition and other forms of deposition.
On our planet, in our technology on our planet, I think so. But aqueous to me,
I hadn't thought about that.
Is my
because he says magnesium is a nightmare. Or magnesium, magnesium. One of the two. No, the tin. Is it tin?
Zinc.
Zinc, thank you. It's whatever's in brass. He said the copper's easy. It's the zinc that just trashes your vapor deposition system. So, I don't know. This guy's got 40 years experience doing this nonsense.
Yeah.
So I'm just learning about the exotic metals. But he said that bismuth is a nightmare. I don't know.
Cover it with some masking tape or something to keep the chamber clean.
Well, the problem with using masking tape is that it's an aqueous base adhesive, and you'll never get the outgassing to stop. So you definitely want to be using like Kapton adhesive or Kapton tape with probably silicone adhesive, because that stuff also comes with acrylic adhesive, and that never stops outgassing. So, I mean, there are materials that are certainly far more vacuum compatible than. Anything's better than masking tape, or anything's better than black electrical tape. That's terrible. That'll never stop outgassing. That'll contaminate everything. So,
how about just aluminum foil, just mechanically held?
Yeah, that's metals are wonderful things in vacuum. They don't outgas. But again, you need to wipe everything down with reagent grade alcohol or acetone, because otherwise you're going to leave a film behind.
Yep.
And man, I did enough telescope mirrors to tell you it doesn't take nothing, because the vapors when you do vapor deposition, that vapor is about 2,000 degrees Fahrenheit, and it's moving a mile a second, coming out of that crucible. So anything it hits, it transfers its thermal energy to as it turns back into a solid, and you'll vaporize any form of hydrocarbon that's on that surface. It'll just turn it to soot, and then you'll be basically freezing your metal on top of soot on top of your surface.
Okay, so that
just makes everybody sad.
Flaking and.
Yeah, that's what causes telescope. That's why they do the little tape test after you do a telescope mirror. You put the little piece of Scotch tape on there or whatever it is, and you pull it up. And if the aluminum comes off, then you get to strip everything back off and be sad and get it all clean again and try over.
Much to learn we have.
Right now, we're just getting our first vacuum down. I think we're getting close to the -6 right now.
So he's just saying use lots of alcohol and not the kind you guys
not the stuff
drink.
not the hardware store stuff.
Yeah, the real. I've been chiming in on that, Mark.
Yeah, we have a chemical store nearby. We'll stop by on Monday and see what they have.
Yeah, they you know, like I said, Fisher Scientific, and as long as you don't live within 50 miles of a port and order a whole bunch of different chemicals, then you don't even get visited by the Department of Homeland Security.
Oh boy.
Yeah. If you do live within 50 miles of a port and order a bunch of vacuum equipment, you do get visited by the Department of Homeland Security.
How long have you had a vapor deposition machine for?
Probably 20 years now.
That was for the telescopes.
Yeah, for the telescopes. Yeah, the new system has been, I don't know, probably 6 months. Had a lot of problems with it because I bought it all secondhand and just had a lot of problems with it. But yeah, vapor deposition is a nightmare. Have you? I don't know if that system, I can't tell what it is, but does it have plasma cleaning?
It's a Denton.
It's a Denton 502A.
So
Plasma cleaning, basically, it's like a 15,000 volt set of little things like this. You turn it on and the whole chamber goes purple. And you just generate a plasma, and it just basically incinerates any organics in the chamber.
Probably not.
No, it doesn't.
Okay.
That's
kind of the last ditch effort for getting surfaces clean, is to plasma clean them.
Okay.
It just has 2 heating elements or 2 feeding rods, high current. It has a rotating center plate and I like a blocker. You know,
That sounds pretty rudimentary. Is that the one you bought at Walmart online?
Yeah, actually no. It was there's a warehouse down here in New Jersey, Bid Services. They had a whole bunch of them, and they know how to service them as well.
I'm just teasing you, man. I'm just messing with you. I bet Walmart does. Let me check. Walmart vapor deposition system.
Nah.
No.
You'd be amazed how tough it is to get an actually operational vapor deposition system put together.
Oh, this is.
And I give full credit, man. Those things are probably north of 10 grand. Put a system together that works.
Oh, it's working. It's working straight out of the box too.
Yeah.
I was just running outside checking on the chiller. It's very hard to control the temperature for the water, for the vacuum pump, the fusion pump. But we should be.
Oh, that thing has a diffusion pump?
Yeah.
Oh, make sure you got some some Dow 701 oil in there. 704, I can't remember the exact
704 we have.
The stuff that doesn't explode. That is very, very real. I don't know what you know about diffusion pumps, but that's another word for fuel air bomb. That is very, very, very serious stuff. Do not use straight mineral oil in a diff pump.
Yeah,
you get oxygen in there, you're going to wish you hadn't. Because, you know, diff pumps operate about 500 degrees above the detonation temperature of the oil in them. So
we're going to be using oxygen afterward, but not when the pump is. The valve will be closed.
Yeah, you better. Yeah, you have. Yeah, I promise you that the fireball will definitely change your attitude. Yeah, I lit one up once. It was a very bad day. That's when I switched over to turbo pumps. At some point, you realize that your life is worth more than the money that you waste on turbo pumps.
We have a turbo pump in the other room. It needs a controller though.
They all do.
And controllers keep burning out.
I actually found a guy. He had some Edwards. I can't remember which ones they are, but they're big, big 19 or 18 or 19 inch diameter monsters, like 600-pound turbo pumps. But they were the engineering spares to the Hadron Collider. You know, they got thousands of these turbo pumps over there, these giant Edwards. And this guy, I don't know where he stole them from. He had a whole bunch of them, new in the box. It was amazing. I bought a couple of those things. Oh my God. You fire up a turbo pump, you know, an 18-inch throat on it. You just watch the pressure in the chamber go, boom. I mean, I dropped 5 orders of magnitude in 15 minutes.
Wow.
That's how long it takes the turbo pump to spin up. It'll drop it 5 orders of magnitude. It is impressive.
That's crazy. Yeah, with budgets like the Large Hadron Collider, there's a lot of spending that goes awry. They buy spare parts, don't need it.
Oh yeah, I mean they have thousands of these Edwards turbo pumps, and you know I guess they cycle them out, or these were extras or whatever they were, and they were still ridiculously expensive. The ones I bought, it was pointlessly expensive, but it's worth it. You push the button and you are rewarded with, high vacuum every time. And when your goal is to, set up and run a test before you go to work in the morning, you want the stupid thing to work. You don't want to be arguing with it. And diff pumps they're just too scary. I have used them for years and they're just all terrifying.
How much did you pay for the turbo pumps? How much do those things cost?
They're about 30,000 a piece.
Wow. Yeah.
It's about a third of what they would cost now. They're about 90 grand for these monsters.
Oh wow.
And it's a fifth of the vacuum. It's a no, not a fifth. This is probably the volume of the turbo is probably about an eighth of the entire chamber. So the chamber is only about 7 or 8 times the volume of the turbo pump. So when you switch on a turbo pump that big on a chamber that small, and the chamber's only, 30 inches in diameter and maybe 40 inches long or something like that. You switch on a turbo pump that big, it's instant magic. It's just happiness. And then I operate from, it's Florida, so I have 95% humidity, and I don't have it in the shop isn't air conditioned because it's just the waste heat is just so horrendous. So I gotta overcome the molecular moisture every single time. It takes a couple hours to really, really get it down. I mean, I can test it. I don't know. I can test it at 2 times 10 to the minus 5 in about 20 minutes, or I can let it pump for the sitting next 6 hours and it's down at 10 to the minus 6. 2 to the 10 to minus 6.
So, what materials have you successfully deposited so far?
Aluminum, because I was really good at depositing aluminum mostly on silicon, on glass.
Oh, for lenses, right?
Yeah, for telescope mirrors.
Yeah, we should definitely keep in touch.
Really good at that.
Because we're going to play around with bismuth. We're going to play around with some of the hard ones.
Yeah, you want to start with some of the easy ones like nickel.
I mean, right now the machine is full of gold, so maybe we'll just do gold.
Gold is easy. Yeah, gold that's real easy to vapor deposit. Our experiments, we had a lot of problems with the magnesium when we were using just magnesium plates. We use copper-coated Kapton for all the flexi stuff, but the secondary plates were all just usually brass. But I went crazy and tried a whole bunch of different metals, and the light stuff, like aluminum and magnesium and some of the super lighter weight materials. I didn't have anything super dangerous. It just sputtered. You put 4,000 or 5,000 volts on it, and it just sputters away to nothing. So we couldn't even use that to make thrust. So we gave up on all that stuff and just stuck with brass because it's real friendly. And the nickel worked really well too. That was kind of amazing. So,
have you tried making oxide layers as your dielectric?
No, because we don't really use a dielectric. We use vacuum as the dielectric, essentially. The only thing I would want to do is I would want to replace vacuum with an oxide layer of some kind or some magic that gets me down to the same 1 permittivity or less. I mean, I would love to figure out some way to, crank out 1/10 permittivity. And some sort of magical oxide layer that generates 1/10 of a permittivity.
Zinc oxide and cryogenics.
I saw where zinc oxide makes super high permittivity, like in the hundreds, but I didn't see it where maybe I don't know if I saw it in the cryogenic realm.
Yeah, there's an article written about zinc oxide in the cryogenic realm becomes a super resistor or super insulator.
Yeah, that would be high permittivity. That'd be something that I don't know. I have to look into that again. I thought I looked into that once. Yeah, that's interesting. Yeah, I'll take a note. So anyhow, guys, this is great, but in Florida, it's 3 hours later in the day than it is for you, and I have a test to run. See, this is the coolness that was yesterday, and we're in the millinewton range for thrust. So I'm going to go and run my test, which takes about 20 minutes, and call it a night.
Okay, Drew, if you want to get in contact with me, just respond to the email that you got the invite from. That goes directly to my email.
Okay.
Alternative at Gmail.
Yeah, it'd be great to go offline and discuss this madness.
Yeah, I think we're getting into a level of technicality that's boring people out.
Make sure myself or Tom is present with Mark when we're doing this. Mark needs a backup on some of this, so.
Sure.
Yeah.
Okay, guys. Well, it's been a blast. Good luck.
Thank you,
If
Drew.
you figure out some way to make shit float, man, let me know.
Spin waves. It's all about those spin waves.
Spin waves. Yes, so many spin waves.
Oh, look
Good
up
luck.
that. All right. Off he goes. How many people are in sub 30 or so? Well, I think we've definitely gone into like open session time. So it's Tim.
Oh, it's indium oxide. Oh, I got it wrong. It wasn't zinc, it was indium.
General session, I think, is probably where this is at.
Hey, David. I have a question for you. I saw your website. You had the section on interferometers. I've mentioned an experiment called the Sagnac experiment. It's out there. There's been confusing issues concerning the controversy of results of experiments. Have you heard anything or read anything about them? In your opinion of those?
No, I hate to say this, but we're kind of confined in a vacuum. We concentrating on what we're doing, and I find that although everything that you guys are talking about is very, very interesting, that I can get contaminated pretty easily and my thoughts sway. So I try to keep focused on what we're doing and where we're trying to achieve.
Yeah.
So I'm sorry to say I can't make comments on.
I'm in the same position. There's so much interesting stuff in APEC. I can't gather them all in. I have to choose what I want to get into. I just stick with what I can do, and that's 3D modeling.
Well, I should also mention that Phil Bouchard wanted to do a presentation also. If you guys want to have Phil on now, if he's still here.
He's walking around.
There he is. Phil, would you like to do your presentation now, sir?
Sure. Yeah. Sorry, I was starting to be here, so I started cooking.
No problem. It's been a long day. I'm actually making dinner for my child in the other room. That's why I keep running away. But.
Yeah. So I like the ADAS section because my presentation are usually short and very consistent. So that's why I prefer to ask to be in the ADAS section. So I'll just go ahead.
Yeah, let's do that. Mark, you guys are all wrapped up, right?
Yeah, pretty much.
Okay. Well, let's do that. Yeah, this is big day today. Get a lot going on today, but that's awesome. This is like classic APEC. So.
Oh, by the way, thanks for the heads up on the metal 3D printer. That's pretty awesome. I thought that 3D printers would work only for plastic, but no, it works for metal. That's really awesome. So thanks for the heads up on that.
Yeah, so Phil, I have you all set up. You were spotlighted. I can see your screen. It looks great. So I would say, go ahead, sir, and just let me know when you're done.
All right. I'll just do a little update on whatever. I know a lot of people know already about that software I wrote. I just want to make sure that everybody knows. And then I'll move on to the TR3B subject. So that's the microgal. That's the software I wrote on GitHub that computes the Earth's tides. It compares the theoretical values with the experimental ones. There's a residual that is found, and it's very similar to the derivative, to the normalized derivative of the theoretical value that we should get by measuring the Earth's tides. The Earth's tides, by the way, is when the Earth rotates. It aligns with the sun at noon and at midnight, but at 6 in the a.m. in the morning, 6 p.m. in the afternoon, then it's going to be perpendicular. So there's a preferred velocity, there's a preferred direction here we measure. So that clearly points out that there is some ether wind or superimposed co-moving gravitational layers in place. So it's pretty obvious at this point that that there is something, obviously. So, and also as I was saying quickly in the APEC forum, the location of a white hole, how do we determine that? The black holes really are aggregate, like it was proven last year, so there's no singularity or wormhole, which, by the way, relativity relies on, because because space needs to go somewhere according to relativity, so it kind of refutes relativity here, and also the gravitational redshift that is kind of mutually exclusive with the locality of relativity. So here, there's a whole bunch of facts. I had a proposal for the ISS, for an experiment on the ISS that was basically the Michelson-Morley experiment aboard the ISS, but I'm not sure if it's worth it to perform it anymore, because all the theories, I have refutes relativity. So I'm gonna move on to the fun stuff. Just 1 second. Yeah. Here we go. Okay, gravitomagnetism and the TR3B. So if we take the measurement units of the virtual particles, the electric, the magnetic, the gravitoelectric, and the gravitomagnetic, it comes down to this. If you simplify all the mathematics, it comes down to this. And the gravitomagnetic particle is actually the simplest one. It's measured in hertz. So clearly, it's pretty obvious that the only thing it can affect is time. So if you have a virtual particle that travels around and it's going to modify the time, which means you can modify the speed or the acceleration of a projectile or anything you want. So that it's kind of the root of all the other particles, and also yeah. So also since we can, it's dipole, gravitoelectric, which is gravity is monopole. So that's why it's a force that can only be superimposed and added, and so on. And now, if we move on to the magnetic field, this is a standard magnet. This is a current loop that generates a magnetic field, which is the same thing as a gravitomagnetic field. And since I just said that the gravitomagnetic virtual particle modifies the time, then you can actually it's possible to find a way to mold the lines of force here to modify the time in such a way that you have some sort of force field, a force field that slows down projectiles going at you. You can also create a tunnel with the walls being made out of virtual gravitomagnetism, the virtual particles. So if you create the walls using that, then you're gonna stop all the other particles, which include gravity, which means you can lower the gravitational potential in it, which means you can travel faster than light. So the only requirements I'm not sure there is if gravitomagnetism, I'm not sure about the speed of gravitomagnetism. Obviously, if it's the underlying force, so if it's faster than c, then we could create that tunnel on the fly. So I'm pretty sure it is, because it's really the underlying particle here, but I'm not sure yet. I'm not 100% sure. So basically, you have a starship, you can create a force field and a faster than light tunnel. And this is the experiment I already done, the spinning disk experiment that I did that was successful. According to a certain RPM, you get some gravitational acceleration shift according to a certain distance. And my next experiment is going to be slightly different. It's going to be based on a cyclotron. That's going to confirm for sure that we're using professional equipment and lab equipment, that we have the right measurements. And also it's also possible to do that using liquid metal vortex, which basically can be done using magnetohydrodynamics. You can make a liquid metal spin very fast, and yeah. So according to a certain velocity, it's going to create a gravitational acceleration shift. But the nice thing is you can stack up the vortices to add up the acceleration shift. So if you have a vortex that creates 7 meters per second squared, then you stack 2 up, then you get 14 meters per second square, which is already higher than 9.8 meters per second squared, which will create anti-gravity very quickly. And yeah, that's basically what the TR3B is. It's a gravito-magnetism generated using magneto-hydrodynamics very intensively. So that's all that it can be. It's either plasma or liquid metal, but plasma is probably what they use because it needs to go very fast. I have, like you say, like you just say, so I have all the calculation. They're undisclosed. The secret sauce still is undisclosed because I'm looking for VCs. But that's the big picture. That's what the TR3B can only be. So yeah. So that's my short and consistent presentation I wanted to share with you, and that's about it. So yeah, thanks for your time. I really appreciate.
Yeah, absolutely. Well, everybody, here, let me put this thing back on speaker view. Everybody, let's give a giant applause to Phil Bouchard. Sir, thank you. Thank you for the impromptu presentation. Thank you for the update on your research. That is awesome, man.
Yeah, thanks. It's and thanks for the forum. I debate some things. There's a lot of emotion sometimes. Debate some things, but the conclusions I got out of it, it's very very valuable, and it's everything I said at the beginning is everything I learned on the forum. So thanks a lot for that. I really appreciate.
Oh yeah, absolutely. Well, on that note, let's go to open discussion. Everybody, open discussion. No holds barred. So, you know what? In the background there, I see. Actually, I should see if Tony wants to tell me about.
Question for you: how do you? What are your assumptions about measuring the gravitomagnetic components in your experiments? Can you expand on that?
My assumptions. Well, it's based on the first experiment, the spinning disk I did in October of last year, that confirms my calculations. Now I'm just scaling it up. That's all I'm doing, using a cyclotron and a vortex, a liquid metal vortex.
What equipment do you use to make the measurement of the gravitomagnetic forces, their components?
For the spinning disk, I just use my own cell phone. There's a gravimeter in it already you can use.
Mm-hmm.
But for the cyclotron, we're going to use a professional gravimeter. To confirm that my cell phone is not misleading us.
Oh, okay. Okay, so you made some theoretical prediction about the gravitomagnetic component, and then you measure it?
Yeah, exactly. And I did try the spinning widget, the fidget spinner, sorry. It didn't go very fast using a compressed air. That didn't work. It didn't go that far with that, but the week after I was able to measure something with the spinning disc. So it's an engine. Obviously I didn't make it on my own, but it's an engine that spins very fast. So yeah, so we're scaling it up right now, and we're looking for VCs. So yeah, I know that I'm still trying to understand. I know you modify time and things like that using gravitomagnetism. That's why it fits very easily with finite theory, because it's based on time dilation, time contraction only. And they're still trying to figure things out down at the quantum level. I measured it experimentally, but I did not derive it. So there's still some work to do. I need to do some work that needs to be done on the derivation side. But other than that, I'm all set, basically.
How are you separating that? On the one side, you're measuring gravity, and the other side, magnetism, and it's not that one is confusing with the other. I mean, how are you separating that you are measuring the true components of each one and the gravitomagnetic component? Are you separate and then measure together, or are they all three? You one gravitomagnetism come together, you measure, and then you measure gravity, and then you measure the magnetic component. Are you taking measurement all three at the same time, or just two of them?
So I made sure that my cell phone was not affected by the magnetic field, and that's why the cell phone. If you get the cell phone close to a monitor or anything electronic, it's not going to shift. It's not going to affect the measurement. So that's why I know that the only thing you can measure is the gravity. So that's. But there's still room for errors. But now I'm going to use a real gravimeter shield.
Okay.
For the cyclotron experiment.
Oh, okay. Now that things become clearer now. Hey, thank you. Good experiment you have there, and keep on making progress. Thank you.
Yeah, I'll give updates here and then.
So hi. So I just had a question. So using gravitomagnetism via MHD to generate thrust, is that what it is?
Yeah, it's
or you're doing anti-gravity. Like what? Just kind of curious about that.
Yeah, it creates an acceleration vector.
Okay.
Depending on the either if it's clockwise or counterclockwise, it's going to create an acceleration vector, and if it's greater than 9.8, then you're going to fly.
Okay. Yeah, because the reason I was curious about it, because I know gravitomagnetism has it's quite. I think it's been measured as very low. So is it something that you've been able to accelerate it, or somehow using MHD? Is that what?
Yeah, it's the theory says that it's 10 to the minus 27, something like that.
Yeah.
The theory was done by analogy, not by derivation.
Okay.
So it's a wild guess, and apparently it's not right. So by a large factor.
Oh, I see. That's interesting. Okay. Yeah, that would be excellent then if the difference is from 10 raised to minus 27 to much higher, then yeah, that's a tremendous advance then. Yeah.
One more question. Have you done the experiment, just to get data comparison with the disk spinning horizontal, and then you put it vertical? Because on a vertical disk, you would have the additional, the gravity produced component of the gyroscopic force. Have you done it at like, for example, this vertical, horizontal, and then in between to see what are the differences? And you can isolate all the component from the data.
Yeah, you mean 45 degrees and 90 degrees and all that?
At 0 degree, exactly.
Yeah, no, I just did it vertically. Well, I mean the horizontal plane and the gravimeter on top of it.
Oh,
But
okay.
I could have done it 45 degrees and then compared the theory with the experiment, I guess.
The gyroscopic force produced when you had it vertical at 90 degrees, you know, parallel to the gravity vector, the disk, did that, the gyroscopic force, the spinning disk produce, agree with your data on the gyroscopic force, what it would be if, for example, that if it is not restrained, it would produce precession. But I imagine you have a disk restrained, so you cannot produce precession. So is that how you did it? With the disk rigid so that there will not be any precession, but you can measure the gyroscopic force, or just how was it?
Yeah, 1 second. I'm just gonna turn off the jumper. Yeah, sorry about that.
Okay.
So, sorry, I don't understand really the question.
Okay. What I was asking, since you did the disc spinning vertical, did you have it rigid that it will not move? Because if you have a disc spinning vertical, there will be a gravity-induced gyroscopic force that can cause the precession of the disc if the whole device was free to rotate. Do you do it, you know, that it was not able to rotate? And do you measure any force, you know, on gyroscopic induced force at, let's say, the 90-degree position, you know, horizontal force on the disc?
Yeah, I didn't measure directly any force directly on the disc. It's kind of they don't have control of the speed or anything like that. I just know it was going at a certain speed, but I didn't measure the precession or anything like that.
Well, it was rigid. It was fixed that it will not move.
Yeah,
because if it was fixed, you cannot measure any precession.
Yeah, exactly. It was fixed.
Oh, okay. All right. Okay. That make it clear. Thank you.
Yeah, no problem. So yeah, like I was saying, if you get the right speed and you stack up the vortices, then you're gonna get anti-gravity very quickly. So that's a cool thing. It's easy to scale up. So it's unfortunate. Is Jared still here?
Yeah, I'm here. I was wondering, I mean, I know you have the Mercury. I mean, I read, you know, there's a lot of prediction about the Mercury, and I've seen a lot of the video about the Mercury. I know many years ago I did Mercury experiment, you know, that thing turned out to be very good, you know, except, you know, just get it spinning. But what you're doing, you know, since you were measuring any anti-gravity effect, you know, especially on the spinning, and that's a part that I'm curious about, you know, what is, you know, the result when you have a spinning a high speed, because I imagine the higher the speed, to make the Mercury a spin factor, you probably have to need a very strong magnetic field and also an input of current, you know, electric current, to make sure that it speed up a lot more. And so there should be some component there, a gravity and anti-gravity component, something that I still see a lot of debate, you know, many people predict it will be there, but I have not seen any accurate data. and it look like you are giving more than everybody else is giving, because you at least you have some data. You have make some educated guesses what it would be, and you're producing something, and that makes your experiment much more interesting and much more important to clarify the whole subject, whether it does or does not produce anti-gravity wave, the spinning the vortex of Mercury.
Yeah, I got the data. I'm pretty happy to learn that we can 3D print metals. So I'm gonna do the apparatus, the vortex, the third experiment very easily now. So yeah, that's awesome. That's really cool. Wasn't sure because for the magneto hydrodynamics, you need metal mixed with wood or plastic, something like that. So just calculated that within maybe within an hour you can get a speed high enough, either using mercury. I would prefer using gallium, but we can measure a difference, a gravity shift within an hour. So that's pretty cool. You just spin it up. At some point, it gets so fast that you can measure a gravity shift.
Oh, Phil, I left the spotlight on you, sir. So it has been on you for the last 25 minutes. I just removed that, so it's still on you as long as you're the one talking, right? But
one more question: have you considered doing the same experiment with ferrofluid?
I wanted to. I was thinking about it using a toroid, but apparently I ran a simulator. I can forward you the link of the simulator. It's a cool website that have plenty of JavaScript online simulators, and you see that the ferrofluid inside of the toroid is gonna move randomly. It's not gonna move according to the magnetic field inside. It's gonna spin. It's gonna rotate. The particles are gonna spin on their own. They're not gonna spin in circle. So that's a very, very nice website. I already posted it on the APEC forum on WhatsApp, but I can forward you the link if you give me your email address. Are you on mute? I can't hear anybody.
I will send you the email.
Yeah, okay. Yeah, I see a comment here. The density of mercury is a little bit different than gallium. I know that gallium is slightly less dense, but still pretty. Still is pretty dense. The density is pretty acceptable. All right.
Okay, I put the email there.
All right, I'm just gonna.
Actually, Charles Crawford is here. He wanted to present. Hey, Charlie.
Sure. Hello, everyone.
Hey, Charles.
I can give a quick update of the Graviflyer. So I've been testing it for about 6 months now, and recently I have been pretty busy, so I haven't had as much time as I wanted to, and so has Todd Desiato. But we've been both looking at it from different directions, and yeah, I got the first kit from Alex Chekhov. So I replaced the center disc because when he shipped it, it was bent. And he's the second kit has also been shipped most of 2 out of 3 packages. So I'll be helping with reconstruction of that kit and testing. Hopefully, if I could fly down to meet Russell to work on that. And yeah, we've been comparing notes because there's some changes in the second kit that's different than the first one. And I've been asking Alexi for more detailed tuning instructions. So with each test, I get a little bit better at learning how to tune it. And I haven't noticed any lift or anything unusual yet, but hopefully before the end of this year, we'll be able to confirm or deny that it lifts or not. Still looking pretty promising. So I've got all the circuits working and I've reproduced a lot of them. Let's start here. The Tesla coil, which was one of the original he showed in the videos. Make it too shaky. I've replaced some of the transistors, added some 12-volt fans to cool it down. And that's the original coil he sent me. And I've reproduced his ultrasonic sensor. This is the one he sent me. And this is the circuit on the little proto board. And this is the high voltage circuit he sent me in that container. And I've reproduced 3 of those with these 3 flyback transformers, and also got another equivalent high voltage circuit. And I've of course reproduced the Tesla coil designs. It's just a Slayer exciter Tesla coil. And these are just with 1 transistor, 2 transistors in series there. And yeah, that's basically it. I've also tried to make a faster spinning one with a larger motor here. So there's some improvements to this Graviflyer frame design. There's acrylic arms instead of the aluminum, so they won't short to ground because these legs are connected to the center plate, which has AC on it and touching the ground there. So the high voltage on the plate will want to jump down or across there. So with these faster motors, though, I'm able to spin at higher RPMs, see if that makes any difference. And Mark has helped me CNC cut some of these discs so that they're less wobbly than the hand cut ones Alex has been using. And I was able to find and kind of reverse engineer the rest of the design. So I put that online and on Facebook, on my Facebook, and on the American Anti-Gravity Facebook. So I'll keep trying different variations of it, see if that makes any improvements on it. But yeah, still testing myself and using this neon bulb and oscilloscopes and other sensors, high voltage probes, making sure it works. And some other Tesla coil designs. And this signal generator for the ultrasound, variations on that. But yeah, again, I haven't noticed anything different. One big thing I did notice that was a mistake on my part was getting these cheap converters from a European outlet to an American adapter. By doing it that way, I'm not actually getting the voltage like the 220 volts I need. So I'm getting a different converter box that'll convert the voltage, hopefully. But I've also got the car battery. I've been testing with that for a while, and this will be easier, I think, to test rather than getting all the adapters and all that for the European power. And yeah, that's about it for me. That's the updates for Gravify.
One question: when you're spinning the disk, have you done any experiment? For example, if you keep the voltage constant and you spin the disk at different RPM, are you getting any kind of voltage variation, voltage differential between the 2 plates when the spinning, as a function of RPM?
Yeah, well, as it spins, I haven't noticed any voltage change on the plates, but I'll make sure they're charged by using a shorting wire or a high voltage probe. And I've adjust the height and distance between the plates. So Alex Turkoff said that's one of the difficult parameters of adjusting on this, where you need this distance to be precise and the distance here between the center plates be unique as well. So I've been trying different heights for those as well.
But do you get a voltage variation as a function of RPM when the disk is spinning, or is it remain constant?
It remains constant. Yeah, unless it shorts to the frame or to the center plate, the voltage on them remains the same.
Oh, okay.
Yeah, it's about as Alex Chekhov wrote on the high voltage kit, it was about 20,000 volts.
Okay. And we're on suspended animation where for us to see you make that thing fly.
Okay, thanks. Yeah, I'll keep trying.
So we're being suspended animation until it happens. I hope you make it happen soon.
Thanks.
That way you eliminate all the waiting.
Yeah, me
Good
too.
work. Good work. Thank you.
You're welcome. Thanks.
But what new have you learned from it? Tell us from what the experiment you have you done some experiment, or are you going to do new experiments, test something new and different to get closer to that goal? What is it?
Yeah, I've learned more about the Slayer exciter Tesla coil design, electronics, learned more about the ultrasound circuit. I found it interesting that Alex wrapped his own transformer from an inductor. So I thought that was something they don't teach us in school, even though I'm a PhD student in electrical engineering. He was pretty creative with that. And of course, I was able to reproduce all his circuits. Here's his gravitometer, he's calling it, to help measure the fields around it. So I reproduced that. I made a copy of this and gave that to Mark. He has one like this. So he's using an analog high voltage meter to measure the fields around it. It's pretty clever. So yeah, each part of the circuit and the Graviflyer is pretty interesting.
Are you measuring the gravitomagnetic effect on that particular equipment?
Just basic voltage potentials from oscilloscope, and this meter is measuring like the high voltage fields around it. It'll light up red or green.
Oh, okay. All right, cool, super cool.
Thanks. Yeah, here's the original Alex Chekhov design there.
Table is 18 inches deep, 16 inches wide. It's that thick. So it's in perfectly in that space.
Well, your buddy's a fucking ignorant hillbilly sometimes. Remember that. Oh gosh.
Oh. Hey, Charlie.
Hey.
So you're not going to show us the coil?
Can't show the coil. Why? Why not?
I can't. Well, I was asked not to.
Oh, well, how does he get over? He's in Portugal still.
Well, until we could, get permission to share that other coil, that'd be good. Or if we could verify it ourselves independently, that would be good too. I know Todd's kind of shifted gears too. He's not working on the Graviflyer as much, working on the coil.
Yeah, life bit him in the ass too. He's got to deal with some stuff not pertaining to propulsion. It's called life in general. So, oh, cool. Let's find the frequency. What's the liftoff frequency? Come on, give it away. Spill the beans. Make it fly.
Yeah, that's the trick.
Is it? There's got to be a feel to it. Fred, let's fly it up to Hutchinson, and maybe he can like do some Hutchinson effect on it.
Maybe. Yeah, we can maybe visit Hutchinson. He's going to be working on his setup again. Hopefully, in summer, he'll have a better internet connection. His house will be complete, and he'll start demoing some of his effects again. He even showed a micro effect where a wire kind of exploded while he was testing a few weeks ago. I don't know if you saw that.
Floating wire. Sorry, the compressor's on. So, the floating wire, or
no,
he made it like it just turned into butter. It crumbled and it fell in on itself. It manifests some strange effects with metal. So I could only see it. I remember it vividly. Like I was, sober down at UNM, locked up in the basement of the business library, and then for breaks I would look for UFO films on YouTube. YouTube was a different beast back then, and the Hutchinson effect, some of it's just been wiped off. Or it's maybe it's restricted. I should learn VPN. Maybe I can find it that way.
That's strange.
Well, Hutchinson might be able to help find the lift off frequency. Or you just, if he's in Portugal, wait until all of the silliness in Europe's over and fly over. There's there's got to be something through your university where you can get travel funds. My UNM had one. It was great. Like you go up there, and they're like not the student union building, but the student services building or something, and they could fund you like a couple $100, like $800 or $1,000 for some of these events. So, or talk with the dean of your college. If you got a PhD, there's some way that you're trying to. Sometimes the teachers, Christos at UNM, he sent me to DC to attend the FAA conference. So it was cool. Like, use the university, man. You're still near it. You should be able to get over there. Go get some.
That big initiative. It's just Alex. He doesn't want people visiting him.
Well, I know, but you're like one of his disciples now. You have a machine that he made, so there should be some. We don't ask him. Why not?
Yeah, we've also tried to ask Alex to come here to the United States, and Mark agreed that if he wants to come here, stay at Mark's lab.
That'd be cool.
Yeah, we're trying to arrange that. He might have changed his mind recently.
Привет, как дела, Алексей? Очень хорошо. Я говорю по-русски язык. I don't know if I am Russian. I'm almost fluent in. If I learned that at the ISDC last week and a couple of weeks ago now, and there were people there, professionals. Some blonde. She was working on medicine and stuff. She had questions about the Havana syndrome. But yeah, she was just blabbing away in Russian, and I was like, oh, totally understood. It's kind of neat. So, Alexei, привет. Поход, поход, that's hike. Самолете. I'll remember. There's certain words I don't have anymore, but get on the plane, man.
Right. Yeah, and Mark offered, Daria to help translate as well. And we have Mikhail from Russia that might help translate.
Oh, yeah. You'd be amazed. I think like your iPhone and the little AirPods now are almost like instantaneous translation, right? I mean, there's something like that out there.
With the universal translator from Star Trek is in your phone right now.
Your AirPods, yeah. Anyway. Oh, some people got to work on holding the world together.
Yeah, and the craziest thing is, while they're translating, they're also feeding their metadata to the Google searches. So if you talk to aliens about bismuth magnesium, they'll try selling you it with directed ads.
So on APEC, has no one come with a proposal for a teleportation system?
No.
They consider propulsion, or?
No. No, I'm just out of curiosity, because I know there's research going on in that area, but they've done it in the lab, but
The Tear in the Sky documentary, where they just saw the alleged wormhole.
A wormhole. Oh, okay.
It's a new documentary out. Will Shatner and Michio Kaku.
Did anything come out of it? I mean, was that a travel portal or?
Yeah, it looks like tickets were in there, and maybe a TikTok thing.
When they went to San Clemente Island and set up all the equipment looking for stuff.
Yeah, that was Christopher Altman, I think, right?
Yeah, there was lots of hype, and all they found was a cloud that disappeared.
I'd say it was
Yeah.
So they call it a tear in the sky.
Tear, yeah.
Yeah, there's a lot of movies like that.
Well, at least they were intellectually honest and showed us what they found, and didn't make shit up. I appreciate that.
Yeah, I was telling Jeremy in the comments, if you go to their UAPX website, they gave updates after the documentary with some of the details. Like one of the IR cameras went out, and in the documentary they thought that was a EMP effect from the UAP, but it ended up being they forgot to plug in the power, so the batteries died all in unison.
I mean, that's the reality of testing stuff, right? Is, especially with stuff like that, you're looking for something that's kind of an anomaly and an exception by definition. So it doesn't surprise me really, you know, and I don't think that's a bad thing. It's just like, okay, better luck next time, right? You know.
Probably, yeah, releasing the documentary there, they only had that one.
Yeah, it's
And-
like you go out looking for Bigfoot. Maybe you'll go where he's been, but you know, just what are the chances that you're going to see him? I mean, it's the same. You know what I mean? So I don't know.
Yeah, that's interesting. They decided not to try to guess at what they were seeing. They just wanted to present the data.
Yeah.
Pretty good.
Well, guys, have we just about wrapped up today's conference? Do you think, or? Yeah. Well, let me stop recording then, and I will do that now. This has been one heck of a conference.
Recording stopped.
Perfect. Okay. And if you want, I could make Mark the host or something. Or Phil, if somebody else wants to host. If you guys want to keep talking, or we could just close it down. It's up to you. Or I could just let it run, but
you need to eat badly right now.
Okay. Well, why don't we close things down for this evening then? And guys, this has been one heck of a conference. I'm really pleased as punch. We're getting the show back on the road, so to speak. And Shreesh, thank you so much, sir, for presenting.
No, it was great. You know, I mean, I know what I'm talking about is really controversial because it's not an electromagnet. It's not normal in the sense it's very thermodynamic. You know, so I totally understand. You know, but I've had similar blank looks when I actually submitted to NSF. You know. So the review comments was again blank, you know. So
it takes people a while to digest it. I think that's what it is.
You know, like you know, when one of my advisors, right, what I mentioned, I mean, he comes from a propulsion systems background, right? I mean, he was an ex-submarine commander, of course, in the Navy, right? And so he knows propulsion. So I told him, like, you know, I like to think that this is a right brain kind of science because you can't look at it straight lines. And this is my biggest problem in explaining this technology, really speaking. You know, you know, people ask about thrust. And I say, well, there is motion without thrust. So it's kind of difficult for someone to get it, kind of.
Yeah. Yeah. It takes a while. It has to kind of percolate.
So I know my challenge is there. I mean, I'm not denying it, you know, but I have to thank you for allowing me to, you know, discuss this in this forum. So definitely, I think the next one I will figure out maybe some way to water it down a bit so that, you know, people can understand it better. You know?
Yeah. No, and we'd love to have you back. Yeah, and you know, we do have folks represent on the same material multiple times, and so, you know, yeah, if you can find a way to make it, I mean, any way to make it more accessible to people. You know, and then they can come in easy and they can learn hard. We've already got the more challenging one. So
yeah. That's definitely. I was kind of debating. I just tell you this. I was debating whether I should dig deep or be very high level. And I said, okay, let's do a little bit of dig deep. You know, but I think it was too deep.
Yeah.
I think this one, the lot of it would be something that, you know. Someone in the academic field who's like an expert in thermodynamics and superstring technology, so to say, science would really understand. But otherwise, because it's just not the normal scheme of things, right? No, there's not that much research in the superstring science area. So there's not even too many people who know about that area. So
yeah.
So
awesome. Okay, well, have a wonderful weekend, guys, and I will start putting this stuff up online. I mean, so the live stream is already up online on the Alien Scientist channel, and then kind of the archival version, if you will. I'm going to start editing that, and I will get that up online the next day or so. So,
okay.
Thanks again.
Okay,
have a great weekend,
everyone.
I'll get a, there's a rubber band.